Hello, I'm Dustmite. I am a C programmer, and on this channel, I make videos about my projects. Um, I haven't made a video in a long time though, and it's because I've been working on this. And one day I knew I would sit here and record this very video. It's why I've crawled through so many papers and pull requests and stuff, trying to figure this stuff out. Is because I wanted to sit here one day and tell you all about it. I'm going to give a brief introduction to the video. I'm going to try to be brief. This is my second time recording this. There is going to be a chapter that you can skip to if you want to skip it. I'm going to be talking about introducing the terminology, the purpose of the video. I'm going to be giving my opinions on certain things. I'm also going to give like a pre-appendix to all the resources. I'm going to talk about what makes chess programming so special as well. But there will be a chapter for you to skip. So what is the purpose of this video? Well, I get sometimes when I do my streams, I get people that come on and then they say, I'm learning C from a book, and I'm not really getting it. What would you suggest? And I always say, make a project about something that you enjoy, but that's a bit open-ended. So I always say chess engine. And why? Because a chess engine is a very simple in terms of coding. It's very simple. However, it's very complicated and difficult in a totally different sense, in the sense of comprehending what's going on and understanding the various techniques that other people use, right, and implementing them yourself. It's kind of a different difficulty. It's sort of, you kind of have to be a historian and go through all these, pull requests and forum posts and stuff and try and figure things out. And read papers on logistic regression, if you plan on implementing your own tuner, which brings me to my next point, that all of the code in my engine and in this video is going to be implemented in C with only the C standard library. It's how I prefer to do my projects. I'll use OpenGL or etc. But I try to keep things just only my libraries, or just no libraries, because I like coding, so I don't like any opportunity to not code. But yeah, I will be talking about some really good resources though, because you're not going to be able to do all of this yourself without reading other people's code, which brings me to my next point, that the code, my code base will be available on GitHub, including my tuner. I have to definitely clean it up a bit, but hopefully I think I have to put it up by the time this goes live, and so that's what I'm going to be working on. I've already started commenting a lot of stuff, so I also wanted to talk about what is my purpose in why such a long video. It's going to be long, because I think my kind of understanding of the way the world is right now is that we have ChatGPT and all these AI LLM stuff, and it isn't because they're smart that they're so widely used. God, no, they're very, very, very bad at giving any accurate information about anything beyond what the color of the sky is. No, they're quite bad, but they are better at being humans than humans are right now. I think humanity has failed, and so we're living in the age of information, but none of it is given with kindness. You ask somebody a question, and they're aloof. Anybody who has information, likes to feel powerful, and stuff like this. And I just can't stand it. I think information should be given in a way where you are willing to answer any follow-up questions, and want somebody to give them help, just because you think that it's neat. And so that's kind of the thing here is send me a message or leave a comment or whatever. I always respond, and always will respond to any follow-up questions, because I that's kind of the whole point, is is I don't know, if I can take even a couple of pennies out of Sam Altman's bank account, then that's what I'm going to do. So yeah, that's that. I think so. I want to talk about. I want to convince you of why a chess program is important, and impressive. Because you may think of it as just a toy or just a bot, right? A chess bot, it's not. I would argue that a chess engine is something different than a chess bot. An engine is very much like a game engine. What else is on this channel? It's a very complex thing with a lot of neat things going on in it. And I wanted to give like an introduction into what alpha beta is and the math behind a chess engine. We are going to be talking about everything from bitwise operations to machine learning today at the end. And so I'm going to take you from the very beginning to the very end. We're going to be talking about how to make a strong modern chess engine, not just, any chess engine. And so there are some things that you have to understand that I didn't understand when I made my first chess engine. Even coming into this one, I was still like kind of foggy on what alpha and beta are and what they mean. Okay, so alpha, beta, okay, are your lower and upper bound. Okay, when we get a position, I also want to dispel the notion that a chess engine is some backtracking algorithm. It is not. It also isn't a calculated machine that looks at a chess position and tries to figure out, how do I solve this? No. It's the opposite. It's an aggressive sort of program that, discards any position that it seems might be impossible, right? And so how do we decide which positions to discard? Well, a lot of different heuristics, but the foundation of what we call an alpha beta chess engine is that we have these two bounds. We have a lower bound named alpha, we have an upper bound named beta. And I wanted to just give a simple scenario, right, for you to get a peek into what we're going to be talking about, right? And so you're going to start from your search, right, and you're going to have all the legal moves that you can play. Well, pseudo-legal, but we'll get into that later. So we're going to play a move, okay, and then we are going to switch our side to the opponent's side and play a move, okay? So we're going to do that all the way down the tree until we evaluate, right? And then we're going to go all the way back up and get a score, right? A chess engine has a lot of recursion in it, which makes it kind of hard to debug sometimes. But you're going to get a score back for that move that you played, okay? Now, what we're going to do is, when we get that score back, if it is greater than alpha, which right now it is because it was negative infinity, we're going to raise alpha, okay? So we raise alpha to that value, okay? Now, why is this important? Because every time we recurse down, we're going to swap alpha and beta and negate them, right? And so the idea is that beta, let's say it was negative 45, we got that score back, okay? What that's going to be for the child node is a 45 beta ceiling for its upper bound. Now, we are going to, progress, and then we're going to play another move, right? And then that alpha will become beta for the child node, okay? So their ceiling is 45. Okay, what does that mean, right? Is that they are going to play a move, recurse all the way down the tree, and then they're going to come, the score is going to come back. Let's say it's 80, it's above 45. What does this mean? Well, it means we can do what we call a fail high, okay? And cut that child node off and stop iterating its moves completely, cut it off completely. It doesn't exist. Now, why? Well, the significance of that negative 45 alpha for the parent node is that we already had a move that was that good, right? And so us flipping this is basically flipping it to the other side. If the other side has a move that is now greater than 45, that 45 for us is that negative 45, okay, which we already got for the move we already played, okay? So if we play a move and then in the child node we discover that it's already past that 45, we know we already have a move that was good enough that we would never look at that other move, okay? And what we do then is we simply cut off that child node, okay, and stop looking through that part of the tree. This is the basis of what an alpha beta chess engine is. It is us playing with these lower and upper bounds and seeing how far am I under alpha, how far am I above beta. If we're in some sort of pocket, if we want to update some heuristics, this is what it is. And so I hope that me giving you that insight into it would dispel any sort of notion that this is a simple thing. This is not a simple thing. It's a very complicated thing, but the code for it is simple, and that's what kind of makes it like a special type of programming. What else makes it special? Well, I think you become sort of a historian when it comes to this stuff, and reading these sorts of things. If you go on this journey of trying to implement a chess engine yourself, you're going to come across these talk chess forum posts between these people, and these names are gonna stick in your brain. It's this sort of like historical unraveling, like X was arguing with Y about this, and then you're gonna find them later down the line, these same names. It's something very, very special about chess programming, is that you're kind of entering into this like rich history. I haven't found that with really anything else. I highly recommend you treat it as such, though. Don't treat it just like any other task. If you want to make a strong modern chess engine, I think part of the joy of it is uncovering all of the history. In it. That's what I enjoy most about it. Now, to talk about all the resources that are going to be in the video, I want to talk about first and foremost the chess programming wiki. I think it's like super pretentious, but also cool that it is pretentious. You're going to go on there and like look at their pages, and on their pages they're going to have all these links at the bottom, to like jazz concerts that have the same name as the concept that the page is on. It's wonderfully pretentious, but I think that speaks to kind of like what chess programming is that it's like this sort of there's this sort of like meditative artistic quality to it that is different than other engineering programming things, and so it's similar to a game engine in that way. And more importantly, though, is all the links are very important resources at the bottom that are going to link you to all these forum posts where they talk about these topics for all of it. And so I think that that's like the greatest single resource for sure. Other than that, we're going to be talking about everything from magic bit boards to this and that. So I'm going to recommend first of all, like in order, right? Read the page on FEN notation, okay? Read the analog horse blog post on magic bit boards. I'm going to reference that later. Also, get a reference engine. There's a page on the chess programming wiki where they have all like 1,000 engines or whatever. Just go to whichever one has like a cool name, and read their code. Not right away. I recommend that like once you have made the search and made your evaluation and stuff, just to like get ideas, and figure out, they did this way, why, a big part of this is going to be reading code, but you can also read my code. It's going to be on GitHub. So yeah, I think that that's pretty much it. Also, I want to give a shout out to like, I don't think that there has been much like good chess programming stuff on YouTube in the past few years, but Code Monkey King's Blue Fever software, very important to get a handle on certain things. I remember when I made my first chess engine, it was definitely like the single biggest resource for me, because Code Monkey King's really, you'll see him on the forum posts too. Like he really wants to understand, and the amount of work that he put in is just incredible. So, with all that being said, I guess we can start talking about things. And this is my second time recording this, so I already know my bias. I started talking about move generation before I talked about game position setup, before I talked about FEN notation, FEN parsing, and I want this video to be completely accessible. Also a big thing for this is to be completely accessible to people that barely know how to program or don't know how to program yet, or are new to it and learning from a book, because this is the project that I recommended them to do. And so I'm going to be explaining things like bitwise operators, pointers, and things like this as we go along in an accessible way. I'm sorry if that frustrates you, or if it's not information that you need. I think it's very important to, because otherwise, what's the whole point in the video? So with all that being said, I want to start talking about the code. Oh my gosh. Yeah, so this screen capture, I'm going to have to restart it, unfortunately. That's unfortunate. Okay, there we go. There you go. So I have to also transform this to fit the screen. There we go. And now I disappeared. Okay, we fixed it. Before I start yapping away, I know that there's going to be a question here about like, what's my theme, what's my development environment, what's my font. So I'm also going to have in the description the repository for that. The font I'm using, especially to be readable for this video, I usually use weird fonts, but is Iosevka Slab. Okay. And the theme is my own. I'm using Helix as my editor. Okay. And this is a new theme I made. I really, really, really enjoy this theme. I do have to bring the diagnostic info back, like it doesn't show on the bottom anymore, so I have to fix that. But otherwise, I think I really enjoy this theme. I think it's super minimal and really non-intrusive to work with. Okay, so how do we make a chess engine from scratch? I'm going to run you through the basics. Okay, so I recommend, very, very first thing you do, you're going to want to make a few structures. Okay, we call them structs in C, which are basically just layouts for memory. Okay, we have members inside of a struct like this. Okay, so we have members inside of the struct, right? So this is a side, which is side to move, with things like this. Okay, side to move, this side is simply an enum, okay, with 3 different things inside of it, right? It has black, white, and both. Okay, so black in my engine is 0, white is 1, and then both is 2. Okay, so this would, in terms of what these represent in integer space, is 0, 1, and 2. Okay, so when it's black side to move, we have it at 0. When it's white side to move, we have it at 1. But it just encodes itself as a side, which we read out as directly that. It just makes it, there's no difference, okay? It is literally just a way for us to read it, okay? Make it readable. But this would be the same if I simply had this as an integer, okay? So that's basically what it is. So a struct, this is my game struct. You'll also hear this be called a position struct. Okay, this is everything inside of it is stuff that is our position information. Okay, so you're going to want to make this. I recommend you go and look at the page on FEN notation and simply put that stuff in your game struct. You're going to put inside of it the side to move, the en passant index, the castling flags, and the board, which is what I want to talk about next. The amazing mathematical thing of a chess engine is uint64t's, which are 64-bit integers. The thing about 64-bit integers is understanding there's a word for it that I'm not getting, is the observation that there are 64 bits in an integer and there are 64 squares on a chessboard. This is very significant because now what we can do is have a 64-bit integer that has every bit as a square on the chessboard, as 0 or 1. It's very, 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 very convenient thing. And so what we're going to be doing throughout our chess engine is we are going to be doing a lot of bitwise operations on these 64-bit integers. Okay, I will give examples of this later in terms of what they look like, but you're going to want a integer for each piece, a 64-bit integer for each piece. Okay, so it's very important, an unsigned 64-bit integer for each piece type, right? And so your pawns will all go on 1, and then your bishops will all go on 1. I have it per side. You can also do it both, have both on them, and just have a board with each pieces, and then just and them together. I just like it this way. Is the way I have it. You're also going to have one with board pieces. Okay, I have these enums color max. Okay, this is just a very simple way for me to write 2. Okay, in my engine. Okay, so this is for white and black. This is going to have a max of 2. Okay, and this is color max plus 1, right, which has both. So board pieces, I have white, black pieces and both pieces on one board. That's basically the structure of it all, right? So color max plus 1 is 3 here, right? So black, white, and both. And so that's basically what's going on here, and that's the back end that you want to make before you even get into move generation or whatever. So I recommend all of that. Now, how do I make a program though? How do I make a program if you don't know how to program? You know, you may be like a bit like how do I get in a string? You know, or well, the way I typically do it is I just have an integer that is running or it isn't running, right? If it's 1, the program is running, and if it's 0, then it isn't running, right? And I use a while loop here, okay? And this while loop is we exit out of the program when running is no longer 1. Okay, so that is how I do it. There's probably many other ways to do it, but I typically do this in my programs, right? And so I have this initialization routine before we go into this, right? This init routine basically does all of the making of all these pre-computed bit masks and hashes and all of this. You don't have to worry about this right now, right? But just keep this in mind. I will be talking about the initialization stuff later. Okay. So we get down here, we are handling our input, okay? So we are running, we are handling our input. The way I handle all of this, right, is I just simply use fkets to get in an input line. I highly recommend you do that as well. Probably use a bigger line size than 100, but regardless, yeah, so I use fkets in C. I get the line, and then we tokenize the line. STRTalk is a function that basically takes in 2 arguments, which is our line and the delimiters is the word I was thinking of. The delimiters are space and our new line character. So basically we're saying if there's a space, then we want to break on that. If it's a new line, then we want to break on that. Okay, so the reason why this is significant, right, is because when you're taking in a command, right, you want to have a first word and then arguments after. So you just want to tokenize it, get the first word, and that's what it is. Because if we have a space here, if we had an L, it would switch on all the L's. If we had an A, so that's what this is. So we tokenize it, but you can also use STRTalk R. I'm not going to go over that, but I use STRTalk R otherwise in in other places in the program. So you're going to want to tokenize it. So switch on the space, and then your first word is going to be the command, okay? And I have a command called fen, which I use and then everything after the fen, I just input the fen, right? And so I set the command to command fen, and then down here I have the switch case for all the commands. The switch case in C, if you don't know, is basically just a way to, you have a variable and you have different values that variable can be. You just have all of these cases down here with all the different possible values it could be, and that when we have a command that's command fen, we just come down here in the switch case, right? We set it to command fen, and then we come down here and we tokenize it again to get the rest of the token. Here you pass null for the pointer. It's kind of weird, but yeah, it just uses the pointer that you already tokenized and then just gets the rest of it. And so obviously when we have a fen, I type into my engine, I type in, fen dat, and then that works. So that's how that goes. And we call setBoard to fen. Your fen parser and your fen set is going to be the first thing you create within your engine, other than the setup that we just talked about. So what is setBoard to fen in my engine? Well, it's very simple. What you want to do is you want to initialize your game struct first, which means everything you want to set it to 0 or some they call it sentinel values. Okay, not that complicated. Okay, you just want to set all your your bitboards to 0 for now. The rest of the stuff doesn't matter yet. So we are going to go through how to tokenize and parse a fen. I did this on stream also. I think it was the first of the second episode, but I'm going to go over it briefly here. This can be done a lot safer. Okay, I think probably should do it a lot safer. This probably isn't the best example for my engine. I kind of made it once and then forgot about it. You should be checking if the tokens are your null terminator. Okay, you should be doing that. I don't. But just don't give it a garbage fen. Anyway, so we're gonna go through the beginning is we are looping through all of the pieces. Okay, now if you don't know what a fen is, I want to talk about that briefly. Okay, I'm just gonna go to the bottom here, and here we have our fen. Okay, so this is a start position fen from white to move start position. Okay, so this is what a fen looks like. It has the entire board encoded in rows, and each new row is a slash, and then the amount of white spaces is 8, right, for an empty row. And so following that convention, obviously, if you have a space, if a pawn isn't there, you would have a 1, or if 2 pawns aren't there, then you would have a 2 to represent the empty spaces. Okay, so that is what that means, right? This is what a fen looks like. You're going to parse through all of that, and obviously once you get to a space, you're going to get to the next thing. Everything is separated by a space, by their category, right? And then next would be side to move. Then these are the castling rights for both sides. This is white, and then this is black, right? Lowercase is going to be black, uppercase is white. And then you're going to come to here. This hyphen is actually the placeholder for everything that might not have a value, but it is actually the en passant square. Okay, so that's very important, right? This would be whatever in terms of integers to give you which square is the en passant square. I'll be getting to that in a bit. We also have half move and full move clock at the end. Okay, so that's all of that out of the way. I want to go back up to not output game to fen. No, right here. Okay, so we switch on when it's a slash, and we basically increment the row. Okay, I recommend you just do this from scratch. It's not too complicated, and it's a fun little exercise. if it's a digit, we do this neat thing with ASCII, okay, where if you have a single digit, then you can subtract the 0 ASCII character from it in C, and I'd imagine other languages as well, and this will just give you the number itself, right? Because they're next to each other. So a char, if you don't know, is just an integer. Okay, so basically that the 0 character, you're subtracting it, and then they're all lined up after it. So 1, 2, 3, 4, and so if you subtract 0, then you get that number, and so you find which you get the amount to skip spaces, if that's a 1 or a 2 or whatever, and then you increment based on that. What I wanted to talk about here is we get into the first putting a piece on the board. Okay, we're gonna put a piece on the board, and how we do that, I was writing this earlier. You don't have to have a function like this. This is really old code. Basically, what you want to do, just ignore all of this. By the way, this is all stuff that's we're gonna talk about later. Okay, but just worry about this. Okay, this is how you put a piece on a board. Okay, you just OR it with that piece. Now, what does this mean? What are these numbers? What is this doing? 1 ULL is you're saying 1 unsigned long. Okay, that's an unsigned 64-bit integer. Okay, this is just a one bit on that. So a 1. If you don't know like bits in binary, you're basically just saying this is 1 bit at the first position, and then we are shifting over by this index. So we are basically pushing it to a certain position on the bit board. I'm going to give an example of this later, but you can think of what is an index on a bit board. We are just going to shift that 1 bit at that starting position all the way up. Okay, so that's what that's doing. When you're shifting to the right, you'd be going into the opposite direction. Okay, so this just shifted to the left, which is okay. So you get to that index, and now you're ORing it with the current board. So let's say you have a board with a bunch of pawns on it. Okay, now you have that extra pawn because you OR it. ORing is we are going to have both. Okay, so we're going to have both what we had before and what we have now on the same board. Okay, if it's AND, okay, then we are only going to have the overlap. Okay, it's very simple. So I want to give an example of this to people who don't know how this works, right? We're gonna say we want to print out the whatever board this is, so side type, and I have a piece thing here. So the one before we're gonna say white pawn, and then the one after we're gonna say black pawn, just to show off what's happening. And then I'll just compile the engine here and then try and show off what I'm talking about. It does take a while to compile because of all the inlining that happens, so I apologize for that. So how are you doing? Okay, there we go. So I'm showing you exactly what's happening here. Oh my gosh, you know what, I believe I messed up because of this, so now we have to wait again. Yeah, I apologize. I did do this right. Yeah, I did. Okay, so there we go. Okay, so obviously you have the white pawn is what it was before, and the black pawn is what it is after. So this is basically just, we had this here, and now we have two of them because we put one here. This would have an index of, well, we're going from here, right? So this would be an index of 62, going from 0 to 62. Okay, so that's what we did. We pushed this bit all the way, and then we ORed it so that ORed it with this so that both of them are there. Okay, hopefully I explained that good enough. Okay, so that's handled. now you know how to parse in and put stuff on the board, hopefully, right? Okay, so moving on. You're going to parse the rest, tokenize the rest, just, basic character stuff. You're going to check if a character is white or if it's black, and then set the side to move. You're going to do the castling flags. My castling flags are uint bit mask. I recommend you just start with booleans, okay? It's only marginally faster otherwise, and when it comes to the polyglot stuff, you just have a lot less room to work with, but do it whichever way you want. Also, I want to just do a thing here, because a lot of things in my engine have been optimized to a point where they should look different from your engine starting out, like 16-bit integer moves, for example. These things are honestly a pain to debug, especially if you're just starting out. I highly recommend you don't do that. Anyway, man, this coffee tastes like alcohol. Okay. Oh. All right. So you get the en passant. The en passant, if it's a hyphen, would be 0, would be no en passant square. If you don't know, to give you an introduction onto how en passant works in chess, if a pawn double pushes, it can be en passanted by a pawn capturing the square behind it. Now, we are only going to have an en passant square, if we read the Fen notation page, if a pawn double pushes, then we will automatically have the space between it be the en passant square. So that's what this represents. In my engine, no en passant square is a -1. Okay, because if we have it be a 0, then a 0 is still a valid space on a chessboard, because we go 0 to 63. In all programming things, we start at 0. So, okay, so we set it to -1 if there isn't one. And we do full move and half move. You're not really going to use this, to be honest, but yeah, I just use Sturtol. And down here, I'm doing a bunch of initialization things that aren't going to really make sense yet. It's a lot of hash key initialization and stuff. We'll get into that later. Okay, so that's basically how you parse a fen. Okay, hopefully, it's not too complicated. So, I think it's time for us to get into movement generation. That's like your next logical step. Okay, so you have that command. You say fen. You put in a fen. Okay, you set your board to a fen. I could show off, actually, by the way, I do have to make a note here. The name of my engine used to be Vixen, and now it's not. I still call the binaries this, but Vixen apparently is a name that was taken by another chess engine, and now the name of my engine is Sarah, after Sarah Records. So, to give you, I don't actually have a fen on hand, and I would just be setting it to the other fen. So just pretend like I put in a fen there. And in my engine, the way to get moves is just press auto. This is like, I guess, a look into what's going to happen later. Okay, with your search, how to get all this debug stuff working and all of this. I don't know. I just wanted to kind of put this here as like this is what it's all about. This is what it's working towards. Okay. I think that like the next thing is to naturally do the movement generation. I have it inlined. You don't have to. So what are we doing here? What are we doing here? So pawns are the most complicated ones. Okay, so we're gonna talk kind of a lot here, just to try and explain what's going on. Okay, so let's talk about the arguments that we're taking. We're taking in a move list. Okay, when you have your generate moves function, you're just gonna have a move list that you pass into that. I have a move list basically on my search. I create a move list and then I pass it all the way in. You're also going to have a move count. Okay, I just use a uint since it happens to be the exact same amount as the 256. Okay. Amount of move list, you don't need more than 256 moves. We have the side, whichever side we're generating to, especially important for pawns because they're going to be moving in different directions based on the side. We're going to have potential captures and own pieces. This is simply just a way to reuse without another pointer dereference for all of our pieces versus all of the enemy pieces. Okay, and then we have only non-quiet and generate checks. In a chess engine, we're going to have something called a quiescence search. When we are searching, okay, we're going to get to the bottom, okay, the bottom and bottom out, right? And instead of evaluating from that position, we're going to want to get to a quiet position first. A quiet position is a position where there aren't captures, okay, or aren't promotions. The idea behind it is because quiet positions are ways that we can evaluate because there isn't immediate material that's going to change, right? Let's say you hit the bottom, you bottom out your search, and your queen is about to get captured, right? You would evaluate that, and in a modern chess engine, you probably wouldn't have that bad of a horizon issue, but the idea is you want to keep searching until all the captures have been played out, so that you have a safe place to evaluate. Okay, and so that's what that only non-quiet generate checks is about. It's different stages within our quiescence. Okay, we only want to be generating non-quiet moves in quiescence. We don't want to be generating just random pawn pushes and stuff, but we also want to generate checks in QSearch up to a certain amount of plies, and I'll get into that later. I generate 2 plies of checks. There's a few reasons for that, but it won't make sense to you now. So that's why that exists. Those flags exist. They exist so that down here I can check down here. If we're only generating non-quiet and we aren't generating checks, then we can simply return out without iterating the rest of the moves. Okay, so there's that. pushes the foundation of a chess engine. So right now these are not sided. Okay, it's not sided because I'm lazy and I didn't want to swap it around. Okay, obviously in a game of chess, your pawns can only move in one direction based on which color you're playing. So this just represents that. Unfortunately, you cannot bit shift a negative direction. Okay, it's going to get mad at you here. You can't. That would be really neat because we wouldn't have to have these conditionals, but we do. If you don't know, this is just an if-else statement inlined. That's what these operators are. This is if it's not side, then this, or else this. To go back to what I was saying about enums, this side is if not side. If it's black, if your side is black, then you're going to be doing this, and then if it's white, then you're going to be doing this. Okay. Otherwise, it would be if white, do this. Like this would be if white, then you do this. If it's black, then you do this. Okay. Hopefully that makes sense. So why the blockers? Why the blockers? This is actually important, right? Concept here. Because I used to, in my old chess engine, and when I was setting up this one, I did each pawn individually. Believe it or not, this is only marginally faster. But yeah, I did each pawn individually. And because of the double pushes, I couldn't figure it out. And it was because you would have to jump over pieces. You'd end up jumping over pieces if I did them multiple. The thing is, you want to stage it. You want to stage it, right? So you have your pushes, you check against blockers, and then your double pushes, you check against blockers again. You don't do them both at once. That's the way I thought about it, was like you would have your pushes and then you would have your double pushes that you go from starting position up to your double push masks. No, you want to do your pushes. You want to take those pushes that you just made so that your pawns don't jump over pieces. This and not, if you aren't familiar, an and not is removing the bits from our bit mask, right? So let's say we have these pawns, we push them up 8, okay, and we want to make sure that there isn't a piece at that position. Okay, that's what this not blockers is doing. If there is a piece at that position, we are removing that push from our pawns. I kind of want to make an example here. Okay, so this is what this is going to do is it's going to show us what the game board is, and then after we push, what the mask looks like. Okay, so I'm just going to do that just to show what I mean visually. Yeah. Okay, because it's multi-threaded, it's going to do this. Can I get one that wasn't mangled? I'm trying to do a video here. Okay, maybe we shouldn't multi-thread things when we're doing this. Okay. Okay, there we go. We got one. Kind of. Oh, we don't have it. Okay, okay, whatever. It's the same thing. Okay, so as you can see, this mask is the one that we are pushing. Okay, so we have this exact structure here, and we just push them up one. Okay, we don't have any blockers, but basically, if there was one here, then we wouldn't have this bit here. Okay. Yeah. Yeah, my computer lags, and then the stuff gets mangled, unfortunately. So hopefully I might have to pause and do some things to make it more readable. Okay, so now we have our pushes, and then we push our pushes again and check against the blocker mask to get our double pushes. Right and left attacks. Now, why is this kind of tricky? This is tricky because to encode a move, we have to know the start position and the end position. This is important because, when we make a move, we need to know what piece we're moving. Unfortunately, when we move all of our pawns at once like this, we don't know which one came from where. And so we have to do our right and left attacks separately because we need to know which direction to go back. Okay, very simple like that. Okay, so that's what this is. Okay, we are... The trick here is that we are shifting over 7 and 9, which are obviously diagonal, where 8 would be one row. This is just one row and then in the two directions, right? And we are ignoring our wraparound. Okay, so on our right, we may go this way, right? Actually, this is right attacks, but from a certain perspective. Okay, not from white's perspective. That's why we're doing not side right. So basically, if this goes off the board, we and not the file mask on the opposite side. Because if we go off the board, then we're going to wrap around, because that's how bits work, unfortunately, right? And so we and not the file mask on that side. Okay, and the same thing with the other side. Right. So we remove that bit. Okay. To go back to here, if a pawn is here and then it gets an attack here, right? This would end up here, and then you have a mask pre-computed for this, and then you just get rid of this, right? We're going to be doing that a lot of times in the engine. So then you get the mask for the overlap with the enemy pieces, and these are our captures, and then we do our promotions. Okay, these are our promotion captures and our promos, and then we remove them from the pre-existing mask so that we only push them once. Okay, so our promos and our promotion captures, I do a different function called push promo that pushes it with all the different promotion types, right, from knight to queen. And this is already showing you how we do the left and right attacks here. So we are adding one for our right attacks, and we are subtracting one for our left attacks. Okay, that's how we deal with it. I also have here a push direction that we're multiplying times 8. So if we're white, then we're going up. If we're black, then we're going down, right? And so this is how we figure out that, and we multiply it times 8. This is how we do it. Okay, same thing for left and right attacks. En passant index. Okay, so this is a bit more complicated, right? We are checking. This is why, by the way, we have we keep our RA and left A on a separate UN64T. We keep them there because we want to use them to determine if we are able to en passant. So if our RA or left A overlaps with the en passant index, right? I have this bits, which is just basically it's just pre-computed bits on each square. So a bit at the en passant index, if it is a valid en passant, if it is a -1, then if we have overlap with the left attack, then we push that as an en passant. You want en passants encoded as a separate type because they have special logic, especially when it comes to things later down the line. I'm trying to think of something that isn't just because it's an integer packed move. The first thing that's coming to mind is obviously when it's an integer packed move, we need to know, is there a piece at that square that we need to remove, right? An en passant is a capture where the piece isn't at that square. Do you get what I'm saying? If there isn't a piece at that square and we're making a move, we need to know if it's an en passant, because an en passant is a special case where the piece is already behind us, right? So that's that. Pushes, double pushes are regular, right? We just use 16 since this is 2 rows to figure out where we're coming from, and that's all the pawn logic. And that's the most complicated part of all of this, is the pawns. Now I want to talk about the sliders, which is the second most complicated thing, but it's not. I'm going to leave a link in the description to the Analog Horse blog post on Magic Bitboards, okay? I have used that both of the times making a chess engine. I have not made a magic number generator myself. I'm actually kind of interested in doing it now, but I've always been very confused about it. And that blog post is super helpful. They also have a list of magic numbers in their example, and that's exactly what I have in my engine. And so I just want to talk about all the setup you have to do for that and what magic numbers are and stuff like that. So a slider, a bishop, a rook, or a queen are different types of pieces than the rest, right? Because a knight cannot be blocked, right? Of course, it can be blocked on the square by a piece on the square, okay? But it can't, its moves aren't blocked. For example, a bishop, if there's a piece on a certain place, it can't go past that, right? This actually becomes a really difficult mathematical thing, right? For you to have to check if you're blocked. You have to step through the individual pieces and check if you're blocked. It's way too slow for a chess engine. What we use is magic numbers. Now, what are magic numbers? Well, the name probably keys you into what they actually are. Magic numbers are magic. They just work. That's kind of what they are, is that they're kind of like brute forced sort of numbers that we find that just are masks that we overlay with our masks, and then they just give us the correct answer given our occupancy on the board. So it's kind of magic that they work, but that's why they're called magic numbers. Anyway, so they're basically hashes. They're hashes. The first hash in the chess engines are full of hashes. This is the first hash. Okay. So we get our index. Okay, we get a magic entry that is index 364 for the position of our piece on the board. Okay. And then we will get the entry, and then we basically just take the blockers and it with the mask, and then shift it, multiply times the magic number, and then shift it over by the entry's values and add the offset. And this will just give us the index inside of the massive table. Now, how do we build that table? Okay, so this is the part that you're gonna have to do yourself. So this is what it is. I copied the analog horse way of going about things. I think it's a fantastic way, because later, when you are pre-computing bit masks for your engine, you're gonna want something like this, okay? Which you're gonna want to generate all the different directions, and so having a setup where you can just generate slider moves for any given slider delta is pretty convenient. Okay, so what are slider deltas? Well, for a rook, it's going to be -1, 0 is going straight down, right? Because you're not stepping in the x direction, it's just -1 going down in the y. For the bishops, it's going to be similar, right? Going -1, -1, like a graph. Okay, so that's basically it. These are all the directions, right, for cardinal directions for rooks, and you're going to want to pass that in and create the sliding piece table. I did this on loop as well. On loop. I did this on stream as well. I think it was like the first to the second or the third episode. So yeah, you're going to want to loop through, okay, and with blockers, okay? And how you're going to do the blockers is, I kind of forget how this works. I think that are you, oh, blockers equals, right. So you are basically just populating the blockers more and more and more and more and more until you get to 0, and then you break out. So yeah, I recommend you just do the exact same pattern here. I can't remember how I figured this out, but I remember having some mental trouble when it came to this in the first place. But you're basically you're generating all of the possible blockers for every possible square, right? You're looping through all of the possible squares your bishop or rook could be on, and then you are looping through all of the possible blocker combinations for that square, and then you're just generating the moves for that blocker combination, and then you're just putting the moves at that table, right? And so that's what this looks like. It's literally just stepping in each direction until you hit the border, okay, or hit something with the blocker at it, right? If this and blockers break, so hopefully that's pretty self-explanatory. Once again, you can check the code yourself, but yeah, so that's how you do the table, right? And to go back to where we index it, that's the table that we're indexing here. We are just doing the opposite of it. We find the hash index with the blockers, go into the table. And so that's the table that we did on initialization. And that's the first thing that you are going to want to have in your initialization routine is that very code. Okay, why am I all the way over here? Okay, so that's that. And now you get that board, and that goes into our moves, right? And then our captures are just going to be moves and the enemy pieces. And we're just going to go through our captures first, because then we can early out if we're doing our quiescent stuff. Then we're going to remove enemy pieces from our moves, and then we're going to push the moves. Something you may notice here is that I encode both captures and moves as the same thing. Why is that? Well, I follow the stockfish way of doing things. I didn't always, but I wanted to get my moves into 16-bit integers. I saw other people do it with 32, and I was like, if I can do it with 16, then I want to do 16. So the secret here is that the only case where a capture exists is when there's a piece on the square that we're going to, okay? The only other case, it would be en passant, okay? And we have that encoded already. So we do not need to encode captures. We can simply infer that. However, there may be bugs you create, because now you're just basically saying, hey, just take a piece off that square, man. So, but that is what happens. Now, how do you do other things? How do you deal with castling? How do you deal with all of this? You can go through my streams when I did this the first time. I had a lot more logic here. The move generation was a lot more complicated. I'm happy with it right now. I think I'm at like 25 million nodes per second perfed. I think it's come a long way, but I recommend that you just do the castling logic the complicated way and not the simple bitmask way, actually, just because we're going to get into polyglot later, but it does take a while to think about it, you know. A few edge cases you may not be aware of, right? That you may run into while doing your perf tests. If there's a rook, if your rooks are at starting position, okay, and you still have your castling rights, you may think to yourself, well, we're not going to lose our rights unless we move our king or move our rooks. That's how it works. Well, what if your rook gets taken? These are important edge cases, okay, that you need to consider beforehand before you start, going crazy. That's an important edge case. That one really gets you. So there are a few things like that are important to take into consideration. Of course, you want to. That's going to be during your make and undo move, but I'm simply just giving a brief on that. So anyway, all of the pieces in my engine right now just are exactly the same. Okay, all the sliders are exactly the same. Our kings and our knights are very simple. Okay, you just want to compute a bit mask for every piece on the board. Okay, so for your kings, I just have king moves is what I call it. It's just an array of 64 integers that are just the king moves from every square on the board, just around the king. You can do that very simply, okay, just with math. I highly recommend, especially if you're a beginner programmer, to do that yourself, because I think it's like a really cool, easy exercise to do, is just to, just loop around the king and toggle the bits yourself. So that's what you're going to index to, right? You're going to index your from, which is where the king is at currently, and then that is automatically going to have the moves around it. Same thing for the knight. Okay, knights have the same thing. They just move. They can't be blocked, right? And yeah, so this is what the generate moves looks like. I call a different function during my quiescence called generate non-quiet moves, but it's basically the same thing. It just doesn't do the castling stuff. Basically what this is doing, right, with the castling stuff, I have logic here, right, that generates if a castle is legal, right? Stockfish and some other engines do this. Actually, they generate castling moves just without checking for occupational legality or anything like this, and then they do it later. Now, why do engines do it that way? Like, it just doesn't make sense, right? Because you're just postponing it, and you get, you might get bugs and things like this. Well, it's because in a chess engine, you aren't going to be playing all the moves, right? And so if we do all of this additional logic, leading up before we even play the moves, right, with generating the moves, we're wasting time, okay? And so that's why they do it this way, right? Because this move might just get discarded anyway. So that's why they do it that way. I don't really recommend doing it that way at the beginning, because you have to build the house before you build the castle. Anyway, so that's what this is doing. If we are castling queenside, if we do have the flag for castling queenside, right, our side we switch here to say if we're white or black, and so that's what this is. Okay, so we're checking the castle occupation masks, okay, for side and queenside. And basically what this is it's literally just a bit mask that is all the squares between our king and the rook, okay, We are simply just checking, is there a piece there? If there isn't a piece there, then we can early out of this right away. Then if there isn't a piece there, we might actually be able to castle. And so I have this generate attack mask. I literally just look at the enemy pieces, right? And I generate an attack mask for their pieces to see if any of the squares are being attacked. And then if they are, if this and the castle mask equals 0, then we create the castling move. Okay, so to explain what this does and what the castle masks look like, I probably honestly have to show you by hand, and so that's what I'm going to do. I'm going to show you by hand what these are, and I will go to I have been using Qt browser lately because I don't like this is going to be annoying though. This is admittedly going to be annoying. Okay, well, this might be a problem. I don't really know. So this this website is amazing. However, it does require you to press the X to stop loading it. So that's why we're going to use Firefox. I do love Qt browser though, but I don't know. There is definitely a key binding to do that, but I don't know it. So I would look it up if I wasn't here, but you have to press the X. Okay, I don't know why this website has been doing this recently, but anyway. So to get back to what I was saying. Okay, so this website is amazing. I'm going to put it in the description. This is how you can visualize all your bitboards, generate your masks if you don't want to pre-compute them, for simple stuff. So this is the layout I use, which is 0 is the black rook starting position, and 63 is the white rook starting position. Okay, these are going to be white, these are going to be black. You can do it any manner, right? I like this way because it just so happens that pushing over by the indices just kind of works, in terms of this, because if you push over by 8, you're literally going here, right? And you start here and you go there. So this just works fantastic. So you're going to click layout 3. If you go with the other layouts, basically what the castling occupation thing is we are toggling these things, right? So let's say it's white kingside, right? These are going to be the occupation squares, and this would be what I call the castle masks. If any of these squares are attacked, including the king, then he cannot castle, right? If these are occupied, then you cannot castle. These are the legality checks, right? Is the king cannot be in check, obviously, to castle. So that's the two different masks that I have. Okay, right? And then this mask is also, it includes this side as well, right? Right, and all that. So there's a lot of cool things that you can do here. You can also just like straight up do this, right? Let's say you want file masks for each file. You can just like literally do this and then copy them in. That's exactly what I did for my engine. It's just simpler to do it that way sometimes. But yeah, highly recommend that. You can also do stuff here with, I think that you can do like, this is pretty cool, right? And this also probably like teaches you a bit of those bit operations if you don't know them, right? So yeah, that's cool. Anyway, going back to what I was saying. So that's all the logic for this. I think that's the entirety of move generation that I've talked about and brought you through. I think that's about it. Also, this can just get deleted. I've got a lot of junk at different parts of the engine that aren't in use that I leave around, just leave standing around and forget to delete. Okay, so I'm going to take a breather here for a sec, and then get into Perft. Okay, I can talk briefly about what Perft is and what at this stage of your engine you should be looking to do. Perft is going to make sure that all of your moves are legal. Okay, you're not going to pass Perft the first time. It sucks, but it's actually like one of the funnest parts about making a chess engine is doing all the Perf stuff and kind of banging your head against the wall and figuring your way through it. I have the streams where I did Perft. For a few streams, it was just like 7 hours of me like walking through the search tree with Stockfish and trying to figure out where I was off. That's a part of it, and I'll show you how to do this now, actually, because I think that this is instructive. With my first chess engine, I definitely did not do it the efficient way. I spent a lot of time doing dumb things. Anyway, so what is Perft? How do I get to it? Okay, so this is my Perft routine. It didn't always look like this, but yeah. So Perft, I recommend you read 2 pages on the Chess Programming Wiki, the Perft page and the Perft results page. Those are your handbook. Okay, those are 2, probably like the top 10 most visited sites for me in my lifetime is probably Perft results. That page. The fens on that page are just fens that you should use for various debugging purposes, especially the QE Pete fen. I just go there all the time to sometimes throw a fen in and see, rather than just going from start position. Anyway, Perf results, great web page on the Chess Programming Wiki, and so you're gonna want to add onto your parsing loop Perft. Okay, I have it as just right here. I have Perft here, okay, and I have it just take in a integer with how deep it's going to go. Okay, this is standard. Okay, takes in an integer of how deep. Okay, so what is Perft? Perft, I don't know what it stands for, but Perft is a recursive routine that searches all of the possible nodes. Okay, how does it check for legality? Well, we're going to look at that in a sec. This is also going to include all of our make and undo move. Okay, so make and undo is going to be important for this. You're basically going to make moves all the way down the tree and then stop at a depth. For now, depth is just going to be plies. Okay, plies are how many moves ahead. Depth is how many moves ahead right now. So if we're going to depth 5, that means we're playing 5 moves ahead. Now, how many nodes is this? Okay, good question. Let's go start up my engine and then go perf 5. Okay, well, okay, let's delete what I did earlier, and then I forgot where it was. Okay. Maybe it was that, and then I just didn't compile it again. That's what it was. Okay, so I'm just going to run perf, and then you can see what it is. Let's go perf 5. It is going to be slower because I am recording. Okay, so there you go. Perf 6 is going to be significantly slower. Okay, so that's our perf 5, that's our perf 6. Okay, so what do all these numbers mean? This means that when we played A2, A3, there were 181,000 nodes that were underneath that move, right? And for all of these moves. And then summed up, they come out to 4,865,000, etc. And then for depth 6, it's obviously going to be a much larger number of 119 million, okay? So these numbers get exponentially larger, right? This is kind of why a chess engine is kind of impressive is the raw amount of positions, right? 119 million, by the way. Those are 119 million unique, position, or well, not unique, but different positions that we entered into. It's kind of incredible, especially when you see, what we're going to be doing. Anyway, so that's basically going to be the result, and those are the proper correct numbers from starting position. You're going to want 11 and 19 million, exactly this. It's kind of funny, I've done this so many times that I know the numbers by heart. But yeah, just like I look at them and like, yeah. Anyway, so obviously we talked about generate moves. We talked about this. So you're basically going to make an empty move list, an empty move count. You're going to call generate moves and generate all your moves. And you're going to want to look at that value. I think I have it in my engine as generates. I haven't used this in forever, but yeah. So this will just give you all of the moves listed out. So all that is good and all that is dandy. This stuff with the search stack and the state info, you don't have to worry about. You don't have to worry about this yet. We'll talk about this in depth later. So now we get into the move list, and this is a loop. We're going to loop through all the move count, and we are going to start making our moves. This is the root. The root is separate because the root is the one that prints out the nodes and all of the nodes underneath the node, and at the end it's going to print this out. So you're going to want to have a root, and then that one's going to call this one, and then this one's going to call itself recursively. Okay, so how do we make our move? This is, going to vary from engine to engine and from your convention to whatever. This is my make move. It was a lot different in the beginning. Okay, now it uses a state and it uses a stack. It pushes onto the stack the move piece, the move, and the captured piece for use later in things like continuation history and inside of the undo. What I recommend for starting out is you simply take in an argument called an undo. Okay, and inside of that undo, you store which piece you moved, the captured piece. Okay, I think pretty much that's it. Okay. This is like a very simple thing to do. You just take in a pointer to that struct, and then when you undo the move, you just pass that in. Okay, this is a very simple way to go about it. The way I recommend going about it. Doing the stack and the state info, honestly, implementing that was like the hardest thing. So I don't recommend it. The state and the stack is like, the state is like a linked list sort of thing, and the stack is basically a stack indexed by ply of all the information at that ply. You can do what the state info is doing and what the search stack is doing without implementing them completely, just passing around variables. It's way more intuitive. Okay, so what do I do here? I get my from and my to. Okay, these are just the squares that we come from and we go to. Okay, you're probably just going to have this on your move struct as integers. We get the type of the move. Okay, what these functions do is they simply decode it by getting the bits, right? You can think of like packing something into an integer as basically you have sections of that integer that we need to read from. Okay, so all the to is doing is it's looking through the bits that we have set for the range, right? And I think that it's bit 7 through, I think from is the first 6 bits, maybe. I'd have to look at it again, but yeah. Anyway, so that's all of that. All of this is just, all I do is I cache into pointers all of the stuff that we are going to be mutating to be faster. I'm not 100% sure if it is, to be honest. But I have done all of these things and I've gotten to a point where Perf says that it's pretty fast. Okay. So anyway, what am I doing here with the en passant index? Okay, so what I'm doing here is I'm seeing if okay, so this is complicated to explain. We kind of have to talk about the polyglot format now, I think, before we get into it. It's optional if you want to implement a polyglot format. I highly recommend it. It's going to be what makes you able to use your an opening book with your engine. It's also just a really convenient format to follow for your transposition table. You don't need to implement this right away in your make and undo move. In fact, I should probably just like leave this until after and just talk about your hash key, and hash key updates should be something that come directly after you do your perf. So I'm going to leave that logically until after, but remind me to come back to it. Okay, so I have a switch case for the different types. Okay, other engines like Stockfish do it differently. I might eventually move over to not switching on type and instead just like just because they all kind of share things, so there's no real reason to switch on type. It would technically be faster to do it without it, but I think it's way more intuitive to just switch on type. Okay, so first of all, we have where we're coming from and where we're going to. We're going to do what we call a XOR with our current piece. Now, if we have the bitboard viewer here, very simple. So let's say we have a pawn here. Okay, is a pawn the best way to do this? Is a pawn the best way to do this? Yeah, sure, why not? Okay, so our from and R2, I put this on the move board, right? So we are here. So we're going to go from and to. Now let's say the board is like a board of pawns and they look like this or something like this or whatever, right? What we are going to do is we are doing an exclusive OR with our from and R2. What that's going to look like is this, okay? What a XOR does, okay, is it exclusive ORs it. So that means that we are taking off, we are toggling. You can think of it as toggling on the board. So if this bit is on, it will now be off. Since this bit wasn't on and we had one here, it will be on. Okay, so that's what a XOR is. An exclusive OR means that you are toggling. Okay, so since these were and at this location, we go off. And since these were OR, then this goes off. Exclusive OR. Exclusive OR means that we aren't ORing. We are exclusively ORing. Okay, hopefully I know that I explained that kind of poorly, but that is what it will look like. So we came from here, we are going here, we are now moving there. Okay, very simple. That's also not a legal pawn move. I apologize. That's the legal pawn move. Okay. Anyway, so this piece at and this piece from. I think it's important to just start talking about this now. I have a board. I have an array of all of these enummed piece types for each square on the board. When I move a piece to a certain position, I change the piece at, right? So the piece at the to is now the piece that we moved, and the piece at the from is no piece because we moved from that position. Okay, this is important now because especially if you have a packed integer move, because you need to know if there is a piece at the location you're going to. If you just have a struct with the captured piece type, then you don't have to worry about any of that actually. So that's convenient for you. But you need this because when you determine the capture, like right here, what I'm doing here is where do I set CP? Oh, I set CP up here. Okay, so we said CP equals the game piece at 2. So our CP is like, our capture piece is the piece at wherever we're going to. right? Of course, it's going to be different for en passant, but that's how we infer that. But if you have that encoded in the move, then you don't have to worry about that. Okay, so what's PSQT? PSQT, you don't have to worry about incrementally updating PSQT yet, of course, but PSQT is p-square tables. I'm not really sure why the Q is there, actually. I think it's just p-square tables. Okay, so what is a PSQT? A PSQT is literally just an 8x8 array, well, not 8x8, but a 64 array of the entire board for a certain piece type. Okay, it just basically is scoring our squares on the board for that piece type if it's good for a pawn to be at that square. We're gonna get into how to generate your own PSQT later. That's, you know, the logistic regression stuff and all that. Okay. Wow, this video is going to be long. Okay. So just like with what we just exclusive OR'd, we're going to do the same thing with the bits 2 from the enemy piece side that we are capturing. If this is a capture, okay? Once again, my normal moves don't encode that. So in the old version of my engine, I simply had a case capture, okay? Which is likely what you'll have as well. So in my case, I determine a capture if there is a capture piece or if our move type is an en passant. An en passant will always be a capture. However, an en passant we're never going to go into here. But, you know, regardless, this Boolean gets tripped that it's a capture. So we exclusive OR the bits of the 2. We subtract from the game phase. We'll get into that later, I think. Okay, so within a chess engine, okay, we have different game phases. We have, you know, start game, we have mid game, we have end game, okay? Now, transitioning from mid to end game is done based on phase. How many pieces are on the board? Pawns don't count as phase, okay? But everything else, other than king, obviously, does decrease the phase. So when we remove a piece, we also subtract whatever phase value that piece has from the phase to say we are now getting later into the game. This is pretty much just used in evaluation. We have what is known as a tapered evaluation, which means that our scores are different for mid-game versus end-game, and we are going to interpolate between them based on the current phase value, based on how many pieces are on the board. Now, obviously, queen has the highest phase value, so if a queen gets taken off the board, you know, you get what I'm saying. But if it's a knight, it's less. So, obviously, phase 0 would be only pawns and kings. So, that's what that is. That's why we are subtracting from the phase. Okay, so we remove the PSQT, okay, for the enemy side. Okay, so what is this material score eval params thing? You may be asking here. This eval params is a loaded in array of weights that I've Texel tuned using gradient descent. Now this is going to be the end of the video where I get into this, but this EPIDX, okay, is basically just a struct that I have all of the locations for these values. So for example, the piece values of the capture piece at a certain index into that weight array. So that's what this is. Now, so this is all of this, right? We are updating the things. Actually, yeah. Okay, so this is kind of unintuitive what this is. So the blocker is both sides pieces, right? It's all of the pieces on the board. So us XORing the from instead of XORing the entire move board, this is a bit complicated to explain, but we are basically saying we are going to a position that was already occupied. So that means we don't want to toggle the bit at that position. You get what I'm saying? In the case that we do, okay, so this is no longer pawns. We're not moving a pawn because a pawn wouldn't actually, yeah, a pawn you can't move regularly. Okay, so it would be a bishop. Okay, so we have a bishop at this position. Okay, this is going to be all of the pieces on the current board. Okay, I need to, okay, so this is a bishop capturing the piece here. Okay, so our move board was this, right? Our start position and our end position was this. So if we XORed like it was previously, we would end up with this. Okay, however, because you see it's exclusive ORed, which means that if there's already a bit here, toggling it would mean that we go to 0. Okay, so basically what we're saying is if we are capturing a piece, we want to just do this, okay? Because we are moving from the start position, but we don't want to get rid of the end position because we're there. We are there now. Obviously, this only works on the blocker board for both and not for all of this. Okay. Complicated, I know. Okay, but going through more of it, this is more hash key stuff. All of this is hash key stuff. We don't have to worry about this. The remove piece is also complicated. You don't have to worry about this, I'm pretty sure. This is, this is stuff you don't want to worry about, okay? We'll talk about it later. Okay, that's other hash key stuff. Then down here is the stuff that we do for both captures and both normal moves. Okay, more hash key stuff. All of this is hash key stuff. Don't have to worry about it. Move piece also deals with piece lists, which is also complicated. I'm not going to talk about it right now. Okay, en passant. Very simple. Very similar to the normal move. The capture square. This is an interesting thing. Okay, so how do I explain this? The capture square, we are going, let's say we have a white pawn here, okay? The black pawn is here, okay? We are, okay, I did this wrong. I did this completely wrong. Yeah. Okay, so we have a white pawn here, and the black pawn is here. This is our en passant, okay? So the black pawn goes here, and then we en passant, okay? So we are trying to infer where the pawn was because we don't really know where the pawn is per se because we only have the en passant square. So basically what we're doing is we are taking this 2 position and we are adding 8 in the enemy's push direction to find where the pawn is. And that's what that line of code is doing. Okay, very similar here. We are doing the from and the to, right, and toggling it, right, because there is no piece at our capture square. So the capture square is actually where the enemy is. This is technically where we're going to. This is where we are capturing. Okay, so that's what it is. Okay, so we basically do the same thing, the same bit operations, just different because of that difference of the piece not being there. So of course the to becomes our piece, the from becomes the piece none, and then the capture square we also have to set to piece none. Okay, all of that is similar, and then all of that is hash key stuff. All of it is hash key stuff. So you don't have to worry about that. Also the blockers is the move board and the cap board, which we are toggling our start, end, and this additional thing so that we can get the piece off. Okay, that's what's happening there. Okay, for castle. By the way, I know I'm being very in-depth here. I am going to become less in-depth once we get into the more abstract stuff like evaluation and search and things like this. And a bit more abstract when we get into the texel tuning and all this. reason I'm being more explicit here is because this is sort of the stuff that's like a bit, you know, if you're probably watching this, you probably are, you know, a beginner, right? So that's what I'm kind of focusing on here. Okay, so very similar with the castle stuff. We have this bit mask that we create with the from and the end for the rook, and the from and the to for the king. And these rook castle locations are simply just a simply just this, right? I just have the indices for black's starting rooks. This is where they start, and then this is where they end, right? And so I index this based on, you know, start versus end, right? It starts at 0, goes to 3, and then we just put those bits on a board, and then we just do the operations with it. We use both the CB, which is the castle board, and the move board, or with our side to move pieces, and then obviously this is for the king, and then this is for the rook. So that's that. All of this is hash key stuff, which we'll get into later. Obviously you want to update this for rook and king, and then the blockers you're going to use both, since since they're both changing. Okay, so what is all this? This is promos. Okay, I get the promo type. This is probably just encoded on your move struct. So you're gonna take the promo type. You are going to, of course, I just OR it, right, the end piece onto the promo board. So let's say it's a queen. You're going to put a queen there, and you are just going to get rid of both. Okay. Very simple, very simple. If it's a capture, you do the same thing that we just did with the capture. Okay. Very simple. You're going to obviously decrement the phase too. And yeah, all of this is key stuff. Okay, so all of that is pretty, you know, pretty much the same as what I went through like 20 minutes ago. Okay, so now we get to the first thing that's a bit different. So DP, what is DP? This is double push, okay? So if double push, then we need to change some things. This is also, we're getting into polyglot format here. So I find this with a function that checks is if we're double pushing, that basically just checks if it's a pawn and we moved 16, right? So that's very simple. I don't encode it with the move because it's fairly simple to do and fairly fast. So basically it's we are setting a new en passant index, right? If a pawn double pushes, then you need the space behind it to become an en passant square. So why are we updating the hash key? Well, that's where it gets complicated. I will come back to that in a second. We're almost there. So this is the castling rights. My castling rights used to be a lot more complicated than this. Okay, this is the exact way that Stockfish does it now. You are basically just your from and your to are going to, you are basically figuring out where they are in terms of the masks, and then you are toggling it. Very simple. Why this is so convenient and kind of amazing is that you don't have to deal with the edge cases anymore of like the rook being captured, right? Because you are, as long as you know that you are going to that one location, then you know that you're toggling. Basically, and it doesn't matter which side, since side is encoded inside of the castling rights mask, bit mask flag, and that's just 8 bits, right? So you can look at the Stockfish code yourself to do that. I would have never came up with it myself, but yeah, it was super neat when I saw that, and I was like, oh my gosh, I can't keep doing this, you know. So anyway, in my engine, I put on the stack the current move, the move piece, and the capture piece. The capture piece is down here because if it's an en passant, right, or if it's, it might be changed, right? En passant, we don't have the capture piece yet, but yeah. So that's why I have it down here. I put it on the stack. You'll put it on the undo struct if you choose to do that. We are going to use this information when we undo the move. Okay. So down here, I do the 50 move clock. If you don't know what that is, it's not important yet. So yeah. Okay. Now we can go to the undo. The undo sits above my make move. So the undo should be much simpler than your make move. For me though, when I started my engine, I didn't have state info or anything to remove things, and so all of it I did. I had to redo everything in your undo move. You will probably do that same thing, and so it's probably going to you're going to have a lot of hash key stuff as well here. You're going to have like a lot of keys as well. The alternative is to do your state info, and now what I do is a linked list, and so basically all of that stuff is mem copied onto it, right? So all of our keys and all of that at the start of make move, and so when we undo a move, we simply just set our current state to the one that was previous, right? And simply drop that state. That basically it's pointer stuff, right? So you basically have a chain going all the way back. I can show off later what that is more in depth, but you basically have a chain going all the way back. I put it all the way back to when we enter into our UCI position moves, when we're getting moves from UCI, and I have basically a state chain. So the PST is the previous state. It links us all the way back to that. That's how I check for like threefold repetition and stuff now. And it also ensures that whenever we make a move, we can undo it without actually having to change any keys. We just revert to the state previous. You can do something similar without having to do the whole fancy linked list thing by just restoring things from your undo struct. You can probably just actually mem copy keys onto your undo struct and just simply restore it. I didn't do that at the beginning, and it definitely slowed the engine down. Okay, what are hash keys? I haven't even talked about it yet. But okay, so basically this is just doing the opposite of what we did. So we're going to be ORing the pieces back instead of XORing in these situations. So for example, the captured piece, we're going to OR that bits at the 2 position, right? And so that's what we're going to be doing there. So I do have some assertions here, just in case our game states gets messed up somehow, which it sometimes does. There are sometimes, memory corruption things that happen, and then you're like, oh, this assertion failed, but oh no, So add assertions, I get an appreciation for assertions now. I definitely have it. So, okay, so this move piece handles the game piece at 2s, right? So that's why I don't have them there. But obviously you want to add the phase values if you had captured something, right? And then you want to subtract the phase values from your pro mode piece, right? So a piece here is our promo. It's kind of unintuitive, but yeah, so our move piece is always the promo because it's easier to obviously infer that it was a pawn that promoted rather than trying to infer the promotion type again. You get what I'm saying? Okay, so that's that. That's pretty much the make and undo. Now, I don't expect you to have a bug-free make and undo right out the gate. Probably not. There's probably going to be a lot of bugs that you have to fix, but hopefully this gives you sort of an idea. You don't have to do all the PSQT stuff, all the incremental stuff. Literally just do the toggling the bits and all that. Okay. So that's that. So that's what we're doing in our perf. So we make a move. Oh, yes, I forgot to mention this. So how do we determine if a move is legal or not? I didn't talk about pseudo-legality. So we generate all pseudo-legal moves. Most engines do it this way right now. That, you know, some engines don't. I've read engines that don't. But most engines, and what I recommend, I made a legal move generator actually in my first engine, and it was so painful, and it was slow because I didn't do it right, and so I think it's probably a lot easier to just make a pseudo legal move generator before you go into legality. Pseudo-legal moves are basically all the moves that seem legal, right? So we generate all the moves, like, you know, a bishop can obviously move to this location, or, you know, but obviously a bishop can't move there if it's pinned to the king, or, you know, a king can't move there if it's attacked. We don't check that during move generation because it makes us slow. It's much faster to simply do this during when we make a move, because then we can just look at the board state and see, oh, is he in check? Is the king in check? Because we don't have to check for, you know, any of these, you know, pins, or it's pretty complicated. You'd be surprised. So basically at the end of your make move, you just have a check if the king is in check. Okay, and I just return a boolean if the move was legal or not, right? So our in check, this just literally calls is square attacked with the position of the king for the enemy side, but the enemy side in this case is just the side that's attacking. So the convention is a bit weird, but yes. So this just literally looks through all of the moves, and then just, you know, king moves index, endgame, piece of side king. Right, so you also need to check if your king has moved into the other king's moves, you know, because that's obviously illegal. So yeah, that's all of that. So yeah, you just wanna check that. You also want to make just a function that, you know, that checks if a square is attacked, because it's useful in general. So anyway, that's what happens at the end of your make move, and that's what you're seeing here with this if statement. If not make move, if it was legal, we just want to undo it and move on with our lives. However, if it was legal, we want to recurse down, right? And so we call perft down here, and we are assigning to a uint64t, but it's not a bit board, it's just a very large node number. Okay. So if our depth is 0 and we hit the bottom, we want to return 1. And that's basically, we're just counting all the way up, right? Is that we just have nodes plus equals the nodes from the child, and then we just recursively return that up. We return nodes, and so we're just accumulating them up to the parent. So that's that. That's basically it, right? And you can see I still have this undo here, even though that's what I recommend most people have. Okay, so that's basically that. You get to the bottom, you recurse all the way to the top, and if you did it successfully, then you'll get this. You'll get this, and this is, you know, this, right? And then this was, you know, like I said, when we played A2, A3, we got this many nodes underneath it. Okay, so yeah, so you're going to add all of them into nodes, and then, you know, you can have this fancy nodes per second thing down there, but yeah. Okay, so that's that. I want to walk you through how to debug your perft, because I don't think anybody has ever really talked about how to do that, other than, you know, random posts on the internet. So I want to talk about how to debug it. Trying to figure out if I should break something on purpose to show it off, or kind of scared to do so, but I can try. Man, I'm gonna break something real. Let's just break something in promo. Okay, so let's just get rid of this line of code. Okay, and let's just compile this and then see what happens, because it may or not be seg faulting. What I'm going to be doing is I'm going to be stepping through the search tree to find where we diverge from. I think you should be able to promote in 6 moves. Oh no, are you not able to promote in 6 moves? Oh my gosh. Okay, maybe you can't promote in 6 moves, and that was a bad idea. I know that you can en passant in 6 moves, so we should really just be doing that. Like, what if we just leave that to that? I am awfully sorry that it does take a while to compile. It is just because I have so many things inlined that the compiler really just gets mad about it. I do recommend, since this is a chess engine and operations need to be fast, to inline a lot of stuff. Okay. Apparently it's really hard to break my engine, is what I'm kind of realizing here. We should actually just like be straight up doing something like that. I mean, that might break it too bad though. I might cut this out of the video. I know that this video is super long, but I hope that it will be helpful. I'm going to leave a lot of chapters in to... This has to break it. This has to break it. There's no way that this... Okay, there we go. We got the incorrect number. Okay, I'm going to put that back in just so that I don't forget. Okay, so what now? What now? Well... Okay, so I'm going to pull up... Stockfish. Okay, so there we go. I'm glad that I remembered that. So we are going from start position. I think the name is position start pause. I think that that's it. And then you're going to go perf 6. Okay, there we go. So obviously it gets the number that we just had, right? So what does this mean? This means that they have the right number and we have the wrong number, okay? Now, we are going to go through all of these numbers and find where we diverge, right? And so, yes, it is kind of painful, okay? This is painful. So you have to look through, and we are lucky that the moves are in the same order. Yours might not be. So you have to go through and find where these diverge side by side, okay? It may help you. It did help me. In my first chess engine, I made a script where I would copy and paste both of these, and it would tell me where you were off by. So you may want to do that. That is also a good utility to make. So it looks like B2, B4 is off. Okay, we have 529, 3590, and they have 529, 3555. Okay, so what do we do now? Well, you have to make a command that makes a move, right? So you have to move B2, B4. I haven't tested this out in a long time, to be honest. I haven't, this is old stuff. So I think I have display. Okay, so we played B2, B4. So I have a command that also just displays the board and gives us the fen. So I don't remember what the command is in Stockfish. I think you just have to go position start pause moves B2 B4 and go perf 5. Right, we're going one less move every time because we're going through the search tree. And so I'm just going to go in my engine perf 5. Okay, and we can see, yep, this was the exact numbers up here, right? But we're off by the exact amount, right? And so you're just going to go down the tree. You see A7, A6, I'm off by exactly 1. Perfect. So we can just go down, you know, we go, you know, position A7, A6, and then do that here. And then perf 4. Right, and you see we are 1 move off, and then we are going to keep going down the list, right? Now you see the problems that our things aren't in the same order. If you want to see, I did do this on stream very painfully a few months ago. So hopefully that gives you an idea of how to debug this stuff, because I didn't really know when I did my first, you know, I was poking around in the dark. So yeah. Anyway, that will, once you get down all the way to down the tree, and you'll see exactly which move is off, right? So that will give you much more information to see, oh, why is this 1 pawn moved to here? Why is this capture not correct, you know? And then that'll key you into the exact code you need to look at to debug that. Okay, so I think that that's all of the perf stuff out of the way. I think. If I do miss anything or like skip over anything, just like yell at me, right, about it. I think that that's pretty much all of it. All the make, move, the perf. Yeah, so what next? So I think next, what I did with this engine was I did my hash key stuff because I knew that I had to. You might not want to do it in that order. You might just want to like start implementing your search and like a bare bones evaluation before you make a transposition table. I'm going to walk you through the keys though, because I think that it's very important for everything that's going to come after. I think it's very important. So anyway, to do this, we have to actually look up the polyglot format on here. Should give us it. Okay, so this is the exact website. I'm gonna have this in the description. This is going to be your website for implementing this. This is the exact website. If you go and look at the Blue Fever software video that he references when he's making it, this is the website, right? You don't have to use polyglot format. You can simply make a hash key that has all of these features inside of it. It will probably be even easier to implement. However, you do miss out on what the polyglot format gives you, which is access to opening books and having them inside of your hash table and being able to play those moves automatically, which I think is super helpful. And so if you want to implement this, what you're going to have to do is you will have to follow these things. First things first, copy these numbers. These are your randoms, okay? We call them randoms in hashes because they are random numbers for each specific feature that we XOR our uint64t with, so that we can get a new hash for the table. How am I going to explain this in like a way that that makes you understand what a hash key is? So let's say we start from 0, okay? We have nothing on the board, okay? And then we put a pawn at e4 on the board, okay? What my engine does, what your engine should do, right, is it goes to a white pawn and then goes to the square at e4, and then it XORs it with that random, okay? That to the hash key is basically saying there is a piece of that position, right? And now let's say that piece gets captured. we need to XOR it again to get rid of it. Okay, that's put very simply what a hash key is and what we're doing. We are doing this because of us needing a transposition table. Basically, us saying, hey, this position has been reached before, and we found this out about it. This is absolutely necessary for a chess engine. It does not run without it. Well, it does, but very slow. I'm also sorry because this is so bright and now my glasses and anyway. So these are, I think there's 781 numbers. This is exactly, if you remember, the exact stuff that I have in here. The exact numbers. This is just how you do it. So you don't have to know all the stuff about a polyglot book yet. It's just going to give you that information. What you're mainly looking at is all this stuff. Okay. So the array of 781 is split up into 4 different sections. The first one is for the pieces, what we just talked about with the white pawn and e4. Then you have castle flags. Then you have en passant, and then you have the turn. The turn is very simple. The turn is literally just whenever you do a turn, just you flip the flag. Okay. It's not simple. It's not if it was white to move. It's not if it was black to move. It's every time. Okay. Okay. So, actually, yes, it is if it's white to move, but you will be XORing it every time. So this is the way that this is complicated because I messed up the first time I did this. Okay. If it is white to move, then you XOR white. However, this means that if you're making an undoing move, you're always going to XOR it because it's always going to be either white's turn or not white's turn. Do you get what I'm saying? So if it was white's turn and now it's black's turn, you need to XOR it because you're removing white's turn. But then it's going to become white's turn and you need to XOR it again. So, but it's important to realize that because if you're creating a key from scratch and it's black's turn, then you don't XOR it. Get what I'm saying? Basically, during your fen, when you're setting your board to a fen, you're going to want to create a key from scratch. So that's what I'm trying to talk about now with the turn. Okay, so piece. So how do we do a piece? You're gonna want a way to translate their enum to whatever convention you're following. I don't imagine that you're going to have black or white encoded in with the piece types. It's not normal to do so. I know Stockfish does, kind of, but for me, I just literally do some math to figure out how to map it to their indexing. And the row and file are pretty self-explanatory. So the math here is 64 times this kind of piece plus 8 times the row plus the file. Okay, so how I do this, okay, in my engine is get piece random is the function that does this. Okay, so it's exactly the math that you just saw. It's 64 times the piece type times this square to rank plus the file. This square to rank and square to file is literally just an array, a pre-computed array with those variables. You can think of it as literally 0 to 7, right? Going across the board. So we have an index and we know that it's that file. I don't have to do any math with it, any modulus, nothing. It just is an index into the array. Highly recommend you do that as well. It will speed up your engine a lot. Anyway, so that's exactly how we index into the array. Same thing here. They have their offset, right? Their castling offset. Yeah, so this offset, I just have this as a variable, and then we add the bit, which is just which castling. My convention is exactly matching theirs in terms of numbers. I highly recommend you have the enum the same exact way. Okay. En passant is the part. En passant is the part that really killed my last engine. I mean, To explain just how painful it was, I can't really put it into words. Okay, en passant. Why is en passant weird in polyglot? En passant square isn't like the fen notation in polyglot. In fen notation, when you double push upon, you are automatically setting the space behind it as the en passant square. Okay, this is just just so simple, and it's like a beautiful way of doing it. It's just fantastic. Polyglot just takes a huge dump all over that. I mean, I don't know what they were thinking. I mean, okay, listen, they probably have a good reason for it. Okay, but it's incredibly, Okay, so why is it different? Polyglot only sets an en passant square when there is a pawn that could en passant it on the next turn. Why is that annoying? Well, because we have to figure out if there's a pawn there when we make the move, okay? And when we're unmaking a move, if it could have en passanted. Do you get why that's a bit frustrating? Okay, so this is why, okay, having a state that a linked list that you can just revert the key back is super convenient, because what I used to have was literally checks to make sure that this board state was I did have to Zor it again. Okay, it's really nice to not have to do that, I can tell you. Okay, so that's what this is. Okay, so if the en passant index was an en passant index, right? Okay, so this is complicated to explain, right? So if there was an en passant index, okay, then we need to check if we had a board state that had the flag tripped. So what we do is we go from the en passant index, look at the pawn captures coming backwards. I should be doing this on this, okay? So let's say, once again, we have a pawn here and the black pawn is here, okay? So we have en passanted. But oh no, we didn't en passant. We moved something else, okay? However, we're saying, okay, so we have the en passant index here. We have it still here. We haven't gotten rid of it yet. We have to find if we could have en passanted, but we didn't. So then what we do is we go from here and we use pawn captures, our pawn captures mask, which is just these two squares, and we find, is there a piece here? If there is a piece here, right, then we flip the flag, okay? So this is the key thing about the polyglot format that is very confusing, is that this flag needs to get tripped if there was a pawn here. Doesn't matter if you did an en passant it, doesn't matter. Now the tricky thing about this, okay, is that when you set this up, when you're double pushing a pawn, you need to do the same check, okay? So when you double push a pawn, you need to not flip the flag unless there's a pawn here. Okay, so you need to do the same check. You need to come from this square that you just set as the en passant index, and you need to look for this pawn, and you need to flip the flag. And then when it's their turn, they're going to do the exact same check. They're going to check from this en passant index, was there a piece here? Was there a pawn here? Okay, I'm sorry, I'm like drilling that in, but like, it's not, at least for me, it was not intuitive at all. Right, because you're coming from the understanding of like, once you push a pawn two squares, that's the en passant index. But polyglot format does not see it that way, and they even say it here. They say, note that this is different from the FEN standard. In the FEN standard, the present of an en passant target square after a double pawn push is unconditional. I don't know. I don't know why they do it that way. Anyway, there is a website that you will find useful. I do not have it on hand now. I should have gotten it. That's my fault. it is somebody's website that they made where you can put in a FEN and then get the correct polyglot key for that FEN. I highly recommend using that website to validate your keys before moving on to the next steps. Okay, it's very important. I will put it in the description of this video. Absolutely, that website is important. What is even more important than that is a check hash function. Okay, and that's what I'll get into next. How do you validate that your keys are correct? How do you know if you don't break things in the future? Well, you're going to want a create hash from scratch function. Mine is going to be look different because of the state stuff. However, the idea is going to be the same. You're just going to take in the board state, create the key from scratch. This is what you need to get, correct first before everything else. You need to take in their fens from this page. Just go through every single one of their fens and check their hashes against your hashes. You're gonna have this function, put in the fen, try and get a position out, and as long as you're matching on all of these, then that you're in good shape, right? And so you're just gonna go through the entirety of the position and just flip the flags, right? So here I'm just flipping them per piece. I do the castling. Mine may look different. This is how I used to do it, right? Based on the Boolean flags. The en passant thing, obviously, you're going to check if there is a pawn and at that could en passant it, then we flip the flag. And then if our color is white, then we want to flip the side to move flag. And then you just compose the key like this, exactly like they say up here. Boom. So you're going to get a hash key out of that, and then that's going to be what you use. However, you don't want to be creating a new key from scratch for every position. This is just going to be the one that you get either just for debug purposes or for when you set up your position. You're only going to want to update the key when you make a move, right? Because doing all of this per move would be very, very slow. Okay, so all of that's out of the way. So yeah, so you get this when this function that I'm in right now is set board to fen. Okay, so what this is doing is you are setting the board to a fen, and so you need to create a new key, and this goes into my original state, but you can just put this on the struct, right? Okay. I also have a function called check hash, which computes a new key from scratch and checks it against the current key. And then I had it just print out a bunch of debug information and then exit out of the program. Just literally call exit and then just look at the debug information and try and infer where you went wrong. You're going to want that when you're debugging this after every time you make a move, because you need to find the exact move where you messed up. Usually it's going to be a promotion thing or an en passant thing that you need to work out. So yeah, so that's all of that. And you can go back and you can see, I'm going to leave the code. You can go back through mine and go and check out, oh, he's flipping the keys here. He's flipping the keys here. That gets me into what I'm talking about next, which is what are all these other hash keys that I have here? What significance do they have? I'm not going to go in depth right now about it. Probably once we get to like the end of search. All of these other hash keys are core hist hash keys. You can find them in other engines as well, non-pawns and for specific pieces, as well as the material key. Basically, all you need to know is they're basically updated the exact same as our position hash key. They're just used, when a piece isn't a pawn, then we do it, when a piece is a certain piece, we do it. Basically, they are used for correction history. Now, what is correction history? I'll give a brief primer on it now. A correction history is basically when we reach a certain position with certain features, how off were we? How do we find how off we were? Well, we get a score back, right? And we are checking how off we were from that score based on what our static evaluation was beforehand, right? So this typically happens, when, it happens, I believe it happens when we raise alpha, or we're in a beta cutoff, or within a certain range. I'll have to check what range exactly it is, but it's basically if a score is below beta. I don't know. I have to check. But that's the concept, right? Is you have your score, your best score, right, during search, and you're basically just subtracting your evaluation before you enter the move loop, right? The static evaluation of the position, and you're basically seeing how off am I. Why is this important? Because it basically figures out biases inside of your own evaluation, right? Let's say in a certain position with a certain configuration of non-pawn pieces, you're off by a certain amount. Well, QSearch learns that and then applies that to your evaluation. You simply add it onto your evaluation, actually, and it basically balances out your evaluation. It's very, very fascinating, and it helps out a lot. I'm going to take a breather, I think, like a brief break. I think I've been going for like two hours now, just over, and I will come back and start talking about search, and then we will move to eval, and then I will talk about logistic regression after that. Okay, be back in a little bit. Hello, everyone. It's I tried to come back yesterday after dinner, and I just rambled a bunch because I simply lost the, I got out of the zone, and so I need to come back today and re-talk about this stuff. Where we left off, I believe, was we were done with Perft and make an undo move, and I was at the point of getting into search and what search does. But I realized yesterday I started talking about search without talking about move ordering. And so move ordering is kind of the foundation of everything that we're going to be talking about next. It's very important, and it is honestly more important than a good search to have move ordering, because without move ordering you don't have a good search at all. You will never. Everything relies on good move ordering, and surprisingly it's easy if you do it the right way the first time. I didn't, and so I'm going to try and teach how to do things the right way the first time instead of doing all this other stuff. Most engines do move ordering in really the same way, which is we have a move picker. But before I get into this, I also wanted to talk about some things that I glossed over. At the beginning of this, Sisyphean task of this video was I wanted to make it accessible for everybody. And so, I talked about some things like bitwise operators and all this stuff that you may or may not know about if you know a programming language. But I simply glossed over types, and I glossed over pointers, and I glossed over memory allocation, and I glossed over how you should implement these things in your program. And so I'm probably going to just add a redirection to this point, maybe put it at the beginning of the video, because I'm bad at doing things like this sometimes, where I will gloss over certain things that are just second nature to me but may not be for other people, and so I wanted to talk, just give some examples from the code about what how these things operate. Okay, now in my engine, nothing is actually allocated with malloc or anything. that's kind of the great thing about an engine, is that you're working with tightly packed data, okay? And so you don't have to actually deal with the overhead of pointer indirection all the time, you know? Now what does any of that mean? You can feel free to skip this if none of this applies to you. But a pointer is just exactly what it sounds like. It is an address in memory, okay, that you're going to, okay. However, it is a assembly instruction to follow a pointer. MOV, I think. I don't really know assembly, but so avoiding taking pointers is important, okay, especially when you're working on a program like this. A chess engine needs to be micro optimized, okay, because it's doing, a billion operations a second. I would argue that a chess engine does more operations in a second, in terms of like going through the raw code rather than maybe calling drivers or other things, like doing pure operations. A chess engine has to be like up there with doing many operations a second. And so it's very important that you avoid pointers. However, you may say here, well, you don't avoid pointers, Dustmite, because right here I see, so this arrow in C is a pointer. Okay, we are following to the flags, the member of the flags, the max time, okay, and then using it. So why not just pass this then? And it's because I need to send some data back, right? So flags, I put inside of flags. I trip a flag if it's a mate. I trip a flag if it's a draw. I fill it with some other information and then pass it back. Now, what is this? Why are you passing it back? What does that mean? Well, I'm not passing anything back. I'm simply writing into the memory. But if you just simply, send into a function search flags like this, you're passing it by value, okay? Now, just, simply going over this, okay, is when you pass something by value, you're simply copying it into that function. You're copying the memory, okay? When you pass it by reference, you're passing that pointer. You're saying, here is where this data lies, okay? So when you pass something by reference, you can write into it. You can write something like flags max time equals 0, okay? And now that's within flags. However, if you pass it by value, now there's no pointers because it's not a pointer anymore. This is only going to do the local version of flags. The other version of flags that was in the callee of the function is not going to have this flags max time equals 0. So that's what a pointer is. Okay. Very simply put, the only thing I believe you should use pointers for in your program is your position. Maybe even not your position. And this is something that I've really struggled with myself in implementing things. I think that probably I should move to a point where I'm not using pointers at all. But it's very difficult because we change our bitboards and things within the program. And so we need to change the global, but it's not global anymore because of multi-threading board state, right? We need to change that. And so a lot of the times I pass in game pointer game, right? And then you follow these pointers to the PSAT board or to the board with all the pieces and stuff. And you either mutate it or you use that data somehow. Like all over my my evaluation, okay? I have things like this, okay? We are following a pointer to a pointer. Things like this. You typically want to avoid things like this as much as possible, okay? Now that's not saying go around and mem copy everything, because that's expensive as well. But what I'm trying to say is that for your hash tables and such, don't allocate them. I mean, simply put, all of my tables are stack allocated. And it's the joy of working on something like this that you can get away with that, because all of my tables are simply in 16T. Okay, and when you're working with that data that small, you don't really have to worry about a stack overflow. And so that's the joy about it, is there's no like kind of bloated structs that you're allocating, and there's none of that. So I wanted to briefly touch on that, and like every time that file comes up, the fu.txt is very funny. I was really mad when I wrote that. Anyway, so thread data. Thread data. This is per thread data that I initialize when a thread is, well, not when a thread is spawned, but I initialize all of them on the initialization of the program, because I don't really have a thread pool or anything like that. Okay, so what are all of these? These are core history. We're about to go over this, okay? But I don't allocate them. If I allocated it, if you're wondering, it would look like int16t pointer core hist whatever, right? And then what you would do is you would write into that pointer, you would call malloc on that pointer and allocate some memory to this that this pointer points to now. And then every time you use that variable, you would have to dereference a pointer to follow it to some part of memory, right? Stack and heap. You can do some research on stack and heap yourself, but basically, it's complicated. Okay, stack is ordered in order, and so referencing stuff on the stack is just faster than on the heap. So following a pointer would be to the heap. Okay. I'm sort of like realizing that I'm getting into a rabbit hole of explaining things right now, to the point where it's going to be hard to get out of once I start. And so there's kind of a level of kind of realizing that I can give you kind of an introduction into these sorts of things without sitting here all day. Anyway, all of this stuff is what we're about to talk about. We're about to talk about history. We're about to talk about corrective history. We're about to talk about continuation history. We're about to talk about what a state info, what a state stack is. And we're also about to talk about what a search stack is. All of these things are going to come together in how we order our moves and how we go through the search. Okay, and so I'm just going to navigate to sort.h, which is where I have all my move ordering stuff currently, and I want to walk you through what I think would be instructive and helpful in structuring your own move picker. You can do like a QSort, selection sort of thing. That's what I started with in this engine, because I didn't really, at that point, I wasn't really reading other people's code when to figure these things out. So, you can do that. It's completely possible to do that. What you're gonna want if you do that is simply a score move function that just scores it and will order it itself, right? That the captures are like 2 million or whatever, and then the quiets are at the bottom and are less, right? But okay, so I'm kind of getting ahead of myself. So what is move ordering? Why does it matter? Move ordering, contrary to popular belief, is not only about speed. It's about like the cleanliness of your search. Without good move ordering, a lot of noise and bad moves enter in. That's kind of the interesting thing about about chess engines, is it isn't 100% about speed. It's also about telling your program what is important. if a bunch of noise and bad moves end up going through and we end up searching these all the way to the bottom, we may find something that that makes that move good in our program's eyes. Maybe it causes some cutoff somewhere, and all of a sudden our program will think, okay, well, that move is really good. When if we just had avoided it completely, we would have never gone down that path. And so it's kind of our job to steer our chess program in the right direction and get rid of all the garbage. Of course, this does make our chess program naturally a lot faster as well, but it's important to know that some of these things aren't just about speed. They are about improving the quality of your search. And the number one way to go about that is to implement good move ordering. Okay, and so how do we implement good move ordering? Like I said, you can use sorting. You can look up selection sort, QSort. Okay, if you want to just sort the entire move array at once. Okay, if you don't know QSort, just it's a sorting algorithm that just sorts everything by with a certain compare function that you put into it. And you can do that. It uses const void pointer, and you can just compare them. Okay, so but I'm not going to really recommend that. I recommend you make a move picker, because with something like sorting, you kind of have to get it right. Okay, and everybody does it really the same way. Every strong chess engine does move. At least that I know of, does move ordering in a very similar manner. Okay, so how does my move picker work? What are the stages? What is all of this? So this function is something that I can get rid of now, but I think it's instructive to kind of show it off, okay? Because you probably won't have moves packed into integers at this point. And so this is how I was doing things to avoid copying the structs. What you're going to want to do, okay, and what was kind of annoying for me was figuring out how do I sort things without copying the move struct, because copying the move struct was expensive, right? Much more expensive than copying an integer. And so for me, I was like so annoyed that I was losing performance because of this. And so, this ordering idea, right? And so the idea is that ordering is an array of 0 to move count, right? That, the values inside of ordering are literally 0, 1, 2, 3 to move count. And what we do when we pick the next best move is we are simply moving the ordering values around. We're swapping them. What is the effect of this? Well, these indices at the start map directly into our move list, and so when we swap them, we are effectively moving that move index right here. Okay, and then the next iteration we play that move, and then at the next iteration we start at index 1. Okay, and now that one that was in index 0 is now all the way at the index that was the move that we just played, if that makes sense. Okay, so basically, instead of copying moves, we're copying integers. And now I don't need it because now I can just copy integers because integers are moves. But this is what I recommend if you don't have moves packed into integers yet. So this is the exact logic, okay? So what's happening here? All of my move scores are int 16, okay? That means I think it's negative 32,000 to positive 32,000, 32,626. I'm not really sure, something around there. That's why I start, best score at int 16 min here. Okay. So we set this C to the current index that we're at. We also, we put the current index, which goes 0, 1, 2, 3. That's the one that doesn't get mutated. It just literally moves down the line. So we put that on the move picker, right? And so we are saying C equals the current index, right? And then so we're just, we're just starting at the current index and then iterating to the move count, okay? And then our M is the ordering value. Okay, so that's very important because the indices are not the ordering values, okay? Because the ordering values are the ones that we're swapping. So the ordering values is what we are going to use to index into the move list. And so that's what that M is doing. And so that's why we use that M to index into the move list and get the move to check if it's eligible. Now, what is move is eligible? Well, move is eligible is determined by the move picker stage, okay? Most engines, Stockfish, most engines have these staged move pickers that matter. So I'm going to tell you what the stages are and what the normal way to go about move ordering is, okay? So the typical thing is good captures, and then underneath it is killers, and then underneath it is quiets, and then underneath it is bad captures. And promos are usually above killers, okay? So good captures, promos, killers, quiets, and bad captures. What is killers? Well, I'm going to get to that when we get into search, but I will briefly touch on it while we're talking about eligibility. So we are going to go... Oh, also, I forgot to mention the transposition table move, the move that we store in our transposition table. This move is the one that we get to store into our transposition table when we raise alpha or when we fail high above beta. We always store a move in the transposition table so that the next time we enter into this node, or not into this node, but enter into this same position, we have a move that was already really good to try first. And so that's going to be the move that we play first. So the first stage is pick TT move, okay? This is very standard. So that's basically what's happening here. So we have a certain stage. We are checking if any moves are eligible. And if they are, then we are picking the best one. And then once we have the best one and eligible count was more than one, then I go ahead and swap these indices, right? I get the TMP, what ordering was at that index, at the first index, what it was at the first index, because we're going to swap that. We're going to move it to that first index, okay? So we take the C, we set it to whatever the best index was, and then we move that to the best index, that TMP, okay? And so then we increase the current index, and then I return the index. I return the index and not the move, for a few reasons, for logic reasons, and also because I've been testing things out with bad caps. I want, for efficiency, bad captures, since we detect them during captures. I don't want to, because in my engine I don't encode captures into the move, and so it is a little bit, I mean, it's not very expensive, but it is a couple of instructions to determine if a move is a capture, because I have to decode move type and also check if the piece at a certain square exists. Okay, and so that's like a few instructions, but it's still something I want to get rid of doing multiple times on the same move. And so my idea was to move bad captures into a separate array. However, for whatever reason, I'm running into bugs with it, and so it's something that I'm going to continue trying to do. That's one of the things that I'm working on. Okay, so what does that mean, by the way? So we call move is eligible for on all of the moves when we have a given stage, right? And it's simply just a switch case. Everybody just does a switch case here that switches based on the stage. Okay, so when it is a TT move, you simply just check, is this move the TT move? Okay, when it's a good capture, we check if it's a capture, and then we check the SEE of a move. I was thinking, like, do I talk about SEE now, or do I talk about it at the end? Because when I recorded this first, I talked about it at the end. And I think I'll get to it now, actually, because we have multiple different pruning techniques and things that happen with SEE, and it's something that I'm going to be referencing a lot, and it is kind of foundational. So I'll get into that in a second. So promo, we just check if it's a promotion. You probably will have it encoded on the move. I do. So and then killers, right? Killers are non capture are quiet moves. Okay, quiet killer. The definition of a killer is a quiet move that caused a beta cutoff. Okay, and so you can have 2 of these per ply. Now I'm not really sure exactly why. It's just the way that it works out, where everybody just has 2 killers per ply. Apparently more is worse, and I'm not entirely sure why. It's just the number that everybody uses. And so honestly, killers are like a very historic kind of thing, where I'm not even so sure how necessary they are anymore with the history techniques that we have. But anyway, so killers usually go above quiets. And then you have your quiets. These are your non-captures, non-promotion moves. Okay. We order them and score them by history. And then we have bad captures after the quiets. Now, I just want to mention something here that's important. Your definition of a good or a bad capture is going to depend entirely on your engine. What do I mean by that? We determine our good captures by static exchange evaluation. Some engines say greater than or equal to 0 is a good capture. Okay. However, in my engine, it is a good capture is above an SEE of -60. Why is that? That's because I actually did a bunch of SPRT testing with it, and I found that -50 just seemed to be the sweet spot. And now SPSA 100% what's the word, reinforced that. It just turns out to work great, like -50 to 60 for my engine. But other people have used 0. Other people have used -100. Okay, anything in that range. I used to also, because my engine used to be less mature, you kind of have to like come up with your own techniques, because back in those times this simply didn't work. That's kind of the thing about chess engines, is that the further your chess engine gets along, the more things will start to work, right? If it's early on, okay, you may not be able to get your captures split into just 2 halves. You may have to have this transitional stage, which I had with kind of mid captures, which was like the section of like -60 to -350. While the other bad captures went to the bottom. Is this good practice? Maybe not, but it did actually give some elo, and that was possibly because of just all the other things that just weren't optimized yet. So try everything out in your own engine, but keep those ideas in mind. So what is SEE? What is static exchange evaluation? Okay, so static exchange evaluation is us looking at the spot that we are moving to on the board, right? It takes in a move. It says, okay, we are moving to a certain square on the board. Okay, so what static exchange evaluation is we are going to simply exchange all of the pieces from both sides that attack a certain square until for one side just has no pieces at all. Or if we break above the threshold, which I'll get into in a second. I thought that it would be helpful to also show my old SEE. My SEE now is the more modern threshold SEE. That is not the SEE that returns a value that you check against your margin. That's what all of this commented code is, commented out code is. What this is I was caching SEE scores in a separate array so that I didn't SEE a move twice. And that made it more efficient. But with a threshold, you can't because you don't get a value back. You only get true or false. Now, a threshold SEE is faster, but you do lose that that ability to cache scores, and so you often have to SEE a move twice sometimes, which may or may not have some overhead. Okay, so there are cons and benefits to it. Also, it is technically less accurate, but more but way faster. Okay, so I just wanted to show off what my old SEE looked like. Okay, because I think that it is perhaps good. I'm trying to see if this is the version. I think it is. Yeah, I think this is it for sure. So this is my old value-based SEE that returns an integer-based score. Okay, I kind of wanted to show off I can't compile this now, unfortunately, because I would have to clean it up. I want to get like a newer version of this, but I don't know if it exists. Okay, it does exist. It's this. Okay, so what I'm going to do, oh man, but that's kind of unfortunate. What I wanted to do was show off what this looks like, and see the output, and count the pieces themselves. Unfortunately, I would how would I do this if I want to show this off? Okay, let's do it. So I'm just going to copy and paste this into here. Into here. And I'll just name it SEE2. Okay. And so I'll just call this, and we can just like print out some things here. I want to print out a few things. I want to print the val. Okay. I should have prepared this. I'm sorry. I didn't really. I just kind of thought about this now that like yesterday I was kind of like explaining it, and it was hard to explain it, right? I want to print move full for the move. Okay. So that we can see what's happening. And I want to just print the game board. And we can infer the rest, I think, from there. And so what I'm going to do is I'm just going to put that inside of here. We are just going to call SEE2 on every move, and then like hopefully this compiles. I didn't see any errors, which was kind of concerning, because I just like kind of popped old function into the engine. Okay, so we get a few things here. So if you remember the order, I was printing out the move, the game board, and then the val. Okay, so let's go and find what is happening here. There are a lot of negative ones. Some of them are mangled because of the way I print things out. So negative 230. So let's go see what's going on here. So c3 d5. So c3 d5. It's this knight. Knight takes pawn. Okay. So this knight is taking this pawn. Okay. So this let's just go and count the values. So in chess, right, a pawn is about the value of 100 centipawns, right? So a knight captures a pawn, right? From our side, that's a positive 100. Okay, so we captured that pawn. Now we have 100. Okay, that pawn is protected though by a queen, and so that queen captures our knight. Okay, and that is why we have a negative 230 SEE, because we captured the pawn, but our knight gets captured. So we got 100, but a knight is worth 330. So 100 minus 330 is that negative 230. Okay, so that is what SEE is. And yeah, I think that that's the easiest way to explain it. Now, what happens if we could have captured the queen, right? Then we would have had like an SEE of like positive 600, right? Or something like that. And so this is what an SEE is. I know that this isn't perhaps the best, there's a negative 800 SEE, which must be a queen taking a pawn, I believe. So f6, f2. So f6, f2. Okay, so this queen takes this pawn. And of course, the king just captures back, right? And so 100 is the value of the pawn. 900 is the value of a queen. Okay, you get what I'm saying here? So this is how it works. Okay, so I hope that that cleared things up for you. And okay, so now let's actually talk about the implementation. So what is happening in the SEE? How do we do this? Okay, so the way I went about it in my old value-based SEE, it's easier to understand what's going on. Okay, so you basically are just going to subtract pieces from each direction. You can also do this with quiet moves, non-capture moves, when you move a piece to a square. This is how I determine if we are going to extend on checks. Okay, so going back to how do I implement this? So we have temporary pieces, okay, that I copy over into this array. I copy over the pieces because we need a working kind of a working mask of pieces that we are going to remove from. As we iterate pieces, we're going to remove pieces and take them off the board. Why? Because we need to know what's behind that piece. Let's say it's a queen captures, but there's a rook behind it. Okay, so we're going to take that queen off, and then there's going to be a discovered attack on that square. So how do we go about this? So I copy the pieces. The math is we start off with a value of the captured piece minus our piece. We are assuming that our piece is going to get captured. That's the assumption that everything runs on. We are always going to be one step ahead, you can think of it. We're always assuming that the piece that enters the square is going to be captured. Okay, it just kind of works out that way. And so what you're going to do at the end, what I did at the end, is once everything takes, you have to subtract the last piece because the last piece didn't get captured. See what I'm saying? Okay, so because there were no pieces left to capture. So we start with the value of the captured piece minus our piece, right? We captured it, but we're assuming that we're going to get captured. And if it's a quiet move, then you just negate your own piece because there was no capture. Okay, very simple. We compose an attacker mask for the square. Okay, I just simply, for a square, I just look at, what could attack it. Very simple. And simply move those attackers onto a bit mask for both sides. And so you're going to switch the side since it was just the side to move, and then you are going to go through their attacker mask. You're going to find the least valuable attacker, LVA, which the way I do it is I just iterate from pawns to kings in the attack mask, and then I find what is the overlap, and then I return the position of that bit, and then we simply XOR it. We pop that bit off, okay, and we add the the value onto the val, okay? And what I'm doing here with side equals original side, okay, is you want to be negating it based on the side. Now, the way Stockfish does this, right, is in a less intuitive way. They do the exact same thing. And I'm going to show that off in a second here. And so this is how I do my discovered attacks on the square, is that once we take that bit off that bit board, and then we check for the discovered attacks on the square. And then we move those pieces onto the attacker mask, since they are now attacking the square. And that's it. And then we just add them on and then switch the side again back. And then when somebody runs out of attackers, then we simply, you can see up here, val plus equals last cap. And then I break. The last capture is the last piece. We are just simply, that piece wasn't captured, so we aren't going to count it anymore. And as you can see, that's that works out perfectly, and that's how we get all the scores that I was just showing off. And those scores are what you would use, negative 250 would be a bad capture, right? And so, and it would probably be pruned by SE pruning later. We're going to get into it. So that's what SE is. That's what it looks like. Now to go through the stockfish-ish, SEE, the SEE that most strong engines use now with the threshold is, I've commented it out because, going through yesterday, I was really, not explaining things as good as I should have. So what they say in Stockfish is they early out if the move type is not a capture or a quiet move. And I believe that this is just because of just for efficiency, right? And also because promotions specifically are pretty much always going to be positive SEE well, not necessarily, but that they're interesting enough that they should pass an SEE. And they changed the material on the board, so even like statically exchanging wouldn't really make sense per se. And for en passants is something that's strange for me why they would do this, but I suppose that it's quite literally just for speed, and that en passants are so rare that that it doesn't matter. Anyway, to get into the actual logic with the thresholds, right? I wrote down here, if our val is somehow less than 0, then even if we're captured, we're still below the threshold. That's what this value is. So we add the capture piece before we even subtract our captured piece, and then we subtract the threshold. If we captured the enemy piece and we still are underneath the threshold, then we're losing, okay? Because we can assume that we're going to get captured, and if we're going to get captured, then we were already losing before we were captured, okay? This is very rare because we don't really have a threshold that ever goes positive to the point where the threshold would have to be above 100 and the capture piece would have to be a pawn, right? I don't think that there's anywhere in my engine where that's the case, but I think it's instructive to go over the implementation and talk through it logically. So then once we subtract our piece, right, and we assume we get captured once again, this is the thing about that I totally missed this. This is the reason why that first threshold is actually important, because if it's a quiet move, we aren't capturing anything. Okay, and so if it's a quiet move and we're still below the threshold, we can assume that we are going to get captured anyway, and therefore we early out. It is kind of a dangerous heuristic with a quiet move, but it does work. So anyway, going to the next one. That's mainly for quiet moves, if I understand properly. So going on to the next one, it's if our value is greater than 0 after we assume we get captured, that means that the capture is still positive for us. Does that make sense? So if we capture and then are captured back, right, this means that we don't have to capture back anyway. And so we already won the exchange, right? And so we can just end there and say that it's possible, right? And so this is not only efficient, but it also completely avoids having any of this extra noise. Because let's say our pawn captures a knight. That's a positive SEE move, obviously, right off the bat. A pawn captures a knight. A bishop captures the pawn. Let's say that bishop is defended by a knight, and that bishop is attacked by our queen now. My old SEE would say, okay, we're taking with the queen. Okay, and then the knight would have taken our queen, and then we would have a negative SEE, right? This threshold means that we would never take with the queen. We would just early out, because we don't have to take with the queen. We don't have to take with the queen. And so that is what this version is doing. And that's why this version is better. However, it's not necessary, completely right away, but I just thought that this is kind of important to say. A lot of this implementation directly matches what's in Stockfish, because honestly, I was like blown away when I saw this, and I like logically thought about it, and I was like, wow, this totally solves some issues with like blind sides in my engine, including removing the pin pieces as well. So we are removing the pin pieces, the pieces that are pinned to the king, and we also, okay, so this is really interesting. So once again, this threshold, the val is greater than or equal to 0, is very important. So this is exactly what it was up there. If our val is greater than or equal to 0, we can early out because we've already won the exchange, so or either side, right? So that's true throughout the loop, throughout us going through all the pieces. And also this is really interesting because it's basically a legality check. If the last piece that captured was a king, and there are more attackers, then we know that king is going to be in check, and that's an illegal move. And so we can simply switch the side back before we break out. Now, why are we switching side and not returning an integer? Because this value threshold idea of quitting once you've won the exchange completely gets rid of the need for a value at all, because once one returns out, then you know that side is winning. So yeah, exactly. So that's what I put here. Or it's the opposite. Yeah, it's the opposite. It's the opposite. It's when you exit out. That's why its original side doesn't equal side. It's the exact opposite of what I just said. Okay, so that was SEE. That was my explanation of SEE in the modern way of going about it, and I hope that it was I explained it so within the zone that now my coffee is cold. So okay, so I hope that was instructive, and so that's what's happening in move ordering, right? When we go and check our good captures, we're using that good capture margin, and once again, mine is about -60, right? Based on the SPSAs that I've done. By the way, when I keep mentioning SPSAs and tuning and all of this, that's going to be at the end of the video. I'm going to walk you through my SPSA tuner, my Texel tuner, and hopefully explain some of it. Honestly, it does kind of go over my head. I'm not a machine learning scientist, but I've implemented it based on other people's code, and I have some idea of what it's doing. Okay. Anyway, moving on. So we check if the move is eligible. If there is a score in the score array is simply just a parallel array to the moves. Why are they separate? Because they're also in 16Ts, and copying them would be slow. So I just have them in a separate like parallel array that we index into. Okay, and so if the score is none, then we score the move because we need to figure out, if it's better than all the other eligible moves. Okay, so this is the function that gets called score move. It used to be much larger with, bonuses for promotions and checks. This is my current score move. I don't know if I would exactly recommend this exact structure, if you're starting out, because this kind of requires a lot of prerequisites in terms of history. So there are 3 types of histories here. There is capture history, continuation history, and our regular history. Okay, so what is each of these? So first we're going to start with the non-quiet moves. Okay. To understand what capture history is doing, we have to understand MVV LVA. MVV LVA is it is most valuable victim, least valuable attacker. Okay, so this is what would basically say, right, if a pawn captures a queen, would be the most valuable. And if a queen captures a pawn, it would be the least valuable. Most valuable victim, least valuable attacker. You may think, oh, well, this might, not be a good heuristic at all because it might lead to some really bad tactical, losses. But it actually works surprisingly well, like 99% of the time. I've tried a lot of different things with ordering captures, especially early on with SEE and things like this. Never really worked. I really like the idea of just raw MVV LVA, and I highly recommend it because capture history is only a little improvement. It's really not like an insane improvement over MVV LVA. So what is capture history? What is capture history? Why why does it exist? I really like capture history, and that's why I have it in the engine, because I think it's such a neat idea. So capture history, it's very important you understand this because I didn't understand this. It only replaces LVA. It does not replace MVV, which is what we see here. The capture piece, I'm using the piece val of the capture piece. That is MVV, most valuable victim. Okay, that is that. It stays the same. You do not want to just use raw capture history. It will lose you elo. Now why? Because capture history is only saying which piece it's best for us to take with. Okay, capture history is indexed by piece, the square we are moving to, and the captured piece. So what is this measuring? This is measuring when we took on this square this piece that we went to this square and captured this piece. We did it with this piece, okay, versus this other piece, right? So basically it's saying, let's say we have a bishop attacking this pawn on this square, and then we have a knight attacking this pawn on this square. We are saying that when we capture with the knight in this particular square with this particular piece, it's better than if we capture with the bishop. That's what it's saying. That's why it's a replacement for LVA, least valuable attacker, and not MVV. Okay, because you're only measuring which piece it's best to capture with. And yeah, it works great. And I think the idea behind it is really, really cool. And so yeah, just, so that's basically what it is. And so I decode the move piece, the capture piece, the move type, all here. Okay, so that's really all we do for captures. And it may seem slim, and it is slim, and that's something that it is hard, though, to create heuristics for captures because captures are noisy. Captures are really hard to quantify if they're good or bad moves because they rely on so much context. Quiet moves have a different nature where they don't create immediate material imbalances, right? And so we can use a lot of different heuristics to order quiet moves because we can measure. It's less contextual. It's less contextual. Okay, so that's what basic. So this is now going into the quiet moves. What is history? What is regular history? Regular history is very simple. We are just simply saying when we moved from this square to this square, this was typically good. That's literally it. I'm going to go into how we update history in a little bit, but that is literally it. It is usually indexed by side because obviously it matters if, black versus white. It sometimes is also indexed by piece. Mine was. But yeah, so this is what this is. Okay, now getting into continuation history at the bottom. So what is continuation history? When I recorded this last, it was really hard for me to explain the pointer magic that is happening here. It is very confusing. Okay, so it's important to say what is continuation history. Continuation history is exactly what it sounds like. Okay, we are looking at previous moves, okay, and saying that this move was typically a good response to that move. Okay, it's kind of the child of counter move or refutation. So you are looking at these previous moves and then indexing into the table and then finding if this move was good or not. So how do we do this though? Because if you may be running the numbers in your head, that must be an insanely big table, right? Because it is my old version also encoded side as well. It encoded black and white, it encoded piece, and it encoded the square as well. Now I don't encode the side, but it works basically the same. It still is a massive table, right? Because you got to think, with 6 piece types and 64 squares, and then you start multiplying, times 6 piece types times 64 squares. It's a pretty massive table. And so how do we do it? Well, the way Stockfish does it and the way I have it here is really, really an incredible thing. But it does take, a moment to wrap your head around it. Okay, so a lot of the things that I'm going to be going over today, certain portions of my engine are directly, referential to other implementations. And that's, kind of how a search ends up once you, grow it up to a certain degree. I have a lot of ideas about my own ideas that I want to introduce and stuff, but I've learned so much from digging through the code and figuring out what all this stuff is doing. So I want to, share that with you today. So what is this pointer doing here? How does this work? Okay, so I have on my thread data all of these different histories. It's thread dependent. It didn't used to be actually, but then I saw other engines do it thread dependent. Some people do it global, and then I just I tried to do it thread dependent, and honestly I haven't really noticed some large elo increase or anything like this, but it still does make sense, especially for something like continuation history that is kind of exploring the same sort of lines down the tree, since it's coming from this one singular move. You can think of it like that. So you may see this type here that's continuation history. What is continuation history? What is this? Well, a continuation history is actually just a table. Okay, it is piece types plus 1 to board max. Okay, so it is a table inside of a table, right? So we have a type of continuation history. We have a type of continuation history that is inside of another continuation history. Does this make sense? Okay, so it is pretty confusing, but inside of this array is just those nested arrays, right? And so if you can think about it, those arrays are going to be the move that we are now indexing into. So how does this work in practice? So I'm going to show you, skip ahead in the search to where we actually set these up. After I make a move in my engine, I immediately set up the pointers based on that move into the stack. The stack is simply ply information. Okay, ply, once again, is the amount of moves we are from the root. So 1 move, 2 move, when we play move. Okay, so I have a stack, which is simply just an array indexed by ply. And within that array, I, at a certain ply, let's say that this is 5 moves ahead, I put in, okay, we are setting our pointer to a continuation history that is with the move piece and with the move 2. Okay, so we are saying that we are at this part in the table. Okay, so we set a pointer there. Now, that is exactly how it gets used later, okay, which now when we're scoring a move, say in the child node, okay, in the child node we're scoring a move. How do we reference that move? Well, we simply go into the stack, okay, and we go to the ply previous. Now, this ply minus, the stack minus the ply minus, it's simply just subtracting from a pointer, okay? When you subtract from a pointer, you are basically going 1 back. It's the same thing if we were to index it by numbers. If we were, say, at, it's kind of hard to explain. If we were at index 5 in an array, right, and we wanted to see index 4, right, we would go 5 minus 4, 5 minus 1, I mean. However, if we were past a pointer to the 5th element, or the 5th index in the stack array, and we subtracted 1, then we would still end up at 4. Because you're basically just subtracting the size, okay, so that's what we're doing here. We're simply just stepping back in ply, and then we get the stack, and then we follow the pointer to that place in that table, and then we index into that with the current move. Okay, so this is kind of confusing to understand, but we are setting a pointer to a certain place in the table, and then we are indexing into that in the child nodes. So it's kind of confusing, I know. It did kind of confuse me when I saw it, but I actually have never really seen something like that. I always end up with the kind of flattened out table where we index into it by 64 times piece types times this plus this times this, those flattened 3D arrays, and those giant, it takes a lot of instructions actually to index into them, to just index into them. You have to do a lot of multiplication and stuff. This implementation completely avoids that, and you end up just indexing it with your values. You don't have to do any of this sort of thing, and it's just such an elegant implementation that I just I was so confused when I saw it. But anyway, I hope that I explained that properly, because I think that that's super neat. And so yeah, my continuation history started off as just a massive array, and yeah. So why am I dividing it by this scale? Because I like I found the performance of my engine to increase when the later plies have less scale. You may find it otherwise, but yeah, that's what I did, and I plan on tuning these soon with SPSA as well. Okay, so that's that. Now I can actually get through and talk about the search. So that's how our sorting works. That's how sorting works, is we simply for each move we score it using those methods with history. Now, you know, what is history? History, we update when a move raises alpha or it fails high, and we penalize all of the moves that didn't, which is pretty cool. It's pretty cool. But we're going to get into that a little bit later. Okay. This video is going to be long. Today, my plan was to go over search, eval. Yeah. But so far, I haven't even talked about search. Okay. So this is the main search function. Okay. We enter into this when... Did I talk about UCI? No, I didn't. Okay, so we kind of have to talk about that first. What is UCI? I wonder if I did talk about UCI. Oh yeah, I brought up this because I wanted to talk about this old Stockfish pull request. But okay, so UCI. What is UCI? This is the UCI protocol. This is how GUIs communicate with chess engines. Not only GUIs, but also, you know, just various chess programs. This is how I communicate to my chess program when I'm tuning it. And so this is kind of required. I think that there's also like export or board. I'm not really familiar with that. But UCI, at least from what I understand, is what most people use. So how do I implement this? Well, it's just like your normal command loop that you're sending strings to your engine. To enter into UCI mode, you typically get the string UCI. Okay, and so if we go here and just enter into UCI mode, I'm going to get back ID name. Okay, yeah, also I meant to mention, I am so lazy that I refuse to rename my engine, but it isn't named Vixen anymore, unfortunately. But yes, maybe I did mention that earlier, but I'm just so lazy, but I will once I upload it, you know. Anyway, so after we do this, it you know, it says ID, just like it says here. It must identify itself with the ID command. And then we do is ready, right? It will say is ready, right? And this is what the GUI will be sending to your engine during runtime if you know are playing games with it or whatever. Okay, so now we do all this. It'll say UCI new game. It'll give it a position, and I don't really have a position ready to show it off what it would look like. We can just go once again to my favorite website, Perft results. Okay, and just get like one of these fens. Okay, so we're just gonna get this one, and we will write position fen. Okay, and it's not going to say anything because it doesn't require it to say anything. And then I'm going to say go move time with this much. And okay, so we forgot to get rid of that. I apologize about that. We do need to, if I'm going to show this off, we do have to get rid of the stuff that we were debugging with earlier. Well, not debugging, but you know, showing off earlier. Once again, it does take a while because of the inlining, etc. Okay, so we are going to position fen go move time to and it's going. It's not saying anything, but it's going. Right now I don't have info printouts enabled because I was SPSA tuning earlier, and so me setting it to a long move time like that is quite counterproductive to the purpose of this video. Okay, we're just going to do a move time of this. Well, that's sort of slightly concerning. Okay, there we go. I thought that this was a really small amount of time, but I guess I don't know how milliseconds work. Anyway, so it'll think for this amount of time, and then print out best move. Okay, that's what it requires is this syntax of best move, and then it in algebraic notation what move it chooses, and it shows b2, b4. Before f4. I can't read. Okay, so it's taking the pawn with the rook here. Okay. Yeah, I just got out of it. Okay, I gotta get back in the zone. Okay, that was funny. All right. Anyway, so that's what UCI protocol is. So to show you what my implementation is, once again, this is the state stack. Did I talk about this yet? No, I didn't talk about this yet. So this is what my UCI implementation looks like. It's the same exact input loop, basically, right? We take in the line, we tokenize it, we find, which command is it, and then we go down into a switch case and do all this stuff. This is my tuning stuff. This is how I, on a new game, this is how I reset things. And then when I get in a position, I do kind of this cursed loop to play moves that we get in. The syntax for that is that it would be position fen, and then it would give moves. It would write out moves, and then have all of these moves in algebraic notation afterwards that you have to loop through and play. Doing that isn't very complicated, okay? So you're just going to tokenize it like we already talked about. You can even do it, in order like this. It's recommended to do stirtalk R, since, nesting. I'm not really going to go too much in depth about this. But yes, once you find moves and then you move past the move and get to your first move, you're going to want to do just a while loop until the end of the string with all of the moves, just playing them. You're going to generate moves. You're going to find the move in the move list, make sure it's legal, right, and then play the move. Otherwise, you want to probably throw an error, It took me a second to get it right. They also can do start pause instead of fen, very commonly actually. When you're playing a game from start position, they will simply just send start pause every new position and then just add on to the moves, just start pause moves, this, and you're just going to play out all the moves until you get to the point, and then they're going to send you go. Go is the command for your search, and telling your engine to start thinking. Now, what are you going to do when you read go? Well, there are about 6 different possible permutations of this, right? Well, not 6 different, but really 3. But I'm just reading out 6, but really 4 are in one. So the typical one is white time, B time, W ink, B ink. Okay. Now, this means the time for white, the time for black, the increment for white, and the increment for black. Okay, increment and time in chess, if you don't know, you have time on the clock, and when you play a move, you get a certain amount of time back, and that's what the increment is. Okay, and you're going to have a certain amount of nodes sometimes, right? You will get this command nodes. That will be the maximum amount of nodes you can use. You can sometimes get move time, which is what I just used, which is just the hard move time that you're setting the engine to. So those are the different ways that you may get this command, and I just string compare in a while loop while we get in more strings from our tokenized string. Okay, so that's basically what's happening, and you're going to, infer based on that. If you're playing a game with time in increments, you're going to use that information. My formula, I used to just simply have this cursed, time left max time thing. You can definitely do this. I mean, my engine was plenty strong even with just this hard-coded thing. But I ended up going to this moves left thing, which is exactly what Stockfish does. What is the 40? Honestly, it's just always, it is always assuming that there's 50 moves left in the game, even when there isn't. So there isn't really a perfect way to go about this. Okay, I just have like kind of smudged around the values a little bit, and so yeah, this is the way I go about it, and I recommend you don't do this whole thing, especially once you get to tuning, to SPSA tuning and SPRT testing and all that. You're gonna want stable time control in terms of like, you know, it being multiplicative or dividing, or, you know, it needs to be smooth across the entire thing. It can't just be like, you know, I move with 5 seconds here and 4 seconds otherwise, or else it's going to bias certain things in your testing. So that is the basics of the UCI stuff. You can also, you know, we're going to get into set option later and things like this. So I'm not going to go talk about that right now, because this was just the precursor to talk about search. But, you know, I hope that that was helpful. It really isn't that as difficult as it sounds, you know, implementing all the UCI stuff. It really isn't that bad. Iterative search. So this is the function that gets called when we get a go command, okay? That's going to give us a move. It's the massive search. Now, I'm going to go through from start to finish here. Just, I'm going to go chronologically. Otherwise, it gets a bit messy, even though this isn't logically kind of makes sense to go through the parent function first. This is the top level parent. This spawns threads that are the root, that call the root function, that then call the child search, right? That recursively goes down, and then at the bottom it bottoms out and hits QSearch. So that's the structure of this thing. Okay. So what do I mean by threads and stuff? When a program is multi-threaded, this means it's making use of different threads on a CPU. Okay. So how do we do this? I'm not going to assume that you shouldn't multi-thread your engine in the beginning. This should be something down the line, right? When your search is kind of stable. Okay. But I'm still nonetheless going to go over how it works for me. Right now, I simply hard code the thread count, by the way. Reason why is it's just simple for me to do so. I'm not at the point where I'm like releasing a binary to my engine. I'm sharing the code, right? But I'm still actively working on things. And so when I get to that point, yes, I'll make a command. But anyway, so what's happening here? So we set up a start time. Okay. Time in my engine uses time spec. Okay. The reason why it uses time spec and not clock is because of clocks per second. Obviously doesn't work in a multi-threaded context because different threads have different clock speeds. And so you're going to have to use a different thing. And I think it will depend on your maybe operating system. I'm not really sure. I simply just found something online and then just literally copied the code for it. And it's the same timer I use for tuning. So basically, I just get the amount in seconds from start. And then, we subtract at the end, right? Okay, so that's I set up a start first and foremost at the top of the search. Okay, so some of this stuff isn't in use. Like this isn't in use. You don't have to worry about most of this stuff. It's going to create errors. This is actually in use because of aspiration, but most of this stuff just is like extra. Okay. So what do I do here with root data? A lot of the stuff that I'm going to go over is entangled with multi-threading, okay? When I'm talking about this parent level function. Down there, it's not, it's going to be all, within the threaded context, but for now, this is going to be all over the place. So root data is what all of the threads communicate with, okay? Root data is which move we currently are on. It is the parent move list, the move count, the best move score, things like this. I can bring up what it looks like, okay? So it looks like this. It is the move list, the move count, alpha, beta, the current alpha and beta for that the threads use, and some atomics that we trip, right? And the PV that we copy into. What is a principal variation? I'll get to it in a second. Okay. And search data. Search data is what I highly recommend is you to make something like search data, where search data is all of the things inside of this are just raw counts. Whenever I have a certain heuristic that prunes or have some lazy evaluation cutoff or something, I just simply increment this. And I increment it in each thread, right? Because it would be really slow to increment an atomic every time. I just increment it for each thread individually, and then I simply add them all together into the root search data. And so that's what this is, basically. Okay, so that is what's happening here. So we generate moves into the root move list, okay, for the current position. And here is... Okay, so what's happening here? This is the state stack getting copied into each thread, okay? Why is it getting copied into each thread? Because of race conditions, okay? Because of a need for speed and us copying one thing once instead of, later down the line having to do all these mutexes during runtime. You don't want to do that. Instead, just copy it once. Okay, so why copy it? Why copy it? This is brand new code, by the way. Why copy it once? Because each thread needs to walk back the state linked list to detect threefold repetition. Okay, this is not easy when the state stack is a global that is shared by all threads, because now you have race conditions and stuff. So what I do is I play out the moves and I generate a state stack as a global, and then once I enter into search, I copy it into each individual thread, and within those threads I then link them together, and that's what I'm doing here. Okay, I start at 1 and then I point PST to -1. Why? Because pointers obviously become garbage when you memcopy them to when you memcopy the entire thing. So that's what that's doing. Now, it's okay if you don't 100% understand what I'm talking about here, because this is honestly like, but it was my solution to come up with this and to stop these bugs from happening. It was, causing blunders, like really bad blunders, because it was walking back and finding repetitions where there weren't repetitions, and things like this. And it was basically like up like the value of a queen, and then it would just blunder the queen or something like this. But yes, so this is why this piece of code is here. I'm sorry if that's complicated. It is kind of complicated, but okay. So this is opening book. Okay, I need to make a command for this, but if you implement an opening book, it will look similar to this. You just index, you try and find a transposition table entry for your current key, and you that key is then points to a move that you have stored there. I have on initialization, I fill the transposition table with an opening book based on the keys. I can go over that. I can definitely go over that. But I may not do that right now because it's kind of like maybe I'll do that like at the end of the video or something like this. Basically that's going to be the same like polyglot logic that I talked about earlier. You just are going to have to read the binary and decode those values yourself, and then translate the moves into transposition table entries. I just mark them as opening book, and then if TT entry is opening book, and then I just simply play the moves. It's very simple. I don't really do the whole weights thing. You definitely can do that, but you would have to store multiple moves per, TT entry. Very possible. It's very possible that you can do that. Anyway. Okay. So, table bases, endgame table bases. I don't have them commented in right now because I haven't really verified them and if they work. And it's kind of hard to verify if they work, to be honest. It takes a lot of testing, I think, because these endgame kind of scenarios, I feel like my engine kind of wins that already. I couldn't find that it was some great benefit to having them in the engine. So, yeah. I do recommend that you give it a shot, though, if you get to a certain point. I only have 3 to 5 men endgame table bases. I know people that go up to 7 or whatever. But yeah, so what that is it's basically just 3 to 5 pieces on the board, and we are probing the table bases to find which move is the best. So yeah, that's basically what's happening here. I don't do it if there's castling or if there's an en passant index, which I mean, like, rarely that would even be the case with 5 pieces on the board. And this is how I probe them. And this is the reference code you can use, I guess. I think that this works properly. What this is doing is it passes a results array that is an empty array to Ziggy. Okay, that's the format. Ziggy is also a person that came up with it. It passes that array as in the results there, and then it gets back information, right? And then we loop through the moves, and then we get information from that results. I don't know. I think that these are macros. Okay. That or maybe functions that decode it for you, and then you simply use that to find which move it's referring to, and then use the information to sort your moves. This is the top level function. You also have a function at the bottom, like at the bottom of your search that you call. But yes, so this is the slower version that's supposed to be used for move ordering. Okay. So here's where we get into iterative deepening. Iterative deepening is we are going depth 1, depth 2, depth 3, depth 4. We don't just search to a depth of 8. We don't just search to a depth of 9, a depth of 10. What we do is we are going to search down to 1, then down to 2, then down to 3. Then down to 4, and come back up and go into the next deeper every time. That's what this loop is doing. Now why iterative deepening? Why not just go down first? Wouldn't it be faster? Well, there's a few reasons. A part of it is kind of the phenomenon of transposition table and move ordering, but also a part of it is time control itself. Because when you go down to an iterative deepening and you run out of time, you simply just revert to the last iteration, which is the last depth, right? So let's say you get to depth 9 and you're halfway through the search and then you run out of time, okay? Then you use the move that you already stored from the search that you went to depth 8. That's a part of the reason. The next part of the reason is kind of, I guess, my kind of thinking of it is that your search becomes richer because of good transposition table entries that are informing the later depths that you have stored from the first entries. I'm not sure if that's exactly the case, but I think, in terms of my own engine, what I've kind of observed is that case. Anyway, surprisingly, it's fast because of your transposition table and because of you are storing all the information from your previous searches. You can, go faster through the same information again. Anyway, so going through the code here. So search data, I simply just set everything to 0. Okay, this is pretty standard. I just memset the PV table. Memset just sets memory to 0. Okay. Based on if we have search flags, I set the flags to the amount of nodes. If we're going nodes per move, okay, just basic stuff. I just set everything to 0 for the root. Then we have aspiration windows. Okay, now what are aspiration windows? It's kind of hard to explain what aspiration windows are without entering into the search and explaining things with that. Basically, back at the start of this long video, I talked about alpha and beta, okay, and how one was going to be negative infinity in my example and one was going to be positive infinity. Now, what if they weren't, infinity? Well, that's what aspiration windows are. We typically do this. I've seen people do it from depth 5 to depth, 6 or 7. It starts at. You're going to go through the first few depths just with a normal full window of negative infinity to infinity, and then we are going to assume that you have enough information about the ballpark of the bounds that we are going to create a window around that last score that you got. And so let's say you do the first 5 depths, right, and you get down and then you come back up and then that last score you get is like 80 or whatever, right? What we're going to do for the next iteration is we are going to set alpha at a delta below 80 and then beta at a delta above 80. Does that make sense? So you're creating a window around your previous score. And what this does is it speeds up your search. It speeds up your search. Is it completely sound? No. But it does speed up your search quite a bit. And it is pretty standard to use it in general. However, I recommend not going for like an insanely small window, especially at first. I started with like a window of like 120. I think that my window right now is super conservative, and now with all the tuning, I should probably bring it down or tune it. I should probably SPSA this, but I haven't gotten around to it. But yeah, I pretty much just set it and forgotten it. Every time I try to change it, probably like weeks ago now, it just made things worse. Okay, I scale it with depth. Okay, now why is it dangerous, and how can you make it less dangerous? Okay, so you have to research when the score gets out of bounds. Okay, so let's say you search with this window, that you've set up, and you get a score back that is outside of the bounds. Let's say it's lower than the alpha that we set. What now? Well, it's basically saying, well, we betted that it would be in this, and since it's out, we have to research because we don't we don't have the proper information, to like, to be sure of it. It's kind of just the way the bounds work, that if it goes out, we probably discovered something that changes our search, and so we have to search it with a full window. And so full window, what does that mean? I basically break the window in one direction. So let's say that it's below alpha. I set alpha to -infinity, and then I research. You don't have to break the other end. I used to break the other end, but then I saw in some other engines that they don't do that way, and so now I just break one end of the window, because you already know which direction it's going in. So you do that. I used to like try to like gradually widen the windows and stuff. It really taints your entries, your hash entries, and things like this. Or at least, this was my experience with like gradually widening the window and going looping. It just taints your search, and especially your hashes and stuff. So I highly don't recommend that. Yeah, so that's pretty much it. It's not too complicated. But yeah, so this is where we do the search, right? So this is what it is. Okay, with a multi-threaded context, I use pthread create, and it basically just sends a thread on a mission, and then I just join them afterwards. Pretty standard. Okay, you want to join threads when their job is finished. And so I'm not sure exactly why, the reason that is. The whole multi-threaded thing always confused me. But anyway, that's basically what this is doing. We init the search data for each individual thread, since they all have different search data, as I said earlier, and we call search thread. This is the function that we put the thread on a mission to. Okay, and I go and I loop to thread count, and then I set it to search thread. So what is going on in here? So this is the root. Okay, some engines have their root inside of their regular search, right? They just set a flag that this is the root. I don't have pruning in the root. I don't have any reductions in the root. I don't yet see a reason to. Like, maybe there is some, but I don't see one right now. And I still do have logic inside of here that would make it kind of difficult, but maybe it's something that I'll think about in the future. But anyway, so basically what happens here. So this last state thing, you may be wondering, right? Like, what am I doing here? I'm basically linking the new state, the latest state on the thread data. Before we enter into this, we copy the position struct, the game struct, into thread data. Okay, and so what we have to do now is, you remember how I already copied the state stack into thread data. I mem copied it and linked them all together. I now have to link this new game state to the top of the state stack, and that's what I do. That's what that is. Okay, and why I do that there is because then I check for threefold and for draws. Okay, so then I do do a check for if we're stopping, if we ran out of time. Okay, so down here, this is a lot of stuff that's probably a bit complicated, a bit hard to explain what's going on here. All of this has to do with my search stack. Okay, so we are setting my stack to 0. I initialize. Okay, so you remember how we did continuation history earlier, and I subtracted from the stack to find the continuation history that I was indexing into. Well, this is how that works, right? Is that I start off our stack at 8, okay? So because we know that we're always going to subtract 6 from it, and so I give us headroom. Okay, so that's why we're passing the pointer down and not just indexing into it, because we start our ply our ply 1 at 8, okay? Because at ply 1 we still might subtract 6, right? And so this is what this is doing. This is iterating through the first part of the stack to store values there that are just empty. And the reason why is because we don't want to index into a segfault, right? We don't want to crash, like go out of bounds of the array. We can't do that. So that's what we do, is that we set the first 7 to null values, and then we set stack plus 8, and then that's what this is. That's why it's piece none 0 is just empty space. Okay, so then I evaluate. Why do I evaluate here? I evaluate because I want to cache it to check for improving later. We're going to get into that in a second. And then we just while loop through the moves, exit out when we hit the move count. This atomic fetch add is finding the new root index for the next move that we want to check, and then incrementing it so that each thread goes onto a different move. You don't want threads, going through the same space. Okay, we memcopy a fresh instance of the game just to be safe, and then we, once again, very important, we need to link the new game state to the top of the stack again, and then we make the move. Okay, and once again, going back to this is the S-1, that means that it's 7, and then that we pass down S, which is 8, which is stack plus 8. So, and then we set also here, once again at 7, we're setting the final, right, for this for the ply previous, right? Because we made a move here, we made a move at ply 0, and so we need to set continuation history and concore up for us to index into later when we do move ordering. So that's all of it. Okay, down here what I'm doing is I am checking if the score we got back is the best. Okay, it looks complicated, but that's all we're doing. And then if it is, we are storing the PV. Okay, now what is PV? We'll get into it later. But then we are memcopying the PV table, the top row of the PV table, into the root to make sure that it has the current principal variation, and then we undo the move, and that's it. All of this stuff is not in use. Okay, so that's basically it, right? We go down, we find a score. In the root, we aren't doing anything fancy with it. We are literally just saying, hey, is this score better than everything else? Okay, so you may see, this monstrosity of a search call with a lot of arguments. What is this doing? Some of these things aren't in use necessarily, but this beta alpha, what this is. So, like I said earlier, with the beta and alpha, that they're getting swapped. This is and negated. This is what I'm saying. This is exactly what I was saying. The negative beta and the negative alpha. If you go here, you see that this is supposed to be alpha, right? And so our negative beta becomes our new alpha. This is what I was saying. Okay, so why is this important? Why is this important? Because when you negate something and swap them, you are switching side. You are switching side. So this is how the opponent is going to view our bounds, which is what I talked about at the beginning of the video with the scenario with the negative 45, and then the opponent has a 45 ceiling. That if they go above, we know that we can't, that we'll never even look at that move that we played to reach that fail high, so we can just completely cut the node off. Okay, okay, so we're gonna get into what all that looks like. So all of that is that and And so I have no clue how to really go about this function. It is a massive function, but I'll just go down from the top. Okay, so we do checking for time here. We just check if our time is up, and if we are doing nodes per move, then we just check that. Okay, very simple. Now, node type. What is node type? What is nt equals PV? Okay. In some engines, we use a node type that isn't inferred. Okay, so what do I mean by this? Well, there are 3 types of nodes in chess programming. There are all nodes, there are cut nodes, and there are PV nodes. What do these terms mean? Well, a PV node, it varies, I guess. Like the definition of a PV node in terms of our search is maybe different than how others might think of it based on, you know, us raising alpha, you know, or the score is in between alpha and beta. The definition of a PV node is usually one that we, you know, a node that we search with a full window rather than a null window in terms of our search. So a cut node would be, you know, a fail high node, and an all node would be one where we are under alpha. Okay, you know, at the end, right, where we don't raise alpha. Okay, so this node type, what does it signify? Well, mainly it's going to signify if it's PV or not PV, and that's literally all I have is PV or non-PV. I got it from like old Stockfish pull requests and some other engines, and I just couldn't understand it because to be honest, right, like most engines do this, right? They determine this expected PV node flag by if alpha doesn't equal beta -1, which means that, you know, null window. What is a null window? Well, the null window is exactly that, where alpha is 1 under beta. Okay, you're gonna see us, you know, do a lot of null window searches during this. So I was really confused because, you know, isn't this just the same thing? Aren't we just inferring it, you know? And it's strange because it actually changes the search, you know, and I couldn't figure out why. And I think it may be, you know, a number of things. I think that there are some heuristics that we do that it's important to reinforce that this is a null window. And I think that there may be some cases where a window ends up becoming a null window when that wasn't what we intended. And so it's perhaps important to be explicit with this, and it directly impacts how we store things into the transposition table and if we retrieve things from the transposition table, as you're going to see. So depending on whatever you want to go for and whatever you test within your engine, you may want to go for the detecting the window approach of saying a PV node equals alpha doesn't equal beta -1, right? You know, a bigger window. So you can definitely go about it that way. I also have asserts here that assert that that is actually true, right? Every PV node for me is already with that, you know, not null window, right? This is what this assert is doing. So this just me reinforcing it just makes sure that our intention is correct. Okay, so that's what that is. This PV node flag is expected PV node. Okay, it's not. We haven't really verified that yet. But it's the same as the expected cut node flag that we're going to talk about. So first things first, when you enter in a new node, you need to check for draws. You don't want to do any work in a node where it's a draw. Okay, hi. I have been watching back these, these sections of the video that I record on different days, kind of like a podcast, just to try and make sure that I'm not missing explaining anything. And I think that there are a few things, since the search portion of the video was so complicated and had so many things inside of it, I was really worn out by the end of it. I'm sure you can tell if you watch it back. But I wanted to put this before the search section, before I start talking all the way through the main search, all the way through QSearch, because I do need to give an introduction to some things that I don't really explicitly say later. They are kind of implied, but I don't really, to me it's kind of second nature, but to you it might not make any sense. And so I want to talk first about null windows, because I talk about windows and I talk about us raising alpha, failing high, right? And I explain, what all of this is and how it shapes our search tree, right? That failing high means that in the parent node we already had a better move, and we have refuted the current move in the child. Okay, so I explained that in the traditional sense, a PV node principal variation is when we raise alpha, but we don't fail high above beta in a node. Okay, and you can think of this, a principal variation is the best possible continuation from both sides. And so that's what you can think of this. We are inside of our lower and upper bound. We don't refute, and we aren't so bad that we don't raise alpha at all. Now, when I talk about null windows, the way I describe it in this video is that we are testing against some value. Okay, and I simply don't really explain explicitly how that works. Okay, so I'm just going to go to an example with a null window. In fact, let's actually just go straight to the PV search. Okay, so this is the null window that is kind of inherent in a PV search, right? Is that most of our searches that we're doing here are actually with a null window, right? It's only within PV nodes that we are doing a full window search. Okay, and so what are these these two null windows, right? And how do they function, right? The purpose of these null windows, and why I say that we're testing if we can get above alpha, is that it turns our search children into a binary function, right? We are passing down to the child a window that is only one wide. Therefore, alpha can never be raised. The condition to raise alpha is a score that is above alpha. Okay, and if you think about, let's say alpha is 0 and beta is 1, failing high is greater than or equal to beta. So therefore, being above alpha means that you're failing high in a null window non-PV node. And so this is what I wanted to explain when I say that this is a binary search. Null windows are a speed optimization because you're failing high a lot more, because you don't have a full window where you can raise, right? You're simply saying, if we ever go above alpha, we are failing. We're getting out of the node. And so that's what I wanted to explain. That's why it's a speed optimization. Now, how does that affect our search, right? Like, why you're going to see me explain in the next portion of the video when we use these null windows, we often get a score back, and then if it's above this bound, then we research with either a full window or we do a deeper search. So why this is because we can trust null windows less, because the logic that I just explained, where everything above alpha is a fail high. That means if we're only a little bit above it, it's a fail high. If we're a lot above it, it's a fail high. So we don't have that fine-grained sort of information to make correct inferences a lot of the time if we have a null window. And so that's why when we are in a expected PV node, meaning we have a full window, okay, right here, when we spawn children from here, these are going to be PV nodes, with expected PV nodes with a full window. Those nodes we prune a lot less in, okay, because they're inherently more valuable for us because of the more accurate information that we're getting back from them. Okay, and I wanted to put this before I started talking about search, because I was listening back to what I was saying, and I simply I don't really explain it properly. So there are a couple other things that I want to mention here. Okay, I also completely missed talking about how do you store the PV, the principal variation. Now what is the PV? Here I was doing some preparation for what I'm going to be talking about today, which is, hopefully today is the last recording day. I'm going to talk about evaluation and how to set up an SGD or Atom tuner and SPSA tuner. Okay, so this is going to be probably the most complicated recording day, but as you can see, this is what I was doing here. I want to show you though, very quickly, if I can show you something. I want to show off, I need to bring back debug information because I was running my SPSA overnight, but I want to bring back all of these printouts to talk about what does the PV look like. Okay, and so we're going to see a printout right here in a second. I'm just going to set it to auto. By the way, what is auto? You see me type in auto is just the engine playing a game against itself with the same engine instance. It just simply plays the best move, and then at the end of a search, right? And then it's just a very simple way for me to debug. Okay, so we see printed out here a bunch of stuff. Okay, so this is all my search debug information. I also kind of gloss over this. Okay, so yeah, so I don't really talk down here about like what's going on here in the video. I talk about the aspiration window, but then I somehow missed what's going on down here and how we store our best scores and stuff. So let's just talk about this now. Okay, so down here what I'm doing is I do talk in the video about how I accumulate search data from each thread into the mutex in the root that has the entire search data. Okay, and this has every count of every raw heuristic that we have reached during the search, millions and millions. And that's what you see, all of these, we had this many hits, this many probes. Some of these just aren't in use currently because I've restructured the search. We have this many of these prunes, we have this many of late move prunes, this many futility prunes. So that's what that is. I highly recommend you do something like that where you can toggle it off and on. And down here is where I print out the PV. This looks a lot more complicated than what it actually is. So the reason why is because I have two printouts here. You can see here I have info and then I have this. Okay, I have info and then I have this. This is because info is what I'm sending to UCI. UCI recognizes info as an input command to display that those things within the GUI, like the score that our engine sees and how many nodes we traversed and what the principal variation is for our engine. And then I have just a version that just doesn't have info underneath it, and it's because sometimes in some GUIs, if I have my engine on plies or whatever, it will completely obscure the debug information from me. It will only say, sometimes just the info at the end of the search rather than throughout each depth of the search. And for me, when I'm working on my engine and maybe something goes wrong, I need to see at each depth, what the PV was, if the PV got somehow truncated. Okay, these are important things to know. However, sometimes they get obscured from us. So that's why this looks a lot more complicated than it is, because I am concatenating these moves onto a string that I print out separately. Okay, so I'm basically printing everything out twice. So you can just in your mind, just get rid of this, okay? Because I'm not actually talking about this. This is just me printing out the PV in a loop after I print out this info string with our depth, our score, and our nodes. Okay. So I'm printing out the principal variation. Like I said, the principal variation is the best possible continuation that our engine sees from both sides. So in this case, what I was showing off is what the PV is. I really need to also change that this is, I'm just so lazy that this changes the text to black, and this is completely my fault here. I need to fix that. But as you can see, we have E2, E4, D7, D5, E4, D5, E7, E6. So completely normal opening, right? Our engine is expecting the opponent to play the Scandinavian, and we will accept it, right, with that E4, D5. And so that's what the principal variation is. And if you have a correctly structured PV, it should typically be as long as the depth itself. And I'm not entirely actually sure if ours is in this case, because I've been working. But this is, if I do have a bug here, it is probably due to the work I've been doing lately. I'm trying to count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. So no, this is 14. Okay, so we have one extra. Now why do we have one extra? It's because I also store the PV from QSearch. Okay, so you want to have a PV that is at least as long as your depth. Okay, that's kind of the proof that it is working. And how do you do this? Well, the way I do it now is with a triangular PV table, right? The classic kind of implementation. I used to use just simply the transposition table. Now, how do I do that? I could probably revert to the transposition table now that my replacement policy is more correct, right? And doesn't replace, PV, what would be in the PV, okay? But in the beginning, things were more rough around the edges and not entirely correct. So how did I use the transposition table? Well, you can think of it as the transposition table, as I say later in the video, will store this best move, okay? A move that either raised alpha or failed high, okay? So by definition, each position in a chain, when we play the best move, should lead us through the principal variation inside of our transposition table if we did everything correctly, right? So from the position we are at currently, if we play the best move and then search for an entry in the transposition table, it should give us the next best move to keep following the chain of PV all the way to the end until we don't have it anymore. However, depending on your replacement policy, it may be entirely possible. I'm sorry, my voice has been dying because of how much talking I've been doing the past few days. It may be entirely possible that that you lose the PV, and your PV may become truncated, especially at high depths. And so you can do that. It's a very, very simple way of going about things. It's simply just a while loop until you reach the end. It does require correctness in everything else. Okay. That's not to say that the triangular PV table also doesn't require some level of correctness. So what does the triangular PV table look like? And what is it? Okay, so a triangular PV table consists of actually two different tables, two different arrays. Okay, we have one table that is indexed by max ply and max ply. Okay, it's a three-dimensional array. And then we have another one that is just indexed by max ply, and we call that one the PV length. It's exactly what it sounds like. The PV length stores at each ply going down from the root what the PV length is. This makes it possible for us to iterate it and also reset the PV length when we enter into a new ply, which is what we're going to be doing here in a second. So I want to show you just what these look like. So inside of my search data, I have the PV table and the PV length. This is what I was talking about, indexed by max ply, and the PV length is simply an integer that goes to max ply, while the PV table has our actual moves inside of it. Okay, so the implementation is just the standard classic implementation. There's a wonderful video on it by Code Monkey Kings, and I will put that video in the description. And it is exactly this very code. It comes from I believe the CPW engine, the didactic engine that a lot of simple ideas are based off of. But yeah, so this is exactly it. The precursor to this that we have to do at the top of each node is we need to reset the PV length. We need to reset the PV length so that we can copy in the next ply. Okay, so instead of what we may think, right, is that we are going down, and so we are propagating downward, right? We're getting longer. When the nature of a PV is actually in the back propagation of the recursion. So actually, we are copying in from ply +1, meaning underneath us. We are copying up and up and up. And so this is what this is doing, right? We are inserting at the first index at our current ply the best move, okay? The move that raised alpha. Of course, move that raised alpha, and this is not when a fail high, right? I explicitly store PV after I check for a fail high, okay? So that's important. Okay, so we are iterating up until the PV length of the next ply, and then we are copying in those values, right, into what is after, right? So we are going I +1, right? So we are starting at 0 with our current move, and then we are copying in from the ply beneath us everything past that move. If I'm making sense, if I'm being clear here. Okay, so we are going to the PV length, so we are copying in a chain. It starts with our new best move, and then what was the chain afterwards, and we're copying it up. Okay, and then simply all we do at the end is we set the PV length for our new ply is going to be the PV length ply plus 1, okay, because we have extended by 1. Okay, so hopefully this helps you understand. Okay, so the PV, to help you understand a bit further, it's the opposite of what you would think. It's actually shorter at the bottom than it is at the top, because the top has the full chain, while when you're propagating up, that's why we are adding 1 to the length every time we go above, is because we are, adding on till we get the full extent at the top. Okay, so hopefully that helps you understand. I know it is a bit confusing, but so I wanted to say that first. And so you're going to see I do it where I reset the PV length. Obviously, I believe I have to do it here, right? I reset the PV length at the top of the thread's root, right? Which is something you have to do. And then I reset the PV length at the top of the search, but there is a special case here. I believe now I just do it here. Okay. Now you may run into some issues with this, and I'm trying to remember how I figured my way past them. It's hard to remember, to be honest, but if you have any trouble here, it probably is honestly some other way you're handling the PV that is truncating them. If you follow this implementation exactly, it will probably be some other way you're mishandling the PV. Now, what do I mean by that? Add these asserts. These two asserts are necessary, in my opinion, right? And these basically assure that alpha never goes above beta. I was really surprised when I added these asserts in that they failed. That at some point in my search, alpha somehow became above beta. And so it's something that should never happen. Never. Because alpha is lower, beta is upper. So add these asserts, and it will show you, hopefully, where you are mishandling the PV. Okay, so this was like a 20-minute sort of amending, okay, of what I went over, and I'm trying to remember what else. I talked a lot, and okay, so here's something else I wanted to talk about. I did a lot of testing last night with IID, with the implementation that I had switched to with just depth -1, right? The idea is with the depth -1, I've seen it in a few other engines, that it simply gets us lower and lower and lower so that we can get a TT move next time, right? However, it is incredibly risky, right? And so since I was talking through it, and I was talking through it, and was sorry, I just got distracted. I just I got like math stuck in my head or something. Since I was thinking about it, I thought about it since I was talking about it, and then it came onto my mind. Like, it is weird that that this is this way, and then I switched it back last night to my last implementation. I was going through some test fence and some test positions, and I was testing these two implementations against each other, and this one was performing better. And so this is perhaps something that I wanted to talk about, that a lot of the things that I'm going to say in this video and talk about are what I have gathered from many different sources. And so all of it will maybe, not be entirely not correct, but things that I'm going to follow even forever, right? I'm making this video, this isn't a sort of a video where I've figured everything out, it's a sort of video where I'm saying this is what I've learned, and I may learn new things in the future, and things that may make some of this information possibly redundant. I'm only making this because I think it's perhaps some way to bring purpose to the Sisyphean task of programming all of this stuff yourself, is to perhaps give some purpose and say, if I was to do this again, I would have liked to have this resource kind of explaining all of these things so that I didn't have to, look at these things confused for so long. And so this implementation is what I was kind of referring to in the further part of the video that you're going to get into, is this other way of going about internal iterative deepening, where you simply search at a low depth. Okay. And so what I'm doing here, this may seem confusing. This is actually just one. We're searching at depth 1. Well, no, we aren't searching at depth 1. We are searching at depth 1 at the bottom depth that we do IID at. So basically this is saying if we're doing IID at depth 5, we are going to drop to depth 1 to do this search. And so if we are, at depth 10, we're just going to subtract 5 and then go down there. Okay? And this is the implementation that I saw in multiple different versions of Stockfish. And it's different from the traditional IID that I have been kind of struggling with for a long time. And so, testing these test positions, I found that this simply performed a lot better. And actually, found really, the best move, sometimes in a couple of plies earlier, which I was very surprised on. So this is something you may want to try for yourself as well. They use a much higher depth than I'm using. I use depth 5 right now. And so what this is, once again, is here you are just searching at the very same ply, just as at a lower depth. So you are seeing, can I get a transposition table move, and it's less expensive since you are doing it at a lower depth. However, it is still expensive because you are still having to go through QSearch, at depth 10, you're basically doing a depth 5 search on the same ply. It is sort of dangerous if you're doing this many different times in a search. So anyway, that's what I wanted to talk about. I think I covered everything that I wanted to discuss. Oh yes, so a couple of other things that I want to clarify. There are a couple of times where I'm a bit foggy on how I want to choose my words when it comes to talking about how we are moving. When we're improving, why are we scaling back our prob cut beta? When we are improving, why are we increasing our NMP reduction? And so I use the word momentum or velocity or something like this. And what I mean by this, it's a bad choice of words. What I mean by this is that we are inferring from our direction. And I also say something similar when it comes to the core hist updates and the conditions for a core hist update. I directly I say momentum or velocity. What I mean by this is it is taking our, directional vector, right, from our from 2 plies ago, right? We are saying we are better. So it's the direction we're going in, right? And so these heuristics that are checking if we are going to cut, if we are going to be above beta, right? If we're going to cut, if we're above beta, right? The NMPs and the prob cut specifically, we are bringing down those margins. In my, assumption, right? It's kind of hard because to find, literature on this, but from my kind of reasoning about it, it's that we already know that we are going upwards, right? That we are, reaching that upward bound. And so that's kind of my my thinking about it, as well, as the chorus update, where it is checking if our new at the end of a node, when we process the node, if it is upward from our static evaluation at the start of a node. This, I believe, is direction, and so to update we have to fail high if we are going upwards, and so it's sort of a validation. If we are failing high, we don't want to have been going downwards, right? Because that would give a misleading sort of gradient, right? Because if we fail high, the idea is going upwards. So if our static evaluation was higher than where we ended up, but we still failed high, we don't necessarily want to reflect that inside of the corrective history, because that gives kind of a misleading sort of correction, right? Because fail high should mean going upwards. So hopefully that gives some clarity. I know that putting this probably before the search is probably going to be a bit confusing, but hopefully it's kind of hard to order these sorts of things, because I don't want to amend something afterwards, because then you've got to go through. I mean, this is an incredibly long, you're gonna have to watch like an hour until you get to the amending, and so hopefully this helps you understand. Okay, so now I'm going to go over there and get my water because my voice is dying. Okay, so I'm starting to realize that I think I grossly underestimated the raw amount of time that this is going to take. This is 4 hours, but I still have to go through the majority of search, go through evaluation, and then go over the tuning stuff. And so I'm going to try my best, right, to go through this. I'm trying to be very to be very accessible and to explain things, not gloss over anything. So I'm going to I took a break, and I'm going to come back and keep going, and I'm going to start off from when I talked about the expected PV node thing. Okay, and so because I kind of got out of it, but I'm back and I'm gonna stay in it. So here we check out the draw stuff, which is similar to exactly what I did in the root. We just do this before we do anything with inside of the node, because you want to make sure if it's a draw, then you just return straight out, right? 0 is the draw score. Now, threefold, how do we check threefold? I check it with our state info, okay, which is that linked list thing, and so I just walk it back. For you may have a key history, like it's exactly what I had when I did this. Was a key history that was simply, I believe it's probably even on the key history is still on the game struct, yeah. So it's this just literally a list of all of the keys, and you're just gonna put a new key on the list whenever you make a move, and then when you get rid of a move, you're just gonna decrease the counter. So that's what the key history was, and you may have that if you don't have the whole state thing set up, and that works completely fine. But you're just going to iterate the key loop, the key list, and then just find matches with the current key, and then that's how you detect threefold. If there are three keys that are exactly the same, that's the exact position, because keys are the exact position. So that's what that looks like. And then down here is the endgame table bases, right? This is how I probed them. I have it commented out once again because of me needing to test it more. But I believe that this is the correct code. This probes the endgame table bases for 3 to 5 men. This is the exact. I can't remember if I showed you Fathom earlier, but that's pretty much what everybody uses. Okay, so you can go to tbprobe.h. Okay, and then this will show you all the documentation you need to figure out all this stuff. But it's really not that complicated. This is the one that we do during our search to try and find if it's a winning position or a losing position. I don't have a lot of fancy stuff here. You can go and look at the Stockfish implementation of it. It's got a lot more in there, but I haven't found the need for a lot of it yet. Mainly, my engine kind of wins once, games are usually decided by that point. But anyway, so QSearch, this is what I was talking about earlier. At depth 0 or less, sorry, once again, my space heater is going off, so there might be sound in the background. It is cold, so I had to warm up. So QSearch, we drop into QSearch when the depth is 0 or less than 0. This means that we've bottomed out our search, and now we are looking to close it out, right? So I forget if I explained what QSearch is, quiescence. Just to go over it again, quiescence is us trying to find a quiet position to evaluate from, because those are the stable positions where we can actually trust an evaluation. For example, if our queen was just out in the open and about to be captured, we might evaluate that position as fine, but then our queen gets captured in the next move and it isn't actually a fine position. Quiescence prevents that by playing out until there are no captures left. Okay, so that's what quiescence is. A lot of our search time is actually spent in quiescence, and so it is actually important. So we'll talk about that in a bit. So this is our probing for our transposition table. Okay, so this is what we've been talking about all this time with the bounds and the transposition and the keys and the hash keys. This is what it's all leading up to, right? We look into our transposition table using our hash key. Okay, once again, all of my arrays are on the stack, our stack allocated arrays, and so there's no looking into the heap for it, so it's very fast. Okay, and then we only use TT entries that are greater than or equal to our current depth. Why is that? Well, I already did this, in my last time I recorded this. I already did this, so you can see it right here. But I wanted to show off what it looks like if we break this rule, because it's going to break everything you're going to see here in a second. So let's say this is a normal search. This is what my search normally looks like, single-threaded, okay? Very normal. We get E2, E4 from start position, which is, the textbook move, okay? So now what happens if I say, well, we're not going to verify depth anymore? What's going to happen? Well, let's take a look in terms of iterative deepening. What happens when we don't validate TT depth? Let's go and see. Wow, really, really fast, huh? Wow, depth 21. Our search breaks, okay? And I can show you it breaking even more if we do it in PV nodes as well. The depth number may look really fancy, but it breaks the search. It breaks the search. Why? Because we are no longer searching positions. See? Yeah. So we are, when we get rid of the PV node flag as well, we are literally only searching depth 1, because in every subsequent depth, we are simply early outing based on our stored results and not searching any deeper. You can think about this in terms of iterative deepening, how we go to depth 1 and then we return back up, right? And then we go and again in the loop and we go to depth 2. And we're going deeper every time, but we stored that search at depth 1, we stored it at depth 1, okay? And so you can think of that now, that plies at depth 2, okay? So if we are using all of those values and then early outing at what is now depth 2, then we are literally just going to return out of the function, okay? So to keep searching new information, we can only trust entries that are at our current depth or above it, or else we risk completely destroying any chance of uncovering any new information in our search. And so I hope that example helps to show you what all of that is. So that's why those conditionals are here. We have stack excluded move equals 0. This is excluded move. It has to do with singular extensions, which I'm going to talk about once we get into the moves loop. Okay, so adjust mate score from TT. I'll talk about this in a second. I wanted to talk about how do we decide what to store in our transposition table, how to store it. I think it's important to talk about this now. We've already talked about alpha, beta, and what these bounds mean. I am noticing that my face is kind of dark on the whatever. I typically don't like to have this this light near the window. I don't like to have that light near the window because then like bugs sometimes get in, you know, like they can sometimes like crawl under the window, you know, if I have a light next to it. Anyway, what am I talking about here? I'm talking about, I think it's important to get in now since we know what upper, lower, and exact are. I think I explained this right. We have 3 types of nodes: all, cut, and PV nodes. And exact entries are entries that are in PV nodes and they raised alpha, okay? Upper is where we didn't raise alpha, right, and we were, you know, lower than alpha the whole time. And then a lower bound is where we failed high, okay? So, sorry. How do we decide which entries to keep? Do we just overwrite every time? No, we do not overwrite every time. How we do this is, well, this is where we search. I have bucketing implemented. Now, what is bucketing? First of all, how do you index into it? You index into it like this, okay? You're going to AND your key with the mask value. What is the mask value? The mask value is simply the size of the table minus 1. That's all it is, okay? And so we can see the values here inside of my constants. They should be here. Yeah. So this is exactly it right here. So I have the amount of space in my transposition table is power of 2, right? So it's 1 shifted over by 23. That's the size of my transposition table. I suggest you do something similar, okay? And then my mask is simply the size minus 1, okay? And that's just how the hashing works out. And so this is what that looks like, right? You're just going to and your key with the mask, and that's it. And that'll give you the index. Okay, and that's the index that we use right here to index and find the entry. In my case, I have bucketing. Bucketing is very simple. I don't know if I'm going to keep bucketing, and so I was considering not even going over it, because strong engines sometimes don't even have bucketing. Like, I don't even think Stockfish has bucketing. What is bucketing? Well, bucketing has, typically 4 slots, okay, of inside of one hash key, right? You can have different entries inside of one. And so the goal is to only get rid of entries that are older and shallower. That is the main idea behind transposition table, is the deeper that they are, and the the newer entries, right, is are the ones that you can trust more. So as you can tell from here, right, TT entry depth is greater than or equal to depth. Those are the entries we want to store, the deeper ones. What do I mean by deeper? It's kind of important to go over here. Deeper, when I talk about deeper, I'm talking about closer to the root, okay? So as depth goes up, okay, we are higher up in the tree. As depth goes down, we're closer to the leaves. So you can think of it as the opposite of ply, not, just for you to think about it, to get a handle on it right now, although it isn't ply at all. But that's the main idea, is that the stuff that has high depth, those are the things that we trust more. Those are the things that we don't want to prune as much. Why? Because they have all of the search tree below them that is recursed all the way up. The shallower, the lower the depth is, the closer we are to the leaves, and the less the search is underneath them, right? We can't trust it as much, and we can prune those things with more certainty. Because if you prune stuff at the top, then you're cutting off major parts of the tree. When you prune off things at the bottom, you're only getting rid of garbage leaves, So that's the way you should think about depth and plies and things. So the higher the depth, the better, so just for you to think about it. So how do we decide what to store in the transposition table? If you said that's why you said we cherry pick, we don't overwrite every time. Well, I'm going to show you the condition that I use, okay? And here, this is the condition that I use, okay? So this is pretty similar, I think, to Stockfish, and I'll show you what I had before was. Okay, this is similar to what I had before. Okay, so what are the differences? What is any of this doing? I've tried everything from +1 to -4. All gives actually a very different result. You'd be surprised. So what is this doing? So this depth that we are taking in is the depth that we are currently at, that we are storing, right? So if our depth is greater than the entry depth, then that typically means we want to overwrite it, okay? But here you can give a certain margin of how high we need to be above the entry depth to overwrite. So that's important to understand. So that's the thing that you can play with. Now, entry type equals upper that I just wrote right here. What does that mean? Well, upper bounds are the ones that we can trust the least. They are the weakest. This is something that I'm kind of I don't understand 100%, but I think it's got to do with that uppers are the most common, I think, and so also they give us the worst outcome. Okay, why do uppers give us the worst outcome? Because uppers don't let us fail high. And uppers aren't PV nodes, uppers aren't exact entries where we can exit out, right? Uppers are bounds that aren't strong, that we can't trust, because and they won't make our search go faster or be better. We want lower and we want exact entries, and so typically getting rid of uppers is a good thing. And other engines do this in various different ways. You can do this in many different ways, and it's something that I definitely want to play around more with, but yeah, so that's basically what this is. So yeah, you want exact entries, you want lower entries. Lower, once again, is fail high, and exact is raise alpha. Okay, so we can get rid of this. I almost quit out of Helix. That would have not been good. Okay, so what are we doing here other than this? Like, what are we doing with the score here? Okay, so first of all, we adjust the score from the mate. Okay, so what does this do? Okay, well, this if we have a mating score, which I define as greater than or equal to mate score minus 200. Now, what is this? How do we define this? Well, it probably the simplest way to do this would be to show you when we return a mate score. So I'll go down here to where we return a mate score. Okay, so I return the mate score here. If we don't have any legal moves and we're in check, we're obviously mated. Okay, so how do I do this? Negative mate score. Mate score is a positive value. I don't remember what it is, but some large value that you would never reach otherwise. When we do negative mate score, we're basically saying we are mated. Okay, so when we add ply, what does adding ply do? Adding ply gives us an indication of how far the mate is. Without adding ply, what our engine will do is it will not know which mate to choose. Okay, if you have every mate score just returning mate score, just every mate just returning mate, no matter how far it is from the root, your engine is going to chase around random mates, even if they aren't the one that happens in the least amount of moves. This will, result in just your engine not being able to find mates because there are so many mates, and some of them are 20 moves away, and some of them are 1 move away, and it'll just keep, moving the queen around the king, in an endgame. So the ply is how we indicate to our engine how close it is. So when we add the ply to a negative value, right, it is subtracting from that ceiling. And so when we get a negative mate score back, right, what this is doing is we are this far away from the mate, right? And so the lower the ply is, the closer it is to the root, and so the higher the score is going to be. You see what I mean? So let's say we have a mate score of negative 30,000, okay, and we subtract a ply of 2, okay, so now we have negative 31,998, okay. Then what's going to happen here is that if we have another one, say of ply 20, that score is going to be less, right? And when we negate this mate score, right, and the other side has now a positive mate score, we want to have the higher score, right? And the higher score is going to be the one with the least plies. Okay, so that will tell us, our engine, which mate to choose, basically. Okay, so now what happens when we store them in a transposition table, though, is that we need to retrieve them. Okay, every engine does it the same way, the exact same way, exact same code that I'm going to explain it here. So if your score is a mate score, right, and based on the logic that we had just talked about, if the score 200 is basically just the ply, the max amount of ply, even though the max ply in my engine is something like 128 or something like that. 200 is just like the headroom we give it, right? Saying that if we are 200 within, within the ceiling of our mate score, then we're considering it a mate score. And I also say, if it's in the opposite direction, if it is less than the mate score plus 200, so if it's within that range of that 200 and the mate score and in the opposite direction, you see what I mean? Okay, so you need to know the sign, okay? So if it's a positive mate score, then you're going to do it this way. You're going to add the stored ply and then subtract the current ply. Now, how do you get the store ply? You have to store ply with your transposition table entry, okay? And so you're going to add that ply to it and then subtract your current ply. This is just the way the math works out. And we can derive this, right? The stored ply it's basically telling us, it's translating the mate score with the mate score minus ply that we did. It's basically how do I explain it? It's basically translating it to our current ply. It is getting rid of that stored ply, and then it is subtracting our current ply. So, what do I mean by this? So the stored ply, okay, so let's think about this mathematically, right? Is that let's say we have a positive mate score that we stored, right? And that was 2 plies from the mate, right? So that means it was 32,000 minus 2, okay? That stored ply is going to be 2, okay? So we add the stored ply, bringing it to 32,000, and then we subtract the current ply to update it, right? Let's say our current ply is 3. Well, it needs to have that basis of truth of where it actually is in where we are currently, how far we are currently from the root. And so that's what it's doing, okay? So this is how we get our scores outside of the transposition table. And I hope that, I know that it's kind of difficult to explain, but okay, so we get our adjusted score back, okay? So what do these mean? I'm going to put within the description of this video a link to the original, I forget his name that made this, who made the original code for the transposition table. But I'm going to put the Wayback Machine link to his website. This is the same website that CodeMonkey Kings uses in his video when he talks about the bounds of a transposition table. That's the original code that everything is based off of, right? Exactly this code. Pretty much everybody does it the exact same way. We return exact entries because they are exact. Excuse me, I just ate. Upper entries, which are once again all nodes, things that never raised alpha, never went above alpha. We're going to make sure that the score is less than or equal to alpha. Okay, this is us basically verifying where we are in terms of, if the bound is correct, right? If the entry type is upper, the score has to be less than our current alpha for us to trust that. Does that make sense? Because we have to basically say, okay, this score that we got back from this position is still underneath our current alpha, okay? And so we are basically saying this is going to be an upper, an all node, right? So it's the same thing with the lower. We are saying this adjusted score is greater than our current beta, okay? We are saying that we are accepting this bound because the bound is above our current beta, okay? So we are basically saying, we're saying that these bounds are validated because they have to be greater than our current bounds in each direction. Okay, so that's that. You can look at the code yourself, the original code. The only thing I will mention about this is that I don't use exact entries for quiescence. Okay, in that code, it does leave in here a transposition table storing for quiescence values. And I have never gotten any good results from it. So I'd highly recommend you being careful with that, but maybe try it out for yourself. Also, I want to give some insight here. The alpha and beta, as you can see, when we enter into quiescence, don't get swapped. Okay, so why is that? Well, when we enter into depth 0 and we go into quiescence, we are essentially passing the node off. We are not playing any moves. We are basically saying, oh, this is actually a QSearch node. You can go through some old Stockfish pull requests and see this for yourself, that they actually don't even have this at some point. They just straight up called QSearch from the moves loop itself instead of their recursive search routine. That is exactly what's happening here, basically, right? I also want to mention, though, like if you have, for example, if you have check extension, so if in check, if is in check, then depth plus plus, for a starting off engine, I highly recommend you do exactly this line of code. It will help you out immensely. If you have this, I highly recommend you go about this way of doing things, because this depth plus plus is going to affect your transposition table, how you retrieve things out of the transposition table if you hit QSearch, right? If you're at depth 0 and then you're in check and then you add the depth and now you're no longer in 0, you're not going into QSearch. So if you go for this, then keep that in mind. I don't have this anymore because I actually worked really hard to get this working where I didn't have this anymore. Now I have check extensions that happen based on the SEE of moves, which was an idea that I really liked, because there are so many garbage checks that happen in chess where a queen just runs in front of the king, right? And then, the queen that's an SE negative move because you can take the queen. But for us, we might extend on such a move because we're in check. And so I really like the idea of only extending when it's an important check, okay? So eval hashing. How is eval hashing any different from transposition table hashing? I do eval hashing separate. Other engines sometimes do eval hashing, including Stockfish, with their transposition table, actually. I thought that it was messy. I found it messy. I saw, bugs, things getting replaced that didn't need to get replaced. So I keep it separate. It functions exactly the same, though. You are just... my eval hash is a little bit of a smaller size. You index it the same via a position, and it just stores the eval at that position. And so that's what I'm doing here. Just like I retrieved the transposition table entry, I'm retrieving my eval hash, my hashed evaluation. And if I don't find one, then I evaluate this node, and then I hash it if we didn't get a lazy. Now, what is a lazy eval? A lazy eval is a optimization where, say we're inside of our eval and we add our PSQT, our material value, our pawns, the simple things, and then we find that the value is so incredibly large, right? That's what a lazy eval is. That when if a eval is so incredibly large or so incredibly negative that it falls out of the bounds by a large margin, then we can just return that score. Now, how is this sound? Well, it's sound because the margin is usually the amount of eval you have left to go. So let's say you have a lazy eval check after all of your incremental stuff, and you have below that, you have all your threats, you have your king safety. I will get into this later when we go over eval. You have all of that stuff. Okay, so what is this? What does this mean that we're exiting out early? How can we safely exit out early? Well, if the current value is greater than beta or less than alpha by the margin of the exact amount that we have left to go in our search. So that means the sum of all of the terms, of all of your threats, all of your king safety, all of your material. If you sum all of them up, if you're still above beta or still below alpha, then we can exit out, because we know that even if we finished eval, we would still be above it, right? We would still be out of the bounds. Okay, so that's how it works, and that's how we get it to be sound. Now, I have it disabled right now because I want to tune it. I'm still tuning my eval, incrementally, getting through it. So I want to keep, especially when I'm SPSAing, I do kind of feel like I've gotten better results having lazy off, and I want to get things to a smoother place before I implement it again. And I want to implement it with a bit of a safer margin than the aggressive thing I was doing before. Well, why is that? Because my king safety used to be exponential a little bit, and so I had to estimate, because some of my king safety values could be 900 centipons, right? And so if I wanted to have a meaningful lazy margin, I would have to compensate for that somehow. And so I had this idea for king danger, that was this heuristic that if there was too much king danger, then we wouldn't lazy, and that seemed to work. But I definitely have done a lot of changes in the eval now, where I need to figure it out. But the point is that I don't hash lazy evals. Okay, I found it to be a good elo increase, a really sizable elo increase, to not hash lazies. Okay, why? Because you just trust them less, and you can't trust them for things like improving, which we're just going to talk about now. So the maximum ply, I return the static eval. Okay, that you're gonna want that as well. Improving. What is improving? Well, improving is just simple. It's 2 moves ago. If our eval now is better. If our eval now is better than it was 2 moves ago, right? Our last move, then we are improving. Why is this important? Well, because it's going to modify all of the margins we have inside of the rest of our search. We are going to want to be more conservative with pruning if we know that we have improved since our last, if we have been improving as a side, right? If white is improving, we want to be more conservative, because we are trying to find the best possible continuation. Okay, so that's what improving is. It works fantastic. How do I know it works fantastic? Because my SPSA always inflates all of the margins that it affects. It works great. Highly recommend you do it. Now, I use the stack to retrieve this, but if you don't have a stack, how I recommend you do this is how I used to do it, which I literally used my eval hash to do this, right? Is that I would literally just go through, I would go, two keys behind in the key history, right, in the key stack, and then I would just simply search for the eval hash for that key, and then just compare against that. It's the exact same thing, okay? So, but I do cache it on the stack, right, for the eval, okay? Okay, so reverse futility pruning. We're getting to pre-moves loop pruning now. What does any of this mean? Okay, so to get into pruning and reductions and all of this sort of thing, I just want to give a refresher, right? The higher the depth, the less we want to prune, okay? Very important when we get into talking about this. What is pruning? Pruning means we are killing this current node. We are killing this current node. We are returning out early before even looking at moves in these cases, right? And then moves loop pruning is where we are already in the moves loop and we are looking at each move and then, returning out. Okay, so what's going on here? Well, we have RFP depth. You don't have to do this. You can just this should really just be sp.rfp depth. Okay, I'm just lazy. So what is this? What is reverse futility pruning? It's the reverse of futility pruning. It's important to know what futility pruning is first. Futility pruning is a moves loop pruning that looks at if we are in a node that is futile, to be in. That means underneath alpha, of course. We are so bad, we are underneath alpha. Naturally, reverse futility pruning is the opposite of that. We are above beta. We are too good, right? So that's what reverse futility pruning is. I only do these prunes usually in non-PV nodes. Other engines may do it in different ways, but it is typically a good idea to only do it in non-PV nodes. When I say non-PV node, I'm talking about expected PV node, and why that's important is because it's about our intent with the node. If we are in an expected PV node, we want to search it fully, okay? Because it is typically something that we already assume is going to be interesting. And we need precision with, okay? So you want to, right? And so we're going to get into how we create PV nodes once I get, into us actually recursively calling search, right? So how do we calculate this? So if our depth is less than RFP depth, RFP is typically done from anywhere between the top depth of it is anywhere between 3 and 7. Okay, it's a large range, but that's typically the depths that it's done at. Okay, mine I believe is 4 right now. It used to be 5 and 6. Now, why is it 4 now? Because SPSA has optimized my margins to be incredibly low currently in the SPSA run I'm in right now. Is my RFP mul is something like 38 and my base is something really low like 2. And so to compensate for that, the depth has gone down. This is what you will discover when tuning, but before you even get into tuning, I highly recommend you tune all this stuff by hand. Just move the values around. This is important for everything we're going to talk about in search. Very important. This is the most important advice I'm going to give you. Try the values out yourself. Go look at other chess programs. See what they set. And then try those values out. Move them around yourself. Play games against yourself and other engines. Take positions where your engine blundered. Okay? And then look through and try to find which values help you find the right move. It's this is kind of like the rite of passage. You have to do this before you tune, because it's shaping it to your own engine, right? So highly recommend you do that and treat all of the pruning stuff with that mentality, because no other engine is going to have the values for your engine. It's just not going to happen, okay? So if we're not in check, we do this. So why, if we're not in check, are we not pruning? Well, because of pseudo legality, okay? So like we said earlier, we need to play moves to know if they are legal. So if we are in check, we need to know if we have any legal moves. Now, we could implement some legality checks. I've seen in many other engines that I really like, that they have these sorts of am I checkmated before any pruning, right? it's typically an expensive thing to do, or they have already perfect legality inside of their engine. Stockfish doesn't even do this, right? And so it's up to you how you want to do it, but this is the reason why. You're going to see is not in check anywhere where we are pruning the node, because we need to know if we are checkmated. And the only way to find that out is to generate the moves and go through the moves list, okay? So that's why that's there. Now, the excluded move, once again, singular extensions, we'll get into it. Okay, the stand is less than 2,000. Why this? Well, we are checking if we are below known win, okay? This is a common sort of a thing with chess engines is below known win. 2,000 is a usual value for this. Now, why? Because you typically don't want to prune known wins as, you know, it being too good, right? Or it being too bad, or, you know, whatever. Because we are probably trying to end the game, you know? So that's also the case. So what is the math here? What is the math here? So of course we're checking if we are so high above beta. So we are taking our static evaluation and we are subtracting some amount. Now how do we calculate the amount? We multiply some value times our depth. Okay? So what this means is that our margin is going to be bigger when we are higher depth. Okay? Now how this works out mathematically, right? So if you are closer to the leaves, once again, we want to prune more, okay? So that means having a smaller margin, right? Having a smaller margin usually makes us prune more, because we are saying if we are above beta by how much, okay? So if we have a smaller margin, that means that just above this much we are pruning, okay? If we have a larger margin, we have to be very, very high, right? And so this multiplier times depth is what assures that at higher depths we don't over prune, because once again, pruning at higher depths is risky because you delete a lot of the search tree underneath it, right? When you prune only the leaves, it's less risky. Okay, so and then we have a base value. Most of these margin calculations are going to follow this multiply times the depth, add some sort of constant base, and then the improving that we just talked about. A lot of these are going to multiply something times improving. This means that if improving, then you add that amount, okay? Improving is only 0 or 1, it's a Boolean, okay? So it would be the same as writing a conditional, okay? So that's that. I will go through some values, I think, when we get to the end of search. I may show off my most recent SPSA values, just to show what they might look like, okay? Razoring. What is razoring? Razoring is futility pruning. Okay, well, it's not, but it is very similar. It's tied to futility pruning, okay? So once again, not PV node, okay? Not in check again. And so what is the calculation here? You know, and of course we are checking if we're under razoring depth. Razoring depth is usually done from depths 1 to 3, okay? I do it only at depth 1 right now. Why is that? It's just the value that I've found works best in my engine right now. I used to do it up to depth 3 though, but now I find that futility pruning just does what razoring would have done. So what is razoring? Okay, well, razoring is futility pruning, but pre-moves loop. Okay, so we are still, it's about being below alpha, okay, but it's more risky than futility pruning. Why is it? Well, futility pruning, okay, futility pruning says that yes, our node is really, really bad, but we still should check the captures and the noisy moves, the promotions and things like this, just because it could you know, bring us above, right? Or it could, you know, have some material change that, you know, saves an otherwise completely, you know, bad node, right? So futility pruning is saying we aren't completely getting rid of the node, we are still entering into moves loop and checking these moves, the captures and the promotions that may actually change things for our node. Razoring is saying we are so bad that we are getting rid of it, getting rid of the node. So it's more risky because you aren't checking any moves. That's the difference between futility pruning and razoring. So the conditions here are the same as RFP, right? So it's our stand plus a value because we're checking the margin upwards, right? So we have, once again, the base and the multiplier times depth, right? Bigger margin is higher, and improving times the improving, and if we're still less than alpha. Okay, and we are checking if our alpha is not mate. Why is that? Because if we're lower than a mate score, it's kind of, it's like, to me, what that means is like if we're lower, if our alpha that we're checking against is a mate score, then we want to keep the node because we're mating, so yeah, or we're getting mated as well. So yeah, when you're checking against bounds, it's important to check some things. And also we have this alpha known win thing again here. So I think that the reason behind this is exactly the same as the RFP known win. It's very common. You'll also see it in the NMP that I'm about to talk about, for people to put this in. But yeah, so I think it's just good to not, because you miss tactics, right? That are when you're doing really good, when you start pruning things like this, like mating sequences and stuff. So that's why that's there. So what are we doing here? Like, why don't we just get rid of the node? Why are we dropping into QSearch? What is the null window? Okay, so this is a verification search. Okay, very similar to what we're going to be doing later on in ProbCut and in NMP. Okay, this is what razoring is based on. Okay, is to verify it using QSearch. Okay, Stockfish doesn't do it this way though. Right now, as far as I can tell, Stockfish actually searches this with a full window, and then just returns the value. It doesn't validate if it's less than alpha. The reasoning is probably that their margin is huge, by the way. The reasoning is probably that it's expensive to drop into Q with a full window already, and so they're just basically trading that off because you don't want to check against alpha, because if you are now above alpha, then you've just wasted a lot of time, right? And so there's a trade-off there, but the historic implementation of it is this, right? You can also go with a full window, but the idea behind a null window in general is to find if we can get above it, to find if we exceed it. That's what a null window is used for. And you're going to see the same thing happen in ProbCut, where we use a null window around an R beta, a beta, right? That sort of thing is it's the same thing. So that's what this alpha plus 1 is. It is a null window. It is non-PV, which is exactly the flag that we pass down, non-PV. This goes back to where we detect if it's an expected PV node. This, of course, would not be an expected PV node because it's a null window. Alpha equals beta minus 1, as we were talking about earlier. Okay, so we verify if we are still less than alpha after we drop into Q, then we return. Okay, so that's razoring. Okay, so NMP. What is NMP? So my implementation for NMP has really changed. Okay, I have added on more of the Stockfish verification search stuff, honestly, recently, and I haven't really tested a lot of it. And so I'm just going to talk about what I understand about NMP, and just give recommendations based on that, because the verification search stuff, I haven't verified it myself, but I know that other engines use this sort of thing. So what is null move pruning? Null move pruning is very similar to reverse futility pruning, where we were doing so good, right? Null move pruning is, it needs us to be above beta already, okay? The idea is that on the null move observation, okay, that it's the observation that if we don't make a move at all, then that has to be a bad thing, okay? It has to be bad for us. Now, it's not always a bad thing. So null move pruning isn't 100% safe, but chess engines are not about being 100% safe. So the idea is we are above beta and we don't make a move. We make a null move. We don't make a move at all. And then the enemy plays a move. Are we still doing good? You know, so that's what we are measuring. That no move has to be always bad. You know, and it has to bring us below, and so that's what null move pruning is about. Okay, so everybody does it differently, but the common stuff is all the same. So null move pruning, I've seen people do it to a capped depth. I've seen people do it a cap at depth 9. You know, with a verification search, I don't cap it. Okay. I do it very common. I'm pretty sure everybody does it at depth 2+. So that's what you're seeing here. And if we aren't in check, okay, once again, what is this game phase is greater than 4? What is the purpose behind this? Okay, so I don't have a Zwag-Zang checking routine. I really should make one, but that's what this is. In late game scenarios where the pieces are just pawns and kings, I believe that this is the definition of Zwag-Zang or Zug-Zang. So what? Anyway, you sometimes in these scenarios not making a move at all is often good, and so this obviously breaks the entire null move assumption. And so you have to check that there is sufficient material on the board. I do this based on phase, because pawns don't count towards phase. So me saying, you know, a safe margin of 4 gives us enough material on the board to be safe. Okay, so there's that. Now, what does not PV node mean? What am I talking about? You already know what a not PV node is. I'm sorry, I just blacked out. Now, why all of these? I probably don't need all of these, but it's important, I think. I put them here for safety, because when my engine was in its infancy, I ran into some problems with mating sequences with null move pruning. So I have that here for that reason. Okay, so if stand is greater than or equal to beta, so this is what I was talking about. We are above beta or static evaluation. Okay. Once again, excluded move is 0. We don't prune when we are doing an SE thing, and not skip null move. I skip null move, I believe. There is a case where I flip that flag elsewhere, and that is simply a variable where I pass it into the recursive search when I want to skip null move. I believe I skip it during probcut. I saw it in somebody else's code base, and then I was like, oh, that seems like a good idea. Okay, and stack -1 current move doesn't equal 0. I'm saying if the last ply wasn't a null move, then we can prune. Then we can null move prune. Okay, so I don't allow 2 null move prunes in a row. I highly recommend you also do something like this. Now, what is this ply greater than or equal to the min ply and the side to move doesn't equal the NMP side? Okay, so the side to move not equaling the NMP side, I believe, if I remember correctly, that you don't want to, when you're verification search, you want to make sure that you aren't doing a NMP from the side that we are verifying. And then the NMP min ply is us. I think we're just like shifting it in the verification search so that we make sure that we don't NMP at the same ply that we already NMP'd at. Okay, now what is verification search? It's when we're at high depths, we want to make sure, it's us saying, okay, well, we want to make sure that our NMP is solid right now, so that's where we do another search. If we get back, oh yeah, we should prune, we do another search to make sure. Okay, so now what is this R? R is the reduction. Now it's hard to talk about reductions when we haven't even talked about late move reductions, okay? But what are reductions? Reduction is where we are reducing our depth in the child node past just 1, right? Typically, what you would see, right, when you're going down the search tree, you would be going, okay, well, our depth is -1 because we go deeper, -1 till we reach 0. But this doesn't happen in a chess engine, in a strong chess engine. You have to reduce more based on how strong the node is, and the depth and certain heuristics that we're going to get into in a second. But okay, so I do it now based on this slope formula. I had it. Probably you should just have it. I had it in if depth greater than or equal to 2, then R was equal to whatever, R equals 1, and then if it's like 4, then this is like 2, and then this is like 3 when this is like 8, or I had it basically like that. Okay, so yeah, that could be something that you do. Tuning this is kind of a pain. But yeah, this is kind of the way it's done. And what is this stand minus beta divided by 200? I've seen this in multiple chess engines. So what this is how high we are above beta, right? We are reducing more if we're high above beta. Okay, very simple. We're saying that if we're high above beta, we're more certain that we can get away with it. And so it's the same thing with improving. Okay, yeah. Actually, yeah, this is super interesting. Because typically, I've had that in there for so long, but yeah, it's pretty interesting because I said earlier, our improving margins make things larger, and so us saying that we are reducing more if we're improving is interesting, but I've seen that in a couple other engines, and so yeah, that's interesting. Anyway, so how do we verify a null move, Brone? Okay, so here's what we do. We make a null move, and to do so, we of course have to do all of the hash key updating for our position. So we change our side to move. We do the turn random, right? We do the en passant thing, right? Where if the polyglot en passant thing, where if we had a pawn there, right? You remember. So we do that. Most other engines will have this abstracted away in a make null move function, but I have it just there. And this is what you're going to do, right, is you do a null window around beta, like we already discussed. And yeah, that's it. And then if you get a score back, right, you're going to get a score back. And if that score is still greater than beta, then we can prune it. So that's what it is, right? Is we make a null move, we see afterwards if we're still above beta, because null move should always be worse. Okay, so believe it or not, you think that this would prune a lot, but it does prune quite a bit, but it isn't the most ridiculous. So once again, you're going to want to undo the null move. Okay, this is how we undo it. We just simply XOR the keys again. Okay, and then down here is the verification search. Okay, so this is very simple. Now we aren't switching the turn. Okay, that's the key thing about a verification search. We are not switching the turn. It's the same thing that we're going to talk about later with how we do our singular extensions. Okay, where we are not going to actually play a move, and we're just going to research at a different depth. We're researching the same ply at a different depth, right? And so we reduce by this amount, okay, and we go down to that depth, and we aren't playing a move, right? And it's once again with the null window around beta. And the formula for this, I have to tune this myself, but the formula for this is just less, is more forgiving. Is kind of the point. And also that there isn't a null move involved at all, right? Is that we're basically searching our part of the tree at a reduced depth to see if we still clear beta, as well as the null score clearing beta. Okay, so that's that. Okay, so this is the pre-moves loop pruning. Okay, so this is when I have already generated my moves. So this is the move picker, this is generating the moves, and I init my move picker. Okay, and this is going to be the first thing, is prob cut. Okay, what is prob cut? Well, prob cut is that we are probably cutting. Basically it's very similar to all the beta pruning, like null move pruning and reverse futility pruning. Okay, so we're basically creating, it's kind of like reverse futility pruning, except we are checking our moves and how they are going to cut, and then creating a null window around that margin. Okay, and then saying for those moves that we are going to try, are we probably going, is this probably a cut node? That's what prob cut is. This is probably a cut node. That you can think of it like that. So what are the conditions? So this is typically done anywhere from depth 5, 6, 7, something like this. I've also seen it done at depth 4. SPSA has optimized it to depth 3 for me. Okay, so we also gate it around Zwugzang as well here, and just like razoring, we gate it around the mating score, right? We don't want the bound that we're checking against to be a mating score. Okay, now, so what is this? What is it? So we are creating R beta, which is beta plus a base minus the improving. Once again, the improving thing is quite interesting. I think it's interesting because some margins we increase based on improving, but here we actually scale the margin back based on improving. And I think that it may have something to do with how certain we are about the node, and also, no, this is exactly what it is, because it's about momentum. I think, now thinking about it, it probably has to do with momentum, right? In terms of us reaching beta, right? If we are improving, we are reaching closer and closer to upper bounds, right? And so I think it's probably has something to do with that. So that's why we're scaling it back by improving. I think is that we are certain that we are reaching further and further. Okay, this is very similar to how other engines do it. Okay, I saw this line specifically in Stockfish. This checking more if it's a cut node is quite brilliant. Okay, so why do we do this if it's a cut node, if it's an expected cut node? Well, because we probably are going to cut this, so we prob cut. So we want to check a few more moves because this is probably going to be a cut node anyway, right? It has a greater chance for prob cut to succeed. Prob cut is a kind of expensive thing. Okay, so we are going through the first moves in the moves loop, and that's what this is. Okay, if our LM legal moves are greater than 3 or 5, or we have entered into the quiets, right? So I only do captures and TT move. Okay, so we are only checking the first few moves, because if you check too many, then it's expensive. Okay, so you check the first few moves and you make them. Okay. You of course are going to set the pointer in. You do the same thing when we do the null move. Okay, so you get down here, you make your move, and you recursively call. You start with QSearch. Okay, this is typically the thing is you do QSearch and then you do a verification search. Now, why QSearch before the verification search? Because the chances are you probably aren't going to pass this, and QSearch is a lot less expensive than the verification. Okay, so once again, the null window around beta, because we're checking that bound. We're checking the, if we can exceed that bound. Okay, and so you just undo, and if the verification search succeeds, then you just return that value that you got from it. Very, very simple. So once again, all it is us saying, hey, are we going to fail high? You know, like if we are going to fail high, we're probably going to do so in the first few moves. So that's why, because with good move ordering, you know, prob cut relies on good move ordering, because the first few moves, if you're gonna fail high, are probably gonna be in the first few moves, and so that's the basis of what this is on. So internal iterative deepening. Okay, so if we don't have a transposition table move, okay, we have a lot less power around the certainty of, you know, how good our search is going to be for this node, because we first of all, if we don't have a TT move, that automatically means that we are in upper bound. Okay, so that's the understanding you have to come with here, is that if we don't have a TT move and we didn't get a TT move out of the TT, we either don't have an entry or we had an upper bound, right, without a move. So coming with that in mind, we probably want to get that stuff, right, instead of searching this node fully, because we're gonna have to search a lot of moves, you know, to get a good move. So that's what this is it's saying we are going to reduce our depth so that we can exit out faster, so that we get a TT move, until we get a TT move. So that is basically what's happening in IID, is that we are reducing our depth because this node is less strong. Okay, people do it different ways. Okay, most people have a lot of different, you know, I've seen a ton of different, you know, permutations of it. Now I simply just do that. I might touch it later, but I've seen some old code where they actually straight up do a search at a low depth to find a TT move, or they have some math with the bounds to find out if it's good enough to not. But I think it's pretty common to just do the depth -1 thing. Anyway, some engines as well do the IID thing up here. up here actually. And so that's something you can try out. I've seen engines do it actually when they fetch from the TT. I'm not really sure how that's probably pretty aggressive, because that directly feeds into pruning and stuff. So it's something that you can test for sure. It's something you can test for sure. Okay. So now we get into the moves loop. Okay. So you can tell that from here I was like testing some of these ideas from Stockfish to optimize this sort of thing. So I init my move picker again. That means going back to what it was before. I init my ordering array and stuff. So that's what that's doing. I set my stage to pick TT move again. Why am I initting all this stuff again? Because it was tainted by prop cut, because we just prop cut it, okay? So our hash type equals upper. Our default will be upper, okay? If we raise alpha, then we will set it to exact. If we fail high above beta, then we'll set it to lower, okay? This is the typical way of doing it, but I don't even use this flag anymore, okay? I decided at the end of a node, because I verify my exacts have to be PV nodes, okay? So what are these non-quiets, quiets? What is this? These extra move arrays. Okay, so these extra move arrays are an optimization. Okay, I push moves onto those arrays since they are integers. It's easy to do so. I push onto them so that when I'm updating history, I don't have to validate which move is a capture versus which is a quiet. So that's just an optimization, okay? Because for me, I don't have that encoded in the move, okay? So it is a bit of a few extra instructions for me to decode that, okay? So once again, we're going to pick our moves. I kind of skimmed over this last time. It's very basic logic, okay? So what I'm doing is I just start with an index of -1, and then, you know, if we don't get a move back, I don't exit out, and then I keep incrementing the stage, okay? And then if we didn't get a move, then that means that we're out of moves, okay? Very simple, okay? And then, you know, this means we break out of the loop. If we didn't break out of the loop, then I have a move to play. Now, if it's the excluded move, it's excluded, so we don't play it. What is excluded move? Get to it in a sec. But yeah, so we skip over the excluded move, okay? Here I just cache the M score. I just check if this is a capture, if it get a boolean for if it's a cap or a promo. That means that it's not a non-quiet move. If it's a checking move, I have a function that checks if it causes check. Okay, and here we go. This is my extension. I only have one extension now. I used to have a few other different ones. I really like the idea of extensions. I used to have recapture extensions. I used to have pass pawn extensions. Okay, because I really liked other engines I saw do that, like Senpai and stuff, and I just could never get it. It really just slowed my search down, like really, really bad. And so now I only have one extension, okay? And all it does is, if it's a checking move and it's a PV node, or if it's a checking node and it's a positive SEE check, then I extend. Otherwise, I do not extend. Okay? So if we were going from my regular check extensions with that depth plus, the equivalent would be this. If it is checking, then extend. Okay, so that's my only extension I have right now. Now, what is new depth? New depth is going to be just depth plus our extension. Okay, that is going to be what we are subtracting our reduction from. Okay. So this is late move reductions. Now, what is late move reductions? Late move reductions is kind of the most important single part of search. It relies on good move ordering, okay? the further a move is inside of our move array, the more we are betting it's a bad move, because we have all of this good move ordering that we talked about with all of this history and all of this stuff. So we are going to reduce, once again, going back to this idea of reducing depth on those later moves. Okay, so how do we do this? Well, some engines do it in some ways very, you can look, there's a page on the chess programming wiki for late move reductions, and there's examples of like 5 or 6 different engines, maybe even more, of their equations for deciding reductions. My reduction formula started as if legal moves is like greater than or equal to 7, then R equals 2, and then else if depth was greater than or equal to 6, and legal moves is greater than or equal to 13, then it was like R equals depth divided by 2 or something like this. This was basically how I did it. Okay, so this is the way I would probably urge you to go about it, actually, is this more explicit stuff. Why? Because the log depth and all of this, it requires good move ordering to work. Like a smooth equation like this requires really good move ordering. Okay, so that's the difference. Many engines do it actually just this way, right? Where if it's a high depth and you're late in the list, then it's just depth divided by 2 or something like this. Okay, so what is the math behind this? This is log depth and log legal moves. Okay, so it's log times log. This is a very typical way engines do it. It is just a smooth kind of function that just goes, that takes into account depth. So the higher our depth is, the more our reduction will be, and the higher our move count is, our space in the move count is, then the higher that will be. Okay, and so we multiply that times a multiplier, and we add a base. Right now, I believe my quiet mul is about 0.6, and my base is about 0.8. Okay. So what about captures? Do you reduce captures? This is depending on your engine. For a while, it was actually a elo increase for me to reduce captures. And so I had a separate equation, a much more forgiving equation for reducing captures. Now, I don't, and I have just this one, and I remove the captures from it. But maybe one day I'll try it again. During my tuning, I found that it was optimizing this captures, the capture value to 0, and so that's why I removed it. Now, so what are these down here? This is like the most fun part about it, right? I've tried so many different things here. Like you see this bool dangerous. I was trying to, reduce reduction. So what is reducing reductions or reducing more? What is this doing? And how is this different from extensions? Okay, so this is different from extensions because extensions, at least in my way of going about things, is that I apply this extension first, right? And so it makes basically a bound, because I clamp, and I highly suggest you to clamp your reductions between the depth minus depth minus 1, or why did I say depth minus 1? Depth minus 1 and 0. Okay, so what we're saying is that we want to not hit Q from this reduction. We don't want to hit QSearch. We don't want to hit depth 0. We want to hit at least depth 1. Okay, and so me applying the extension first gives us a much slimmer, right, thing, right, where we are now saying exactly 1. If I applied my extension after, right, it would be we might be allowing depth 2, right, instead of depth 1, right, based on that extension. And so this is different than extensions, right, because we are capping it, and yeah, so and it's based off of reduction. So if we have a reduction of 1 and then we subtract 1 from it, right, we're going to cap it out. So that's the difference. So what does any of this mean? So the MP scores is simply our history score for the move. Okay, so I am just checking this. The maximum of all of my histories is 16,834, and then the way I divide my contests, it maxes out at about in 16 max. So that's about 2 times this. So depending on the history score, this ranges from -2 to +2, which means that we reduce by 2 extra, or we subtract 2 from the reduction if it's a really historically a good move. Okay, so and then if it's an expected PV node, you want to reduce less. That's pretty obvious. Okay, if we're checking or if we're in check, I also reduce less. And if it's a cut node, you want to reduce more. Now the cut node reducing more is a bit less intuitive rather than the PV node, but the idea is I think pretty sound, that we want to get rid of cut nodes obviously more than we want to get rid of PV nodes, and so this is like kind of a more modern idea with this cut node thing. Okay, so once again I clamp to new depth -2 because my reduction starts at 1. My reduction starts at 1, and then I add this R value. Okay, so my reduction starts at 1, meaning that depth -1 is the base. Okay, so that's why we cap it at -2, because it was already -1. Okay. Okay, so moves loop pruning. We're entering into the moves loop pruning. Okay, so I don't do promotions. No pruning on promotions. Too dangerous. Also, so why depth greater than 3 and greater than or equal to 3 and legal moves greater than or equal to 4? This is the values that most people do. Okay, some people, instead of doing legal moves greater than or equal to 4, they do if it isn't a TT move and it isn't a killer. It's very similar to the legal moves greater than or equal to 4 thing. It's very similar. So you can definitely play around with that. Okay, it's not set in stone. My depth when I was starting my engine was more like 4 or 5-ish, Anyway. So what's up with this? Okay, so I don't do the PV nodes. I haven't had good success with it, but I see it in other engines that they do move pruning in PV nodes. I haven't found success with it. And if it isn't a checking move, I think that those moves are too valuable. If it isn't in check, once again, because we need to validate our moves to check if we're in checkmate. Legal moves greater than 1, just that basically just asserts that we aren't doing the TT move. It also asserts that we at least search a move in a node, okay, which I think is important. Other engines don't have it because they check it afterwards, like have we searched a move throughout, but you can choose to do it either way. Okay, so, and not when we are approaching a mate score, okay, because we don't want to miss out on tactics and stuff. Okay, so what is this? This is late move pruning. It's the same thing as late move reductions, but All we're doing is we are straight up pruning the moves instead of reducing them. Okay, so what is the formula here? It is usually some number plus depth to the power of 2. And we multiply it times a value if we are improving. This means that the margin gets further if we are improving, you know. So we are pruning less if we're improving, and this value, you know, is, some engines have it at 2. I've SPSA'd it to, I think it's like 1.6 or something. So that's that. Okay. We are checking our depth is less than the LMP depth. I believe mine is at 5. I've seen it anywhere between 3 to 7. I think in Stockfish they don't have it yet. So why cap it if it's already exponential with depth? Well, because it just gets really dangerous to even prune 1 or 2 moves at really high depths. So that's why. So I highly recommend you start with it at 3. That's what I had it at. And you may be asking, so why are you pruning captures? Why is captures not here? Well, I remove is capture from all of these. Okay, I remove it because it's only for SEE. I SEE prune captures, so we'll get into that in a sec. So what is predicted depth? Predicted depth is just depth before we have gotten to singular extensions. So it is literally just the new depth minus that reduction that we just calculated. Okay, so that's what predicted depth is. I've seen it used in other engines, this predicted depth, but it is mainly used as an optimization, okay, to avoid LMR calculation before necessary. Okay, but the use case of it here is the same. Predicted depth, the idea behind it is it's the depth that we are going to after we play the move, after when we recurse through, we are going down to that depth. So the idea when we use it during this moves loop pruning, we are basically adding on to the amount of parameters, just the amount that we are reducing this. Does that make sense? That we are reducing by this much, and therefore we are going to use that as the depth margin. Okay, so my futility depth goes to about 4. Okay, you don't do it on captures, obviously, and you don't do it on promotions. Why? It was I went over this already. You know, that's futility pruning, right? The idea that a node is futile because it's so far below alpha, but we still need to check the pivotal moves, and so that's what this is doing. Technically, you could just calculate this once for the node and then just, you know, put it here, like if utility prune. But what I do here is and some other people do it, you know, a different way. I'll mention in a second. I use the history score here as well to scale by. So good moves have a higher margin, okay, to get futility pruned. And so this means that the moves themselves have some say in it. Okay, so if there are very good moves, we prune them less often. Okay, so what's the math doing here, right? Well, once again, it's just like razoring. We're adding to the static evaluation. We have the static evaluation plus the base plus the mul times the depth, you know, standard there, and then plus, for me, that's the history times a certain multiplier, and then plus an improving heuristic. Okay, we also have sometimes on this thing move count itself. I've seen in a few engines they do like plus you know, legal moves times mul, right? So that, or it's the inverse of this, right? As legal moves like minus 20 times mole. The idea is or no, it's minus, what am I talking about? It's minus legal moves times mole, right? So the idea is that you're subtracting for the further it goes into the moves loop, you're subtracting from that. So that's the idea there. Okay. It never worked for me though. I think it's super dangerous to start subtracting from a margin in general. So what is this? This is counter-hist pruning. So we already talked about contest. This is exactly that. We are using the contest values for the move that we are about to play, and then if they are both below a certain margin, then we are pruning. This has been really hard to tune. Really hard to tune. Really hard to tune. And I just want to show off how I'm uncertain about the way I've tuned this and if it's working. My optimizer has absolutely demolished the margin on this, okay? And apparently it works. But like, look at the amount of C prunes this, contest prunes is. This is 463,000. It's just such a large number for moves loop pruning, right? It is so far above the amount of futility prunes, the amount of late move prunes. It is incredibly large, and so I still am not really sure if it's implemented properly, or I know that my margins for it, that I've been getting out of SPSA are really aggressive. But anyway, so SEE pruning. SEE pruning. What is SEE pruning? Okay, so SEE pruning is just the exact same thing. So if we have a really bad SEE move, as we talked about earlier, you can go back in the video and look at the SEE stuff. Then we're going to prune it. It scales with depth. I've also seen engines do it with the predicted depth. I haven't gotten that to work. But yeah, I do this with the non-quiets versus the quiets. Okay, so what is the non-quiet is just captures, because I don't do promos, because promos once again change the material on the board. And yeah, typically I started this with, I used to have like insanely large margins on this, but nowadays the quiet margin is 40, I think, or like 35 or something, and the non-quiet is like 80, maybe even lower. It's funny how that works, because you're probably thinking like, man, that's so aggressive, but the idea is that it's only going to be that at depth 1, right? At depth 2 it gets to be much larger, right? And going up. But yeah, typically I only do this to depth 3, I believe now. I really tried to get this further up the tree, but it doesn't really seem to work. I've also seen people do quadratic depth here, right? Like depth times depth, or with a slimmer margin. All valid ideas for sure. But yeah, so that's what it is. So all of that stuff is per move pruning, right? Okay, singular extensions. What are singular extensions? Singular extensions is exactly what it sounds like. We are extending singularly on one move, on the basis of that one move. It is when we have a transposition table move that is better than all of the other moves. And when I heard that, I was like, man, that must be really hard to figure out if all the other moves are bad. Like, I mean, like, what, do you search it last? Like, how do you... Okay, so this is how you do it. what you're going to do is you're going to exclude the move. And this goes back to what I've been talking about the entire time with this excluded move thing. Okay, so this is what the excluded move is you, I set it for the stack. You can put it as an argument and pass it into the search, right? That you have an excluded move. And when you search, you're searching the same ply at a different depth. And it's basically researching not researching because you haven't searched yet, but it's pre-searching, okay, with the transposition table move excluded, okay? That's what's literally happening, right? Going back to what is happening here, okay, what is happening here with this excluded move, right? If we have an excluded move, if this move is our excluded move, we're continuing past it. That's what's happening, right? So we're searching the same ply again, okay, and calling search on the exact same ply. We aren't playing a move. We're just calling it again, going through the same exact board state without that move, okay? And we search it with a null window around this beta that we're going to calculate, and at a reduced depth, just to get a taste of like how bad all the other moves are. And if all of the moves don't go past that singular beta, right? What this is, if the score we get back with just our TT excluded, if we don't get past the singular beta, then we extend, because the premise is that TT move must be better than everything else. Now, why do we say that the TT move must be better than everything else? Well, because of the conditions that make us enter into a singular extension, right? And so I'll go through the conditions now, right? So this is typically done from anywhere from depth 6 to 8 plus, okay? It requires to have a TT entry, obviously. It requires to have a TT move, and it requires your current move to be the TT move, okay? Ply greater than or equal to 0 doesn't matter because I don't have a root. So the excluded move, once again, you don't want to chain singular extensions on top of each other. No. I mean, this is, you don't want to singularly extend on top of a singular extension, and I only do it if we haven't extended already. That's a very important part. Okay, so we only do it if our TT entry is lower, okay? I've also seen people do it with exact, okay? I don't do it on mates, okay? Don't do it on mates. Because I guess we've already extended this, in that case anyway. And then this last case is something that I've been trying to think about, like why this exists. But if I had to give a guess, it's just verifying that the TT entry was strong already. It's greater than our depth minus 3. It's greater than by some margin around our depth, because otherwise, we don't want to. The reason why if it's lower, if it's exact, what we're saying here is we don't want to do all of this work for an entry that isn't strong. That's what we're trying to say. So if our score is less than depth times the margin, this can range from 1 to 3, okay, depending on if you want more singular extensions versus less, okay. Most engines do depth times 1 nowadays, but I've seen some do depth times 2, depth times 3, okay. And so this is going to be your singular beta that's your null window, okay, that you're checking against. And the idea with it is that you want obviously stronger as your depth goes up, but you're using the TT entry score, right, as kind of your basis of truth, instead of instead of the beta itself. So that's why. And so that's why you're taking the score and then you're going lower than the score, because you're trying to see if anything can't even get past that, right? So yeah, most engines do it at depth divided by 2. Okay, that's pretty standard. And so all of that is good. And as you can see here, I have true, so I don't null move prune on singular extensions. Okay, so what is this down here? I haven't gotten this to work. It's multi-cut. Okay, so this is if you know how instead our S was less than the beta, less than this this singular beta that we made, right? Then we extend it. Well, what if it's above it, right? And what if this beta that we got is above our beta? Okay. This is basically saying that we are so good that we can cut. Okay. Basically, if our singular beta is somehow above our beta, which seems rare, right? This would mean that our TT entry score, right, is minus the depth goes above our current beta for the node. And if somehow we get a score that exceeds even that, we're basically saying that we're so good that we can cut. Okay. Haven't gotten it to work. It always seems to lose elo, but everybody has it except for me. So that's what that's about. Yeah, so that's all of the pruning and reductions and extensions and all that. Also, I want to mention here, other engines sometimes do double singular extensions, triple singular extensions. I haven't really looked into that yet, but I know that some do. Okay. And I hope that you're noticing every time we do a search, we are asserting our intention, right? Non-PV means null window. Okay. Okay, so we're finally making a move. This is the first time we've made a move in the chess engine. Well, I mean, we did it during Perft and all that. I think we're about 6 hours into the video, and this is the first move we made. Okay, we're making our first move. So what are we doing here, right? Once again, setting the contest and the cont core pointers, and so I'm going to explain what all of this means. This is related to principal variation search, PVS. Okay. So what does all this mean? So we know what our LMRs are, late move reductions are by now. So let's start from here. I think is a good way to go about, talking about, it. I've been talking a lot today. We're going to start from here. If it's not a PV node, or if it is a PV node, okay, so let's just say right here, let's just say, how do I do the, okay, and then you got to do the, there we go. If it is not a PV node, or if it is a PV node, this is implied, and the legal moves are greater than 1, okay, so this means that we always search the first move in a PV node with a full window. Okay? That's what this means. Okay? So what are these 3 different searches? What are these 3 different searches? Okay. These 2 have a null window. What is different between this one and this one? Well, it's the reduction. Okay? So this one is our new depth, once again, is just our depth plus our extension minus the reduction, okay? And then this one, right, I also was making sure, so we add new depth plus equals extension here. So I wanted to make sure that I caught that. this one has a reduction and this one doesn't, and this one has a full window. Those are the difference, right? So what are the conditions? Well, to do this null window search with only -1 depth, we are doing non-PV nodes or PV nodes where it isn't the first move. Very simple. Or if it was a reduction that we researched. Now, what is a research or a reduction? So this is the first thing. In my engine, reductions start at 1. So this means that if we have LMR applied, this reduction number will be greater than 1. And so we go into this search, okay? And this is a null window search with the depth minus the reduction, okay? So this is the reduced search. If we get a score that is greater than alpha, okay, greater than alpha meaning that it's good, meaning that it might raise alpha, meaning that it might, fail high, okay, this is important, we research, okay? So this is the other condition here, where we research. We don't research with a full window, we research at a different depth, okay? So, and then the last thing here is you're going to have this reduction equals 1. Okay, so this means that we didn't reduce here. We go into here. So to re-explain, if we have a reduction, we do a reduced search with a null window. If that score is above alpha, then we research with what everything else gets, okay, other than PV nodes where it's the first move, okay? So if it's an LMR research, if the reduction was 1, which means that we didn't reduce it, or if it's a PV node and the moves are past 1, okay, then we do the null window search at just depth -1. The only nodes that we search with a full window are PV nodes that first move in a PV node, or when our current score is greater than alpha, meaning that it's a PV node, okay, where we were past the first move and we did this null window search and we got above alpha. Okay, let me explain again. This last one, this full window search, happens when it's a PV node and it's the first move, or when it's a PV node and our previous search went above alpha. Previous search being this null window search for if it's a PV node and it's past moves greater than 1. So why all of this? Okay, so let me explain. So these null window searches, okay, once again, are the goal is to figure out if we can exceed alpha. Okay, so when it's a non-PV node, when it is a PV node, okay, and it's always the first move, we want to search it with a full window, always, guaranteed. And then afterwards, we are only searching with a full window what has proven to possibly raise alpha. Okay, that's why. So so why with PV nodes, with respect to PV nodes, is are we doing this? Why the first move? Why does the first move matter? Does it have something to do with transposition table move? So this is kind of my understanding about it, and possibly I'm wrong. It's possible that I'm wrong at some parts in this video, right? So please feel free to correct me. But from my understanding of it, like the way I think about it, is that in PV nodes we want to establish some basis of truth, okay? In PV nodes we already have a full window, meaning that our beta and alpha have some level of width, okay, to them. And so us doing our first move is a way to get that alpha to a certain point from its base value. I think that's what is happening here, to be honest, is that in PV nodes you already have a wide window, and so it makes sense to, for the first move, make sure that you have alpha at a correct base, because that's going to affect your null window that you're searching everything else with, right? So in my mind, it gives you like a certain basis of truth, maybe, for the node. Okay, so that's the way I understand it. Perhaps I'm wrong. As you can see here, we're doing the alpha beta thing. We are negating beta, negating alpha and swapping them. We are incrementing pli plus 1. We are, verifying our windows, asserting them, and all of that. And with that, we've pretty much gotten through the main search. Not quite yet, but we're through the main. This was the final boss. So all of that. There's many ways of writing this, and in engines I've seen them write it a billion different ways. It's all comes back to this idea. Okay. So down here, how do we, now that we have a score, how do we process it? Okay. If our score is greater than our score, our current score, our best score. Okay, so this score in my engine is best score, the best score for the node so far. And so if our current score is greater than that, then we just raise it to that. Don't worry about this new best, it's deprecated. Okay, and then if our pli is 0, I store PV. And the reason why is I always want to have a PV. Actually, this is not in use anymore, because pli can never be 0 anymore. So this, I don't know why this is here. Well, talking through this actually is helping me clean up my code, so that's good. So I'll get rid of that later. So within here, we are now checking, hey, since our current score was greater than our best score, did we get past alpha? And if we did, then what I do is I set this flag raised. I set it to true. I set a new TT, which is the new best move. Okay, the new TT is I get it when I raise alpha or I fail high. Okay, and then if we are greater than or equal to beta, this is a fail high. Okay, so this is what we talked about before. We are getting rid of the node. So I have this here, search data ordering successes, which is when if it was the very first move and we raised alpha or failed high, I say it's an ordering success. So just for my statistics. Now, the killers, like I explained earlier, if it isn't capture, then we want to store killers, which it's a quiet move. So that's that. It's possible that this should be, if not cap or promo, to be honest. I think I switched that from that at some point, but maybe I should have put that back. I mean, it makes sense for it to go back, to be honest, but regardless. So I break out if it's a fail high. There's a breakout. Now why not return? Because we do some work at the bottom of this function. Okay. So the fact that we break out there means that we don't hit this code. Okay, so the logic here is that we have this stuff we've raised out, we are above alpha, but we're not going to touch alpha yet. We're not going to store the PV yet because we want to check if we fail high first. And so if we fail high, then we break out, but otherwise we raised alpha. Okay, so we raise alpha here, alpha equals score, and we store the PV. Okay, and then if we didn't raise, I pass these moves onto these two different arrays. Okay, these are the arrays that I'm going to penalize for not raising alpha or failing high. Okay, so that's what I'm going to reference in a second here. So what is this piece of code right here? This is interesting. So this is for singular extensions. If our legal moves were 0 and the excluded move doesn't equal 0, this means that a move was excluded, but we didn't have any other legal moves. It's very important, okay, that we do not return a mate score because the excluded move could have been legal. Okay, we didn't check the excluded move because we continued on it. We didn't check it. If there are no other legal moves, then otherwise, without this, we would return a mate score or a stalemate score. Okay, we don't want to do that. We also don't want to leave this because our scores are initialized to negative int max. Okay, and you'd never want to return a negative int max. So this is why you set it to your lower bound. Okay, very important. So that's essential for you to understand for singular extensions. Okay, so this is our mate score. If we didn't have any legal moves and we're in check, that's the definition of a checkmate. If otherwise, it's a stalemate. Okay, I also verify no excluded move. And then down here, if there isn't an excluded move, that's the only time I add a TT entry. Excluded move, the purpose of the excluded move is to find a singular extension. It is by definition an incomplete search of the node. Okay, you do not want to be storing entries. You do not want to be going off of that incomplete data. It's important you know that. So that's why this is there. Okay, so if our score is greater than beta, once again, that's a fail high, lower. Okay, if it's a PV node and we have a new TT, what this means is that we raised. Okay, if we raised alpha and we were already in a PV node, that is my condition for exact entries. Now, other engines may just do it if we raised alpha. Okay, that's completely fine. I have found success with asserting that it is already a PV node. It just cleans up and leaves the TTs for exact entries less polluted, because exact entries are kind of dangerous. Because if you remember how we used the entries all those years ago when we were talking about that, we just return straight out. We don't verify the bounds for exact entries, right? So we trust them with a lot of certainty. So it makes sense to verify. Okay, so, and then everything else all as an upper. Okay, and then we create our TT entry. I already showed you how that works and how the replacement policy is going to depend on your engine. Okay, history. So at the end of a node, we have work to do. We update our history. We update our core hist. Okay, so what does any of this mean? This great glob of code. It isn't as complicated as it seems. It really is not. What we are doing here is if we have a new TT, that means if we raised alpha or we failed high, we want to update history. However, we don't want to just update history for the move. We want to penalize all of the moves that came before it that didn't raise alpha or fail high. Why? That's because it's kind of like correcting our move ordering. We are saying, hey, we put these moves first, but this one was better. This one was further in the list. Let's balance this out now and move this one further. So we are decreasing the history for all of those later, earlier moves that were not as good, that we found out were not as good. So this is the basis of strong history. My updates here have changed a lot from the beginning. I used to just have history updated first. I just did it on beta cutoffs. Then I did it on alpha and beta, but then I was having I didn't do capture histories back then, but I've done it in many different ways. And now the way I do it is the exact pattern of Stockfish, but I use different values for my penalties and multipliers. What this means, okay, what all of these values are, these are all individual, parameters that I've tuned. So this is the capture bonuses, and this is the capture penalties, and then these are the quiet bonuses, and then these are the quiet penalties, okay? The idea for different values for penalties versus bonuses was given to me. I read Yukari's code base, and they had similar but different values for how they do penalties and how they do bonuses. And I like the idea. I like the idea of penalties being weighed a little bit less than the bonuses. And as far as I've done my tuning, it seems like that's just true. And so I find the idea neat. Now, what is this extra code here with this beta bonus? Well, it's the idea that in general, a move that failed high is more valuable than just a move that raised alpha. Because, that's kind of our goal, mainly in a chess engine, is to fail high so that we can get out of nodes faster. And so that's just a little bonus. I think it's only 30, while everything else is like in the 150-ish range. I also have seen engines do quadratic depth for this, means like depth times some value, and that seems to work for them as well. But I've found that this works for me. And by explaining the Stockfish, a pattern here, what do I exactly mean by that? What I mean by this is only I'm trying to, like, my brain, this video is like 6 hours, so the thing is, what they do is very interesting here. So they penalize captures. This is very interesting what they do here. They penalize captures regardless of if the best move is a capture or not. The idea behind that is it's just simply a speed optimization, right? So the idea behind it is if the move is a quiet, then that quiets always come before captures. So therefore, you always are going to penalize all the captures. If the move is a capture, then you're obviously just going to penalize all the captures anyway. So by putting it outside of here, it's the same. It's just a speed optimization, but it's a neat way of thinking about it, right? That you always are going to be penalizing captures because captures always come first. So that's what this is at the bottom here. This is just the penalization for the captures, and then this is the bonus. If it's a capture, if it's a non-quiet move, this is the bonus, and then if it's a quiet as the best move, then this is the bonus, and then these are the penalties for the quiets. Okay. it's just logical. There's no actual sort of difference between, you know, just putting it like if we did this, for example, it would be exactly the same thing. Because if the best move is a capture, right, then Q count, quiet count would be 0 anyway, because we didn't search any quiets before captures. So it's just a logical thing. I think it's just a really neat kind of way of going about it. However, yeah, so that's the idea, and that's what we pushed onto those arrays earlier, the non-quiets versus the quiets, push them onto arrays, so that now we know the quiet count is all the quiets that we need to penalize here, and the new one that we don't. And it's the same reason why here I do not raised. You don't want the best move to be on that array, right? So if it raises, you don't. Right? Okay, so that's that. At the end here is going to be core hist, corrective history. Oh yeah, how do we update history? That's a good thing to mention. So let's just go to this, since capture history is basically just quiet history but less. This is the gravity formula, okay? Pretty much every engine does it this way right now that I can think of, that I've read the code of recently. The gravity formula is it is kind of like what it sounds like. It is asymptotically reaching a maximum, okay, like you know. And so that's what this is doing, right? We are taking the current value of the history and we are multiplying it times the bonus, and then we are, you know, dividing that by the maximum, and then subtracting this from the bonus, right? And then you add that to it. Mathematically, I'm not really sure how it works out, but that's basically how it works out, right? Is that you reach that maximum kind of smoothly, and that's just the formula there. So this is what I'm doing. Like, I'm taking a pointer to where it is in the history. We're simply taking the value of that pointer by dereferencing it, multiplying it times the absolute value of the bonus, and then it's the bonus minus that. I'm a bit too dumb to do math like that, so you're just gonna have to take my word for it that's how that works. Okay, corrective history. So I went through this before today, and I wrote this very comment, okay? And by now in the video, my brain is kind of like a sandwich. It's ready to be eaten. It's very mushy. But so what are the conditions? I already talked about corrective history near the beginning of the video. Corrective history is basically, we have the static evaluation at the beginning of a node, okay, and then we have the score when we're exiting a node, and we're finding the difference between them, okay, and then we're basically putting that into a table and saying, hey, we were off by this much when these certain features were on the board, right? And then it's saying, okay, so when we evaluate the next time, we can take that corrective value and evaluate with it, so that we can correct our evaluation, right? And that's why it's corrective history. So the conditions for when we update it aren't exactly intuitive, and I was trying to really like figure out why before I came in here and made a fool of myself, okay? But everybody does it basically with the same conditions, okay? So it's if we aren't in check, if it isn't a capture or a promo, and if the hash type was exact, okay? And once again, hash type exact means PV node for me. Okay? So, or if it's hash type exact or these conditions, and this is what I was trying to figure out, right? So it's if the score for our node is greater than beta, meaning we are failing high, and that score is greater than the static evaluation. This or if it's the score is less than alpha, and our score is less than our static evaluation. So what this is in my mind, from what I think about, is it kind of is like momentum and direction, right? We're seeing if our score went up from our static evaluation, then it has to be a fail high. We have to kind of like verify this bounds. It's like very similar to how we're using the transposition table bounds, right? If the score is less than the stand, then we have to be failing low. Well, in an all node, so the idea is that, right? I think that's what it means to me in my mind. I may be wrong. This is one of these things. I've got a few of these kind of things where I'm still a bit confused on, even with the implementation in my own engine. And this is one of them. But I've tried to understand it by reading all the code and stuff. But pretty much everybody uses the exact same conditions, these conditions. So that was my kind of trying to give some insight into why it's the case. And so this is the formula to do so. So this is another thing where I'm a bit, confused on it. I use the grain and the weight formula. You can find this in a few different engines. Also on the chess programming wiki. I first did my implementation from looking at the Yukari implementation of this, which was, very similar to what it is now. But basically, there are two kind of ways of going about these things. I think some people do it the gravity way, and I currently do it the Corhis way, the grain way. And what is the grain and the weight? Well, I'm not really 100% sure. It is scaled with depth, once again. That's what the weight is in this sort of value. It's multiplied times this grain constant that is then divided out on the other end. And the diff, this is going through this formula, right? So it's the weight, which is our depth, right, times the grain, which is divided out later, times the diff, which is, once again, the score minus the static evaluation. So the difference between the end of the node to the start of the node. So that's what this D variable is, okay? And this is what is getting basically added on to it. And in C weight is this weight minus our current weight, okay? So that's what we're multiplying the current value by, and then we add D onto it, which is our new contribution, and then we divide it by the weight again. The mathematical kind of result of this is that we are scaling back our contribution by this by the difference between this weight variable and our current weight, that's by our depth, and then we are adding a new contribution and then dividing both of these together by the weight. Okay, so this is how we're kind of adding on to the current value that is inside of the table. So what are all the different types of Corhis that I have? I've got a lot. I've got a lot because I really like the idea. I think it's like such a sick idea, to be honest. And so I've really tried to tune all of it. And so I have, this is pawns, okay, which is just my piece key for pawns, okay. This is non-pawns, which is just my piece key for my non-pawn hash key, okay. If, you can go back to my my make and undo move and see how my updates for all of these keys work, okay. We have the material key for all of the material on the board, the piece counts, and then we have king and minor and king and major, okay, king, queen, rook, and king, bishop, knight, okay. So this is just the piece keys for all of these things, Zord. These are particularly potent and cool, and I highly suggest you use them. I think that they're super neat. The idea behind them is to bolster king safety and to find these kind of patterns. I think it's brilliant. I think it's brilliant. This is one of the things in a chess engine that I was so stoked when I learned about this and what this is doing. And then the last one is super fun, which I don't see being used very much at all, really, in anybody's engine nowadays, is contest chorist, which is, we're doing the same thing here as in contest, but in chorist we are, once again, this is ply -2, using the CR, which is the core cont his pointer that we have, that I showed. You can find this up here when I right here I set this right next to the contest pointer, right? It's just an identical table, separate table, but identical, and we store it in there. And it's the exact same thing. It's just a bit more complicated because we have to keep track of the moved piece inside of the stack, which is what I put in the stack, is I put in the moved piece. Why? Because we don't know that piece later, because so you've got to kind of think about it weirdly, like we're thinking the stack -1 is above us. That is what we are correcting. The reason why we're going stack -1 is because if you think about it, it's kind of hard to understand. It was hard for me to understand. I thought that the code was wrong that I was reading, but no, it's right. So if you think about this, when we enter into a node and we're going to evaluate it, we are evaluating from what was just ply -1. You get what I'm saying? So this is us realizing that that is kind of where our evaluation is, right? Our static evaluation that we're basing our core hist off of is that stack -1, right? Is based off of that. So that's why you have to keep track of the moved piece, because it might not even be there. So at least I think that my implementation is right here. I referenced an old pull request to and went around in the code and tried to poke around to figure out what was happening, and it seems to work. So it seems to work. Okay, so that's all of core hist and all of the main search. And so what about QSearch? We go through our recursive search all the way to the bottom, and then we hit QSearch. And what is in QSearch? Okay, well, QSearch, once again, is us playing out all of the captures till we reach a quiet position to have some stability to evaluate. Once again, I do it's the same thing here with the node type, okay, inferring. And once again, I have this assertion here that makes sure that my PV nodes are full windows. Okay. So, what? Okay. I gotta lock in, Okay. So if our ply once again is greater, then we want to exit out early. So now we get into TT entry in QSearch. It's the exact same thing, or at least I deal with it the exact same way, except you don't verify depth. Now, other engines might do some verification with depth. I've seen in Stockfish that they do some verification with if it's within their checks or not. However, I have never found any success with any of that, and yeah, I mean, it's up to you if you want to try that stuff out. But it's kind of the cool thing about QSearch that depth doesn't really exist down here. Like, it no longer really exists because QSearch is so noisy because there's no basis of truth for anything, because we no longer are checking every move, and so it doesn't matter if something is depth -10 versus depth -20, because we missed 20,000 moves to get there, so yeah, that's what I have to say about it. Stand pat. Okay, so what is a stand pat? How do we exit out? So stand pat is we are only exiting out of recursion once our static eval is greater than or equal to beta. Okay, so I don't really, I mean, this is basically, it goes back to the whole fail high concept, right? I think you just need to fail high at some point to exit out, to get all the way back up, and it's the only safe way, the only sound way to get all the way back up. So that's why that exists. So now, how do we know if it's safe? Well, for me, I only do it if we aren't in check. Okay, that's also what the reference code on CPW is going to tell you, is that when you're in check, it's not a safe position. However, I've seen many engines that exit out of QSearch regardless. Okay, and I've seen many engines not do checks in QSearch, not do evasions in QSearch. It's completely up to you and your whatever you want to do. My engine for a very long time only did captures, and before that I did checks all the way through QSearch. I did checks all the way through QSearch, and then I deleted them completely and only did captures and just returned out when we were greater than or equal to beta. And then later I kind of was like, I looked at other people's code bases, and then I realized this, and then I was like, let's try this out. And then I implemented checks again. I was like, wow, my search is so slow. You'll be surprised. QSearch can blow up in terms of nodes. So especially in specific positions, you'll find them, and your engine will just stop, and it'll just stop going, and then maybe like 10 seconds later it'll come back with like 10 billion nodes or something, So when you add checks into the mix, and then you stop getting out at a fast point, that can be pretty dangerous. But it does stabilize your search, right? Because the whole purpose of QSearch is to find a point where you can safely evaluate. And so by definition, if you're on check, it's really not sound to evaluate. Are arguments that modern probably evaluations can deal with this horizon issue, but I don't know. Well, whatever, it's up to you. I'm just telling you how I now go about things. So then I only stand pat when we aren't in check. And when we are in check, I generate all moves, not just captures. and not just checks, because you need to check if you're in checkmate. This is also something that is interesting, because when I first did my QSearch, I did not check for checkmate. Or I did at first, and it made my engine so slow, and then I deleted it completely. I remember when my engine was in its infancy, it would miss mating sequences and stuff like this, and I blamed it on QSearch. I was like, well, it's not seeing things because I don't check for mate in QSearch. And then I added that, and I was like, well, now I only search like 2 plies less, because of how expensive it is. Because if you think about it, right, if you have to check every move, it just slows your engine down so much, especially when you spend a lot of time in QSearch actually in engine. So searching every move in QSearch is just so slow. And so the ability to simply say, okay, if we are in check, we're just going to generate all the moves and then check them all in that case, and instead of just doing it after the moves loop and going back and generating all and checking them all. That's what I did, right? Is that I would only generate captures, and then at the end of here, right, if I was like, oh, if we are in check and we didn't have any legal moves inside of those captures, then I would generate all the moves and then iterate those and then find if I was in checkmate. That is how I used to do it. I highly recommend that if you want to detect checkmate in QSearch, that you simply do it the way that I do it now. It is to just generate all the moves once if you're in check. I think once you start optimizing things and stuff, it makes your search a bit stable. Okay, so all that explaining. If our best score is greater than alpha, we raise alpha to the best score. Best score being our static evaluation. This part is interesting. I'm not really sure about this. I think it's interesting because we don't do this in like regular search where we move the bounds, pre moves loop, and so I don't really get this at all. But this is kind of one of those things that's just like set in stone that everybody does, and this is what they call a stand pat, right? And yeah, it's interesting. I guess, I think it's probably because QSearch is so noisy that you want to keep bounds that mean something, so that eventually you do fail high. Because if you don't keep updating the bounds with stand pat, like if you don't keep raising alpha to a certain point, then you're never going to fail high in child nodes. I think so. That's probably why that's the case. Is you're raising it to alpha so that as soon as you enter into the move loop, if the child is going to fail high, and early return out. I think it's just speed optimization sort of thing. But yeah. So this futility stand just takes our eval and then adds a margin to it that I've tuned. Okay. So like I said right here, when I generate moves in QSearch, if I'm in check, I generate all the moves. Otherwise, I generate the non-quiet moves, captures and checks. And checks are only done to a certain depth, which is -1. Okay, so that means 2 plies into QSearch. I generate checks because I start at 0. So there's that. If you're going to generate checks in QSearch, then only generate it for a few plies, I think. Past that, it just is incredible. It slows you down a lot, even just this. So it's also just completely optional to do it. I would almost recommend, like, if your engine is kind of early on, don't do that, because it slows you down a lot if you don't have speed elsewhere. Okay, so so here I validate the checking moves. Okay, so I have this boolean is checking, or check if a move is checking, because I only have kind of a soft check inside of my movement generation. I only have like this soft, is it going to check the king, basically, and so here I validate it with a more serious function that looks at that looks at all the edge cases, and like the en passant case and the discovered check and all of that. And so that's why I have this additional check here, where we go if it is a capture, if it is checking, or if we are in check. Now, why if we are in check? Because once again, we need to finish the moves loop if we are in check to check for checkmate. Delta pruning. What is delta pruning? Delta pruning is it's basically futility pruning for captures. Okay, so we are underneath alpha. I only do this in non-PV nodes when we're not in check. We're not checking. I don't do any pruning of checking moves currently, and always you don't want to do the transposition table move, and you don't want to do promotions either, because delta and SEE promotions, they by definition change the material state of the board. So now what is delta pruning? Delta pruning is just futility pruning, but we're adding the value of your captured piece. So you check you have the static evaluation plus a certain margin, is what you saw earlier, and then you're adding the value of the captured piece, and then you're seeing if you're still under alpha, and if you are, then you prune the move. And that's exactly what I did here. And if it's en passant, right, there isn't a piece at that square for us to reference, and so I just add the value of a pawn instead. So there's that. SE pruning, pretty much the same exact conditions as delta, and I just use the margin. It's exactly the same as it is in the main search. Now I want to also make a caveat here with all of the QSearch pruning. QSearch pruning is really the last thing you should add to your engine, okay, in my opinion, in terms of like all of your search stuff and heuristics. QSearch pruning kind of depends on everything else to work. QSearch is incredibly noisy and dangerous. It's taken me a long time to even get SE pruning working at low margins, delta pruning working at very low margins. So I do, instead of like banging your head against a wall asking like why doesn't QSearch pruning work for me, I would recommend you instead invest time into getting your frontier pruning, your frontier node pruning, as in like depths 1, 2, and 3 working, because that will inherently reduce the amount of Q nodes as you get rid of the leaves there, and well, not leaves, but the pre-leaves, So yeah, that's what I recommend. I have this as well, and this was taken from this old pull request where I really did like this idea of it. Or maybe it was a fork of Stockfish that was super old. And so the idea behind this is it prunes non-dangerous checks that are some large margin under beta. And I like this idea a lot. Probably make the search faster, but it was losing me elo, and it's really hard to tune. The point of it is you calculate kind of a dangerous check, and obviously contact checks are dangerous, but checks that forks and checks with high SEE are dangerous, and checks where the king doesn't have any escape squares were dangerous. And I can't think of any engine that has something like this now, but I think that this was a really nice idea, and I liked it a lot, and I've been trying to make it work, and so hopefully I do get it to work, someday. But there is that. Okay, so now this is like just basically the baby version of the move loop in the regular search, right? We make our move. If it's legal, we set up our pointers again, and then we recurse down, right? Here there's no PV search, any conditionals, none of that. It's just we negate beta and alpha and swap them, and that's it. And then we undo the move, and then go down here and verify the score. And it's just a baby version, right? So if our score is greater than our best score, then we raise it. If it's greater than alpha, if it's greater than or equal to beta, then we fail high. Here there's no extra work to do at the bottom, so I just return out here, and I make a new TT entry. Okay, and then down here I do store the PV. I've seen other people also store the PV here. And then down here we have the checkmate check. Okay, of course you can't check for stalemate since we don't check all the moves, right? But yeah, so man, I think that's it. For the QSearch, man, I just totally. I never thought that I was going to get done with this. Okay, so yeah, I make a TT entry at the end with the hash flag, upper exact, because lower is right here, right? And that's why you initialize the flag to exact here, because you're assuming it's going to be an all node. Okay, I'm hoping to finish today. Because I've been recording this for 3 or 4 days. It is now, I believe, over 6 hours, probably like a 7-hour video. Okay, and I'm literally running out of space on my hard drive, which, is really, a bad sign. So I'm hoping that I can wrap it up today, but this is going to be the hardest, most abstract day, right? I'm going to be talking about evaluation, the history behind my evaluation, okay, because it is necessary to talk through that, to talk about where I came from before and where it ended up, okay? Because it is necessary to talk about that, because when it comes to evaluation, this is kind of the personality of your engine, right? This is the part that you get to make it yours, okay? And the way you go about things is supposed to differ from how other engines go about things. When I was going through search, mainly just going through search, right? I was basically saying, I got this from this engine, I got this idea from here. That's pretty common for when it comes to search heuristics, right? Of course, that's also going to be the same for tuning, right? I'm going to say, I read this here, I've read that there, and this is how I, composed this tuner. But, when it comes to evaluation, you're kind of supposed to be sitting here in the dark and trying to figure out how the game of chess works, I suck at chess, but it still has been a good exercise. So anyway, I'm going to be walking through my evaluation as it is and discussing the the steps that I took to get here, because my evaluation looked a lot different when it started. In fact, I wonder how far this goes back, these backups. It probably goes very far back. Yes, this goes pretty far back, okay? So this is, I will probably come back to here later. Okay, there's a lot of code in this file, 2,000 lines. Okay, you can't see it because my face is in here. Okay, but we're going to talk about, all of that. So let's start off evaluation. So when do you evaluate? Well, I talked about this in search, right? You evaluate pretty much at every node. When it comes to your pruning, right? You're going to need to have a static evaluation for reverse futility pruning, right? And you're not going to necessarily evaluate at every node, just every unique position, because you hash it, right? And your eval hash or your transposition table. So that's where you evaluate, and that's where we would enter into this very function. Okay, so first of all, I have eval masks, which is a variable which simply holds inside of it a bunch of 64-bit integers, right? A bunch of bitboards inside of it that are going to help us figure out, which squares are safe, which aren't, what pieces might be attacking here, what pieces are attacking there, things like this. It's attack masks mainly. So first of all, very important, I think, for any engine is to eventually create a pawn hash, okay? This might not be the first thing you do in evaluation, but it is nonetheless very important optimization. So pawn hash allows us to put pawns first, okay, and get a free extra inference before we use lazy evaluation, especially. So I really recommend you do, pawn hashes before you do lazy evaluation. So we search for the pawn hash, we retrieve the score if we find one. If we don't find one, we have to evaluate the pawns. So this is us going into here, and we are going to evaluate our pawn structure. Now there are many different types of pawns that you will probably come across when you read other people's code bases. My pawn structure is fairly simple, and it's always stayed very simple. Okay. Also, my pawn hash does not actually use king position. That is a possible option for you if you want king pawn safety heuristics and things like this. So you may want to hash your king position within your pawn key. That's completely up to you. For me, what that would look like, since I have piece keys for every piece, it would be, game st piece key king, right? I would just store it here. So if you end up with a setup like that, then you would end up like that. So what am I doing here? So I am simply, evaluation is going to be the lowest level sort of bit operations that you're doing. Here I am doing what is a pop count. Okay, we are just literally, this is a built-in function that counts all of the bits that are 1 on a bit board, on a on a 64-bit integer, right? And so that's what I'm doing here. I'm taking our pawns and our file masks for the file that the pawn is on, and I am counting the doubled pawns, right? And so this handles tripled pawns as well, since we are counting them, okay? And this is why it's count -1, because we don't want to count just a single pawn, okay? You could also do something probably faster here and do a function called more than 1 with this bitboard. Now, what is more than 1? Okay, so what is more than 1? Let me try and remember. Let's go with a... Okay, let's try and go with a... How do I do? I never do horizontal splits. Okay, there we go. So I just wanted to go to this function. No definition found. Okay, you're gonna be like that. Where is this function? That's a good question. We could just search for more than 1. Okay. And try and find where it is. I believe it's in utils. Okay, there we go. So more than 1. Okay, this is basically us popping off. Well, popping off a bit, right? This is the mathematical kind of way of going about popping off a bit. We are saying if we take a bit off, will we have still a bit on it? So this just says if it's more than 1. This is way more efficient than doing a full pop count. So that's what I was trying to explain here. So I almost okay. I sometimes get into these moods where I'm a little less in it, so I apologize. So this is what's going on. So I have this attack mask here that I cache inside of the pawn hash for all of the pawn attacks, right? And that's just so that I don't have to pre-compute this when I call evaluation again. Okay, so that's what that is. Yeah. So first of all, you may be also confused, like why does pawn hash matter if we are hashing our evaluation? Well, pawns there are many positions that are the same, that are different, and the pawns are the same. Actually, you may run into a million, positions like this, and this is why here we get so much value out of a pawn hash, right? So these are our pawn hash probes, and this is how many hits we got. Okay, so this number is incredibly close to this number. We get an incredible value out of pawn hashes. So I want to say that right away. So now I'm popping off our pawn bits, and that's exactly what this code is doing. Okay, I am looking for the lowest, least significant bits in this bit board of pawns, and then I'm popping them off one by one. And by doing this, I get the position, and then I do pawns and pawns minus 1 to pop it off. Okay, so this is what that's doing. Okay, so coming down to passers here, what's going on here is I am checking for a pass pawn. I've passed pawn masks which look at I believe adjacent files and in front, and then it's making sure that there is no enemy pawns on the mask. And I am also checking the enemy pawn on file, if there is an enemy pawn on the current file. Okay, so that's what is the definition of a passer, right? And I put the passers on a mask inside of our eval masks. This is very important because every good eval, and I highly recommend probably the most important part of eval is actually passer evaluation. Many games of chess, especially computer chess, are won from dangerous pawn situations, and so that becomes a really big important thing. Okay, so now we have isolated pawns, which are just literally we don't have any friendly pawns on our adjacent files. Okay, backward pawns are a little bit more complicated. Okay, to be honest, I'm a little bit foggy on what exactly the conditions are here, but let's walk through it. Okay, so we have our friendly pawns, and we are checking the. Also, this should be friendly pawns if we are, trying to get rid of pointer dereferences. I'll do that later. And adjacent file masks and in front ranks mask. In front ranks mask takes in our side because we're looking in front, right? In our advancing squares, we are looking at our adjacent file masks, and we are checking if we have friendly pawns there. This is pretty much just isolated, right? But we're also checking in front. Okay, so and then we check from our pawn captures, which means we're going diagonally. If there is no, we are looking at our forward square, which is in front of us, directly in front of us, and we're looking if there are enemy pawns there. The goal with this is to check if our square in front of us is controlled by an enemy pawn. So that's what enemy controls front is doing. So if we don't have a supporting adjacent and the enemy controls the front, or the forward square is occupied by an enemy pawn, then we call it a backward pawn. I believe these are the conditions for a backward pawn. Anyway, believe it or not, backward pawns are not always a bad thing, and we'll get into this while we talk about tuning and doing your features and bucketing, that you may want to do something like I do it, where I bucket by rank, and that is what I'm doing here. To explain, the eval params array is a array of over 1,000 weights that have been Texel tuned. Okay, and so I'm indexing it by this EPIDX, okay, eval params index, which is simply a struct with a billion different things inside of it that points to where that thing lives inside of the weight array. And so that's what I'm indexing in here, and I'm indexing into backward pawn by the rank. So I'm saying a backward pawn on this rank, how much are we penalizing? And so the way I tune things is I tune it based on rank, because a lot of these things, a backward pawn on rank 4 is much worse than a backward pawn on rank 2, for example. Okay, so of course this goes obviously with passers too. So the candidate passer, it is, I forget exactly what the difference is, because it looks very similar. But there is some difference between how we calculate this and how we calculate that. And I think it has something to do with the pass pawn masks. And so I probably will have to, think about this, because the last time, when I was going through this later, I was like, confused. I haven't looked at the pass pawn mask in a long time and, thought about this. I haven't touched my pawn structure in a very long time, because it kind of just, it's never been a problematic point in the evaluation for me, actually. So chained pawn, very simple. That is just us looking, from our pawn captures to see, are we supporting another pawn? That's what a chained pawn is. Okay, so that is pawn structure. In my opinion, the most simple part about evaluation. And so if we just evaluated, we create a new pawn hash entry. All of my scores inside of eval are white minus black. Okay, white is always positive, and I just negate at the end based on what color we have. If it's black, then I just negate the color. Okay, so I do PW minus PP, which is white minus black here. Okay, and you may be seeing S plus equals PW minus PP. Why do you have it in one score? Why not MG, EG? To give an introduction here a little bit further, MG and EG you may be familiar with if you've done any of this research into chess programming, right? With a tapered evaluation, you're basically interpolating between an MG score and an EG score, which are composed of different values based on the amount of material on the board, right? I explained this a bit earlier, that every time we take off a piece, we subtract from the entire phase on the board. Okay, so then where are my MG and EG? Well, a bit complicated to explain here, but a bit of magic is happening here, where I have 32-bit scores, which are composed of two 16-bit integers. The bottom 16 bits are mid-game scores. The top 16 bits are endgame scores. And so, believe it or not, when you add them together and accumulate them, you can simply retrieve the 16 bits at the bottom and the 16 bits at the top and separate them at the end. And so instead of adding and having an MG variable and an EG variable and having all of these extra operations where we are adding twice for each score, it's very inefficient. Instead, we can just add one 32-bit integer once. And it's such a it is such an incredible convenience and such like a magical sort of thing that the bits work out that way. But that's where all of this is. So this is why if you go here to my old eval, you're gonna see MG plus equals this, EG plus equals this, right? And most things are going to be I'm adding this and this, and most things, right, that aren't in here have like double attack bonus MG, double attack bonus EG. We save so much time and so many operations just by adding once instead. So that's a bit of the magic that's happening here. It's also happening here with the PSQT scores and the material scores. So that's very important. Okay, so going further here. So also, these are incrementally updated. If you go back to my make and undo move, you will see these values getting accumulated, okay, and getting changed when we move pieces or take them off the board. You can do this non-incrementally as well. It's actually, not incredibly, much faster. However, this is necessary for lazy evaluation, which I'm about to talk about. Lazy evaluation, as I explained earlier during the search portion of the video, is us checking our current evaluation at different points in eval against the bounds. We are seeing if we are above beta by a certain margin or below alpha by a certain margin. The margin that we are going to use to be safe is always the amount of eval, the sum of the eval that is rest at its maximum. So if we had the maximum score of everything past us and we're still above beta, right, so, right, you've got to subtract it, right? So if we had the worst score possible of everything else and we were still above beta, then we can exit out now. So this is sort of, you may think, okay, so this is a speed thing because we can early out and not have to go through everything else. And it is definitely a speed thing, but it also is a search stability thing as well, because it narrows down the extremes of your eval. Okay, and it makes things, I think Windows just naturally become a little bit more manageable, right? However, I think, so in my kind of thinking about this and the, I don't know. it's interesting. It's hard for me to really understand how it affects the search tree, to be honest, and that's why I have it off while I am SPSA tuning right now, because I was unsure about it. I was unsure about my margin, and while I was doing all of this tuning still, and so it's definitely, it did give me a big elo boost when I did it the first time, but as for it working right now, I can't really say anything to. I do think it's a really neat idea, because there really is no reason for you to keep going, because I guess the idea is that we are already going to cut, right? If our evaluation is already here, we're probably already going to cut the node, right? And so having a static evaluation that is wildly higher may be pointless, but it also, I don't know. It may affect certain things, like corrective history, right? That we have it updating based on the basis of our static evaluation going up by the end of the node, right? So this may affect things like that and the efficacy of those techniques. But perhaps I'm wrong and I'm thinking about it wrong. But anyway, I just wanted to mention that's why this is currently commented out. But I do highly recommend you play around with it once your eval is sorted out. And the way I figure out the margin is I simply, whenever I change something in the eval, I have I basically print out the best scores of the eval. I just track them in this variable inside of search data, the highest reached for everything past that lazy margin, and then I simply just use the highest value that I see. Okay, so that's all of that. Now, what am I doing here? Okay, so this is going to be the hard part to explain, actually. So couple of things here. First of all, this entry is the pawn hash entry. The reason I defer it to here is so that I can skip any unnecessary copying before our lazy one margin, but obviously that isn't in play right now. So you can just imagine that this just copies the masks from the pawn hash entry up here. Same thing. So what are these piece attacks? These piece attacks are indexed by side, piece types, and piece max. What is piece max? Piece max is 16, I believe, which is technically higher than it would be possible for any piece type. But how do I explain this? Well, we're going to have to look through the implementation and talk about it. This method is different from the method I used before. Before, I used a method of mapping each square to a unique ID that was an index into piece infos. Okay, those piece infos were important because in the middle stages of my engine, I was incrementally updating attack masks for each piece. I'd assumed that this would be faster than just calculating those attack masks during eval. I assumed that when you move a piece, it would be easier to just cache the attack mask because in eval you have to create everything from scratch, and so if you already had that information, just think about it, right? You only move a piece once, right? And then you eval and you have to, recompute every attack mask. It'd be easier if you just had the attack mask and then just change the one that you moved. However, doing so is a lot more complicated than you would think, because discovered attacks and sliding piece attacks, right? If you move a piece, you're not only affecting the attack mask of that piece, but other sliders that targeted that piece before. Okay, and so what you end up having to do is recalculating the sliders that intersected with that square, which is a very complicated and expensive operation to do. However, that was what I was doing because I had assumed that still it would be marginally faster. It isn't, though. It really isn't. And so later on, right, I realized that the updates for all of that was too much. And then even further beyond that, I was still using, even though I was now recomputing attack mass from scratch in eval, I was still using those piece info to iterate, right? So what I would do is I would store on the piece info the attack mask when I generate it during evaluation, and then I would simply be iterating through the piece info. I wonder if I have an example of what this looks like. I'm not sure if I do. I do. So this is what this looked like, okay? So I had 32 possible unique IDs for each piece on the board. I would iterate through, get the piece info, and then I would see if the piece was alive, if the side wasn't equal to the current side, or if it was a pawn, then I would continue. This is inefficient, okay? Not only is this inefficient, but it is completely unnecessary, and the square to UID updates were inefficient. A lot of extra operations. Not only that, but inside of make and undo move, right? When you have something like state info, this linked list that is now restoring your previous states, it is much easier to just simply have a function that doesn't do the square to UID messing around, with replacing the UID here, moving the UID there, toggling if a piece is alive, when a piece promotes, changing the type of this piece, right? There's just a bunch of extra operations that happen where this becomes a bit inefficient, right? And just think about it, right? We are iterating through all 32 UIDs every time, and then saying, okay, if it's not our piece or if it's a dead piece, we're going to continue, right? In a chess engine, every single operation matters, and so I moved onto piece lists. Okay, so what are piece lists? Piece lists are very confusing to understand. I'm not going to lie here. I pretty much just iterated on it until it stopped breaking and until the assertion stopped failing. It was very confusing. Piece lists are for each side, for each piece, and then you have all of the squares that all of those that piece type is on, right? Those are the different dimensions of the array. So the last dimension, right, at the bottom is all of the squares that the piece is on, that the pieces are on. So if you had like 3 pawns, right, it would be e4 blah 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 blah, right? 3 different locations. However, you may be saying, well, how do we remove one, right? So this becomes complicated to understand. Okay, so when we remove from the piece list, what we are doing is we are indexing into another array called piece index. Okay, this is the stockfish way of going about indexing things. Okay, so to explain and demystify it, okay, so we are indexing into piece index, which is a 64 array, very similar to my square to UID, where on a certain square it pointed to a piece info, right, based on the UID. Very similar to this, whatever is on this square is going to point into which slot inside of the piece list has that square. Does that make sense? Let me say this again. So we are going to index, so let's say we want to take a pawn off the board, the pawn on e4. Okay, so we will go to the square of e4 inside of this array of piece index. The value we get out of it will point us into, white pawn. We will go to white pawn at this square, at the square of e4, right? We will find the square of e4 at the piece index that we get out of the 64 element array. And so now since we're removing a pawn out of that index, what we do is we take that value and we simply remove it, and then we put the end of the array, the last piece in the array square, and move it to that position, and then decrease the amount of pawns that we have. This requires us to keep piece counts, which we already need for our material hash keys, right? Material hash keys used for corrective history are keys of all of the counts of material on the board, right? So if there are 10 white pawns, right, we just XOR it with the 10 white pawns hash key. And then if there are 9 white pawns, we XOR it. If it goes to 9 white pawns and we take one off, then 9 is a lot. It's more than is physically possible, but let's just play pretend for a second that you take a pawn off, and now you XOR it with the 10 again to remove it, like we do with all of our hash keys, and then get to 9, and then we XOR it with 9 white pawn, the key. Okay, so it requires us to have that piece count, though, because we need to know the end position, the last pawn to pop into that slot that we are removing now. Does this make sense? I hope it does, because it was really difficult for me to understand. It's not difficult to understand. It is difficult to implement, though, because there are some cases here, right? So there's that. Now, how do we get this? So naturally, right, when we initialize our board state and we are putting pieces on the board, we are incrementally updating our piece counts, right? And so naturally, when we put a piece on the board, we are incrementing all of the piece list, right? When we put a piece into the piece list, we increment the piece count, right? And then the next time we put a piece on the board, we put it at that piece count, increment the piece count, right? And then so we're slowly filling up the list, okay? And so when we remove one, what we're doing is we're taking the last one on the list, putting it in its spot, and then decreasing that piece count, effectively, changing the size, the usable size of the array, okay? And this is a way more efficient way of iterating, because whenever we hit the end of the squares, right, we no longer iterate. So there's none of this checking if the info says that the piece is alive. There's no checking for which side we're on. We can even, since it's indexed by piece type, we can just iterate from the knights to the queens for mobility purposes. So there's a big benefit from implementing something like this. So I hope I demystified this for you a little bit, what's happening here. Now I want to, of course, show you the implementation so that you can, if you choose to do something like this yourself, then you can take a look at this. So what's happening here is we have three functions here. One that moves a piece from X to Y, one that removes a piece when it gets taken off the board, and then one that puts a new piece on the board. Okay, so let's just walk through what this is doing. First of all, I glossed over, since we were early on before when we were doing our make and undo move, I glossed over the piece at array. The piece out array is simply that. It's a fast way to look up, hey, what's our piece type at this position? Okay, it's necessary if you are encoding your moves as integers, because now you don't have that information on the move, and so to find out if it's a capture, you need to look at that piece and see if there's a piece there. Also necessary for this is going to be creating an enum or not an enum, a constant, or define or whatever, with two different ones, right? One for piece none and one for square none. I have piece none at the end of my piece types. Okay, after king I have piece none. You can just as easily do it here. For mathematical purposes, I typically like, even though it isn't 0, I like to have my piece nones or whatever none at the end of my enums, because I like to iterate from 0. Just my programmer brain, just the way I think about it, I prefer not to have the none at 0. So in this case, the none is actually an integer space, right? A value of 6. Okay. So that's what that is. And it's the same thing with square none. Okay, square none I believe is 65 exactly. So I put it at a 1 beyond the board, right? Okay, so I hope that I'm, explaining that correctly. Square none is important because square none is going to dictate the end of your iteration. When you hit a square none, that means there are no more pieces left on the board. It makes this incredibly fast to when we iterate it during evaluation, or whenever we're iterating through all the pieces on the board. Okay, so let's see what's happening when we move a piece from one location to another. We are changing the piece at the from. We are taking it off the board, piece not. We are putting it at the 2. Okay, we go to the piece index of the 2, and we put it at the piece index from the from. This is basically the ID of the piece. Okay, you can think of this. However, what this index is, it is technically you can think of it as the amount of pieces that was valid when we put this piece on the board, right? That's what this value represents. Okay, so that's what it is. So we have the piece index, the 2, that becomes the from because we're moving it to the 2. Okay, then we enter into our piece list, right? It's indexed by side, piece, right? And then the last dimension, right, is going to be all of the pieces at their squares, right? And so we use the piece index at the 2 and then turn it onto the 2. Piece index of the 2 is exactly the piece index at the from. Okay, for a move piece, it's incredibly simple. All we're doing is indexing straight into the piece list, where that piece lives in the list, and changing the location of it. That is all that is happening. There's nothing complicated happening. However, the remove piece is a bit more confusing. Okay, so explain. We are getting the last element of the piece list array, which is the last square on that list. Okay, we are going to shrink the array effectively by piece count -1. Okay, now we are getting the index of piece 1, the piece we are removing. We're going to get that from the 64 element array of all the indices. We get that index. Okay, we go into last square's piece index. Okay, and then we slot in piece 1's index into piece 2, effectively giving piece 2 piece 1's identity. Okay, and then we index into piece list with piece 1's index, which is now piece 2's index, and give it piece 2's square that we found out that it lived at from the beginning. Okay, and now we have effectively swapped them in the array, but it doesn't exactly make sense per se, because it's confusing to understand, because typically when you do something like this, you're working with direct indices that make sense. You're switching element 1 with element 2, or x with y, right? Here you have this additional layer of abstraction of these piece indexes, right? Where you have to switch the index before you switch the square itself. Okay, so you aren't actually swapping the elements as much as you are swapping the identities of both of these pieces. Very, very confusing. I'm sorry it took me so long to explain this, right? Because it is a bit confusing. Okay, moving on. That's the most confusing part about all the piece lists. Okay, now putting a piece on the board is extremely easy. Okay, we just go to the piece index of S, which is going to be the square that we're putting it on, and then we just assign a new piece count of the next one, right? And increase the piece count, and then go to the piece list at that new index that we just assigned, and we give it that square. Okay, and then we just change the piece set to that piece. Okay, and to look at how this works in practice, when I remove a piece, I call that function, right? And when I do my material keys, right, since this remove piece naturally decreases the piece count, I simply have this here and have this after, because the piece count has naturally changed within that function. Okay, so I'm glad that we got that dealt with and out of the way. I hope that this clarified you how piece lists work. Now, I'm probably going to explain more right now, but yeah. So when I go into generate attack mask, okay, we are sending in our piece attacks, which is just an empty array. Or, well, it's not empty. I don't initialize it to anything because it isn't necessary. It isn't necessary because we're only going to be iterating what is going to be filled. Okay. All right. Here is generate attack mask and eval mobility. It doesn't eval mobility at all. Okay, the name is completely incorrect. I just haven't changed it in like a billion years. Okay. What is this function doing? Okay, so I commented a bit of this out beforehand. Okay, so this function is it is looking at all of our pieces and creating attack masks and information that we're going to use in the rest of our search later. So here's what happens. So we already have our pawn attacks. If you refer back to what I went over earlier, we already have our pawn attacks. So all we need to do is slot pawns on to attack mask no king, and onto the main attack mask, which I'm calling attack squares. Okay, let's go to eval masks. Okay, I just want to talk about eval masks. What is inside of eval masks? All of these different things. Okay, let's just go through them one by one. We have the attack mask. All of these are pretty much for both sides. Okay, so we have the main attack mask. We have attack mask no king. We have attack mask for non-pawns. We have attack masks for minors. We have attack mask for X-rays no queens. We have SPPA, which is safe pawn push attacks. We have safe. We have attack mask piece for each piece type. We have double attack masks for when we have double attacks, two pieces attacking the same square. We have WSQ, weak square. We have outpost. We have threat deficit penalty, which is kind of the thing that runs everything in my engine. We have passers front, passers file. Now, these three are not in use. Okay, and so I should not see any errors here. I do see 6 errors here. some of these things I need to clean up for sure. We put it on masks passers. We do put it on masks passers. These should not be in use. These should not be in use. They aren't. Okay. I don't think am empty is either. I do need to clean this up for sure. Okay. I think that everything else probably is. I don't think that this is in use. No, it isn't. Okay, so all of these are the ones that I'm currently using. But as you can see, this has gone through many iterations. Okay. So we are putting the pawn attacks. Okay, we already have attack mask pawn and attack mask pawn, right? We already have that done because it's calced and cached in the pawn hash, or we just calculated it on evaluation. We get our occupancy. Okay, so this is how we iterate the piece list. This is exactly the implementation from Stockfish, and except this is how they iterate it, but not in the same calculating the same things. So I do kings separately because I have attack mask no king, etc. So I go from knights to queens. So that's what this is doing. Right, and we're going for our side. We get the pointer to this for this piece, and then we simply increment the pointer, stepping forward in the array until we hit square none. Right, this is like an elegant, fast way of doing this. It would be equivalent, right? If I have this IDX here because I was testing this, right, and down here I have IDX plus. It would be equivalent if we do, we could just use, I want to be explicit, so game piece list, index by the side P, index by IDX, okay. Yeah. This would be the exact same thing as basically this. I think that this would be right. So you start off the position with this, and then you just set it to the next IDX every time, and you just increase the IDX. You could also just literally write this in a much more simple way. In terms of you just increase the index instead of the position and just get a new position. Like you could write this as UT IDX equals 0, and then just at the end just do IDX plus, and then you could just do a while loop, to be 100% honest, because there's no you could just you could just technically go game piece count side P, right? And this would just be it, and then you would get uint at pause equals and I believe that that's just equivalent. Okay, so we are just looping through each index and then going to, well, of course you want to do, sorry, I am, right, you're just looping through the piece count, and then you're going to get the next element in the array. So that, I believe that that's just equivalent, right? Except, apparently this is faster when you are incrementing the pointer. I think it's neat, except writing code like this myself is pretty scary. I always prefer to do this because I just I make less mistakes when I do stuff like this. But yeah, this is equivalent. We're just stepping through the array until we hit square none, and that should be equivalent always to the piece count. Okay, so that's what's happening. Okay. So I was doing some assertions and making sure when I implemented this with the IDX, so that's why that exists. Anyway, so we call moves at, which gets our attack board for the current square that we're at for the current piece, right? So this goes for knights and all the sliders and all that. If you want to know what this looks like, it looks like, you know, this. I meant to open it up in a split, but whatever. Yeah, so this is what this looks like. It just gets our moves, right? Okay. So we get our double attacks, which is simply just the attack mask and our moves. So if our moves overlap with the attack mask, then we just push that onto the double attack array. I'm just going to assume that by now you know what ORing is and ANDing is, right? Because I went over it earlier. So attack squares, we OR it with the new moves. We put the new moves on there. For each piece, we put the new moves on to that piece, right? Since it's yeah, so for knights, right? If knights overlap, right, you're just, you know, it's just, this is per piece type, okay, not per piece, right? This is why we have this piece attacks array. This is per piece, right? Because we're indexing by piece index for the pause. Now, you could just easily do this, I believe, with the IDX itself, this incrementing thing. It should be exactly equivalent to doing IDX, right? It should be absolutely equivalent. We are taking the attack mask no king as well. This is used during king safety to make sure that the king isn't the only one defending the squares around him. Okay, so that's why that's significant. So this is interesting. This is like my own, I think, like this is my own idea that I came up with the X-rays. I ran into an issue when I was tuning my weights and, you know, figuring out how to represent contact checks, because very often you'll find with a queen attacking a king that the queen ends up, you know, hitting the king on the side, but the king might be able to take the queen. Okay, so naturally you may think, okay, well, what if the square is double attacked, right? Attacked by the queen and another piece is backing it up. Well, often what you're going to find is that the very piece that would back up the queen on that square is actually behind the queen, right? On either a diagonal or a straight file, right? A rook behind the queen on that file, or a bishop on that diagonal, right? That they're you know, skewering each other, and so the queen is naturally going to be blocking the piece, the ray, and so you're not going to get the fact that the queen is actually backed up on that square, because she is currently blocking the ray that would back her up otherwise. And so the way I handle this is I simply compute another attack mask without the queen on it. And the effect of this is that now we can figure out if they are aligned, right? Will the queen be safe at that square? Okay, and I use this during contact checks to be able to figure out if a queen is a queen is actually dangerous, right? Because you know, typically you think like you know, once you get to a square, that if it's backed up, if it's double attacked, right, that means safe, right, in terms of evaluation. But in the case of a queen and rook, right, and a bishop, right, these sliders that might back each other up, it isn't the case. It isn't the case sometimes. And so I only do it with queens, but it is possible that in the future I may look to do something similar with rooks. But you do kind of, this is already such an expensive function, right? So anyway, that's what that is. So we're getting to the bottom here with these attack masks. So I do the kings separately just because it doesn't go on attack mask no king, and everything else is the exact same for it, right? Of course, I only do the X-rays for bishop and rooks, right? Okay, so I put it at the piece attacks as well. Okay, so this K square, I maintain a king square for both sides. so that I don't have to actually count the bits every time I want to find where the king lives. This is a good optimization I have. The king doesn't move nearly as much as any other piece, and so it's information that doesn't change a lot. And you want to find where the king is all the time. In movement generation, if you're checking if a move checks the king, or anything like this, you're going to be popping the bit off, maybe a bunch of times. Well, instead of doing that, just maintain a king square variable. So that's what that is, and it's on the state, so I can just undo it. It's very, very efficient. Okay, so attack mask minors, I just OR the attack masks for both of those pieces. Threat deficit penalty. This used to have a lot more conditions to it. I used to remove the kings from both sides. I used to remove the queens. I used to remove the pawns. It went through many iterations with double attacks especially. It used to be like and not queen, and not king, right? My idea behind that is, right, it's kind of like a pseudo SEE, right? If a queen or a king defend a square, it's pretty dangerous for them to take anyway. Now, does this work, really? Based on my tuning, this was the simpler, version of this was what ended up, it seems like it performs the best. I do want to take a look at it again to see how I can think about it differently and test it more. But threat deficit penalty is basically just this: is squares that they attack more than us. Okay, that's literally it, and it's used all throughout my evaluation. Okay, now the smaller TDP, the safe, is used in some other places. Where you don't really care about the double attacks. I really just this is used mainly during threats, I think. I have to look at it again. I may not really use this at all anymore. I've really slimmed down the threat calculation. So anyway, pawn pushes, I calculate pawn pushes. This literally just does the same thing as a movement generation. I only calculate it with the pawn pushes that are safe. This is very important. So safe pawn push attacks. So I push the pawns and then I find if they are safe. And this does use the mask safe. That's where I use it. So a pawn pushing to a certain place, right? I want to make sure that pawn push is actually a good push, and it isn't just going to get immediately taken. So that's what that is, okay? And I check the pawn attacks from there, and I use that as a threat generation, right? So think of, let's say we have a piece, this knight is on this outpost or whatever, and what my evaluation is doing here is it is saying, well, we have a threat here of just pushing a pawn onto a square that they can't take back. And that knight, they're going to lose a tempo and have to move that knight. And that's what this is measuring, okay? And so weak squares are for just, very simply, we attack it with a pawn, they don't attack it with the pawn. It's used for outposts. Now, I really want to take a look at this more and try and figure it out better. I'm going to go through, once I get to threats and stuff, my ideas were really interesting for all the threat things, and tuning killed them because they didn't get enough, signal in the positions. So we're gonna look at that later. So anyway, now we get down here. So this is lazy 2. This was lazy 2 back in the day. I haven't touched this in a long time. The idea was to estimate king danger without doing a full king safety check, just to estimate lazy. But I got rid of it, especially now that my search is just fast, right? My search is, goes to really high depths now. Having this, trying to reach for the speed by sacrificing evaluation just isn't something that I'm willing to do. All right, I just ate, so I'm back, and we're going to talk about the individual pieces left in the evaluation. So first of all, this is my per piece evaluation. Okay, here's what it looks like right now. This has gone through many different permutations. So it starts off with the bishop pair. Okay, so in my engine it is defined as both a dark square and a light square bishop, right? Because that's the definition, not just two bishops, but on the different color squares. So I have two different bit masks for this here. Okay, next I have PF square, which is the stockfish idea for pawns front squares is what I call it. So these are pawns that are blocked by enemy pieces. The idea is to remove squares from mobility that aren't valuable. Okay, so in an engine we are trying to get a value for how active our pieces are, is the idea. And so typically the more good moves they have, the more valuable the score is. So this is the idea, to remove those pawns from it, because those pawns are just not as valuable. Supporting these pawns, since they can't even push, is not a very valuable move. I really like the idea. I've tried many different permutations going through mobility. I've tried only safe mobility, as in any spots that the enemy attacks, or right now I just have only enemy pawn attacks, because spots that the enemy may attack, we still may attack those spots as well. There are some tactics that are important, even if the enemy may attack it. They may only attack it with a queen, so I leave it like this, because if it's attacked by a pawn, that's typically a bad thing. And it's important, because if their pawns attack very important central squares, then our mobility score is going to suffer, and that's exactly what we want. We want to have control of the board. Okay, so going into outposts, how do I calculate outposts? Okay, so safe pawn push attacks. Once again, pawn pushes where they end up at a square that is safe, it's either defended or not attacked. So those are safe pushes, and then we get the attacks, right? So the idea is that we are taking the enemy's weak squares, right? We attack it with a pawn, and they don't attack it with a pawn. And our center squares mask, which is literally just a 4x4 in the center of the board, and their safe pawn push attacks, and not safe pawn push attacks, which is just they don't have a response that would refute this outpost easily, right? That would easily defend it and make our knight move off of the outpost. So that is how I designed it. Okay, so once again we have the pieceless iteration, which we already went over. Okay, and then we have our mobility. So I create the mask. I get the piece attacks once again from our interior piece attacks indexed by piece list. This once again would be the exact same as if we had the C at the bottom, and I was using this to do some asserts just to make sure everything was working. But you could just index this by the amount that we've iterated. Okay, so going on to the next thing. So mobility. So this is exactly what I just talked about, right? The PF square, we are removing those pawns from it, and not the enemy pawn attacks, right? Now SMob is the safe mobility that I use later. I believe that this calculation is used for unstoppable attack, which is my idea that if there are 0 safe squares that we can move to, and we are currently in a threat deficit square, meaning we are currently attacked more than we are defended, then we have what I call an unstoppable attack. This used to be side to move doesn't equal side. What that was doing was it was saying if it isn't our side to move, then it's truly an unstoppable attack because they have the opportunity to just capture our piece for free. It's basically like a pseudo SEE, right? However, this sort of doing it based on side rather than doing it based on tempo, based on move, it's a dangerous thing. It makes things asymmetrical in terms of evaluation. In certain scenarios, people think, okay, well, we'll give an extra bonus for the side to move because they have the initiative. I've read this in other people's code, in other people's code bases. It's actually only made my search unstable in terms of pruning and reductions and all of this, because of the nature of a score propagating backwards, right? If you have this asymmetrical quality to it, right, this will sometimes unbalance the pruning and your search tree, therefore. And so it's something that you can keep in mind, you can test for yourself, but this is just my observation that I get a more tame, more I don't know, generalized result when I do it this way. So that's why that is there. Now I only do outposts for knights, okay, and you're gonna see here B and B down here as well. What is B? Well, it's just simply my pre-computed bits pause mask. Okay, so just one bit at that square so that I overlay it with the outposts and then see if we're occupying an outpost. This idea for us to control the enemy outpost squares, that means that are weak squares, right? This idea, it now is deprecated because I need to calculate the outpost squares outside of the generate attack mask. So I could simply make a step before I get in here that calculates the outpost masks before we get into here, so that I could do this, because this uses the opposite side's outpost, and here I only calculate our side's outpost. So there's a small, I could fix that, right? And so I probably will fix that soon. But that's why that's commented out. But yeah, the idea is sound, right? It's just saying we control these squares that could become enemy outposts, right? Okay, so this piece of code here is enemy territory 3, right? Which is a mask that is just the 3 ranks on the enemy side, okay? So what we're saying here is we cannot enter those 3 ranks. Now during the mid game, that's especially important because you are trying to have activity, right? Create threats, and so that's the idea, that if we can't, if we don't have a single move that's within those 3 ranks, then our piece just isn't doing what it should be. Now, of course, this isn't a something that happens all the time, but Texel tuning has proved that this is a benefit having this. So, okay, so that's all of that. Now here's like some of the more per piece things. Very simple here. The rook things, everybody has this in their engine. If it's on a open file, if it's on a semi-open file, okay, this is just checking. An open file is where there's no enemy pawns, and if there's no friendly or enemy pawns, and then a semi-open is where there's no friendly pawns. Okay. And then if on the moves for this rook, if there is another rook, right, I just add a bonus for connecting the rooks. Okay, and then this is the queen. Okay, so I just have simple if the queen is connected to the rook, if queen is connected to the bishop. Okay, so that's just really simple. So this is straight from Stockfish, right? It was me implementing the check info slider blockers, and it was very I don't know, really just like brilliant to like implement it myself and learn what exactly is happening here. It is basically finding if we are pinned, right? Is we are taking the enemy sliders, right? So the enemy rooks and enemy bishops, right? And we are seeing in this position if we are intersected with the king, which regardless of tempo is like a really dangerous thing, right? Because you're giving the opponent a lot of control, right? So this just says if our queen is weak or not. And it's strange, and I might I don't know if I'll remove it per se, but given tuning, it actually it is only negative in the mid game in terms of a penalty, and in the it skews positive in the end game to kind of balance it out. So I'm not really sure if the signal it's getting is 100%, but it goes back to my original idea, which we can probably take a look at here, with evaluate pins, which was my old function. My bad, I misspelled it, which was here, okay, where I checked for if pieces are pinned to the queen or the king. So this was my original, idea, and it never worked out. It really never worked out. It was too noisy with the pieces that were pinned to the king, and the way that I would do this in terms of like calculating it was this function. Okay, so really I was adding to this pinned mask all of the pinned pieces, and it is possible that maybe I didn't try hard enough, and I should have probably made different values for each pinned piece, right? If it's a pinned rook or a bishop, it matters more, right? And so it is possible that maybe I should return to this like more general idea, because I do think that bishop pins, rook pins are also like important in terms of understanding like tempo and threats and stuff. So I may return to this and try this better in the future, but basically that's what this code is doing. Is it is removing the blockers between us and the king. I also used to do this with queen pins as well. It was super noisy, but that was actually a part of my engine in the beginning. Was I was kind of really annoyed with everything that was king safety, right? When a queen getting trapped, or a queen getting pinned, or a queen or some pieces getting pinned to the queen, are just as dangerous, because if you get into a situation where you have to sacrifice a piece to save your queen or something, this is equally, as bad as your king being unsafe, in my opinion. So I tried a lot of things with queen safety, but it's so noisy because the queen is such a mobile piece where it can go, just like jump across the board anyway. So determining if a queen is trapped or if a queen is in danger is really difficult. Okay, so anyway, that's what all of that is. So what next? What next? Okay, so that's all my per piece evaluation, and now is my threat evaluation. Okay, so this threat used to be totally different. I wonder if I can pull up my old threat code. I definitely can. It is here, right? It should be. It should be. This is here. So this is my old threat code. Okay, so this was the calculation. I had the pieces that a piece was attacking, on a mask, and I while looped and popped off the bits individually, and then I had a table of threat values indexed by our attacking piece and the piece at the 2 square. Okay, and with that threat value, then I modified it by multiplying it by the features on the board, right? If this piece was within the king moves, the immediate 8 squares around the king, then I would multiply it times 2. If this piece was already on a threat deficit penalty for the enemy side, then I would multiply it. And if that enemy side was not side to move, that means that we have an immense amount of threat, then I multiplied it times 2.5. And then if our piece was attacked, I just slightly scaled it back. There used to be also a few more things here, but then only then did I add it to the threat score. So that was my old way of going about things here. So why switch, and why so a lot of this stuff, it's interesting. It's very interesting because the threat value is at a base dictating already these multipliers, right? So a queen being under threat, right, when it's inside of the king moves, right, that it's the king's defender, or that it's already TDP'd, right, and we're attacking the queen, that's going to be a huge value. While if it's just a knight or whatever, it will be a small value. So that's what I liked about this, was that there was this sort of like another dimension to it with how our threat was being applied, and so I really like the idea. However, tuning it is impossible. Once you see later how we are going to compose our feature sets and how we are going to bucket things, etc., doing this sort of multiplying times some scalar, you can't tune it properly, really. It's possible that something like this could be SPSA'd actually, but for the way I ended up Texel tuning and things, doing things like this, and what I used to do with king safety, doing like exponential stuff and all this math, it ends up being a lot easier and a lot more better to not do this. Besides, there are ways for us to approximate this in other ways. And besides the, it being a king defender, right? This should already be expressed within king safety, which you're going to see in a second. Okay, so my threats are now super simple. That was like a more complicated calculation. Now it's very simple. So for now, I just take the enemy pieces without pawns, and then I use this. So once again, this should be just AMM, which is attack mask minor. So that's my optimization there, so that I don't have to do this multiple times. But I think that anyway, this is like the only time that I do it anyway. So anyway, this is us popping off the bits once again, and we have this. So now, instead of doing it per piece, right, per knight, per bishop, we do it threat by minor and threat by major. Okay, so why not have that fine control over it? Why not have that? So what you're going to realize, this is going to be kind of tied into tuning in a way. Okay, so how do I explain this? With tuning, okay, depending on how big your data set is, you may just simply not have enough features, getting enough signal to facilitate having this more fine arrays, right? What I mean by this is, if we had threat by knight, threat by bishop, okay, and then had it for each enemy piece type. Okay, this is adding a lot of variations to the positions that we are finding, and we might find more and more outliers in our outputting data because we simply have some imbalance, right? Where like bishop attacking a knight versus knight attacking a knight, we find that, you know, there are some outliers, and you'll find this with certain things, especially when we talk about bucketing and things like this. That so threat by minor, the idea of threat by minor, is also just to have a smoother gradient. That's really reason 2, right? The obvious first reason is that that we want to pop bits off the least amount as possible. So having this extra second bit board, you know, and then having this split up, right? Then we would have 4 different while loops. That's kind of the main reason here, because this makes it a lot faster. Okay. This is also why it's faster than what I had previously, which just went per piece and then went through the attack mask per piece. Okay, while this gives us a more accurate evaluation, it is not worth the raw speed. Something important that I learned, as you may see, my evaluation has changed a lot. You know, I used to have a lot more going on. Like, for example, this, which determined the amount of blockers that are between us and the enemy king if our rook is, or if our queen or rook or bishop is intersecting with the enemy king. It had these fine-tuned features that simply were not worth the raw speed. And so I learned this through both testing and looking at other people's engines. And I realized, you know, while I loved, you know, being able to design all of these things and like work through all of this, that it was you know, holding my engine back for sure. Especially once you get to a certain point where your search has matured and where the bottleneck becomes your evaluation, you want to be able to, you know, make that decision, right? So that is, you know, what I ended up moving towards. I think once I started tuning as well, I started realizing all of these things just aren't helping as much as I thought that they were. So there we go. Okay, so EDEF is just enemy defended pieces. This actually isn't in use anymore, other than, okay, so it is in use now. So this is determining if it is defended by a pawn or it's double defended. Okay, so very well defended pieces, right? And then first of all, this is redundant. I'm using you as my rubber duck sometimes. It's helping me clean up the code. So I say weak is when oh, actually this isn't redundant, when it's not defended but it is a piece and it's not a pawn and it's on their threat deficit penalty. So a square that we have more threat on, you know, and that pseudo SEE thing that we were talking about earlier. So now we check if they have more than one weak piece, right? With that function I was talking about earlier, more than one, it just simply counts, you know, if we have more than one bit on a mask, and then I add that, add a bonus for that. This is just literally taking SPPA and the non-pawns for the enemy and saying, okay, we have these safe pawn push attack threats, okay? And then SP is our safe pawns currently attacking non-pawns, okay? Especially, so this is our currently safe pawns. The reason why I have it as currently safe, because I want to minimize noise. You know, if this pawn is attacking, but it might just be taken in the next move, I want to solve that horizon issue right now and not count it. So I only count defended pawns. A lot of this stuff has I think when you get into tuning and you start like looking at the values and you start seeing, oh, this seems like, why is this positive? This should be a negative value. And you start like thinking about it and like, then you start realizing, okay, well, maybe if I move this around, then it'll go in the direction I want it to. That's a big part of, tuning your evaluation. Okay. So anyway, next up, we got through threats. Now we're going to passers. Passers is very important. Okay, something I neglected early on in my engine, for sure. Okay, so what are we doing here? I'm just simply looping through all the passers. We push the passers onto that mask, or remember we got it from the pawn hash in the beginning. So what am I doing here? We have a rank, okay, of the passer. We're checking. Okay, so this is a bit complicated here. So we are saying if our rank is on the 7th rank, okay, in my engine the rank is not absolute, so this means rank 6 or rank 1 because it starts at 0. Okay, or we already have a passer on 7, then I bring the threshold down and I say even a passer on the 6th rank can now be counted. Whereas passers on 7, I am with this variable I'm saying I'm giving a bonus for us having more than one pawn about to promote, okay? Because I think I've observed in games, right, this is sometimes a game changer, right, having two different pawns that are about to promote. And so this is me giving this as a reflection, right? So that's what I'm saying here, because during tuning I wasn't getting enough signal from literally having two pawns on the 7th rank. So instead I say if we have a pawn on the 7th rank, I'm also going to count a pawn that is on the 6th rank. So that's what this logic is doing. Okay, so here, very simple, the front square, okay, so in front of us, one square in front of us, if it is TDP'd, if the enemy has threat on that square and we don't defend it, then this is a passer deficit, okay? And if it's a front square and we are defending it, then it is passer supported, so the push is supported, right? Okay, so that's obviously, this is a penalty, and then this is a bonus. So here, if we are blocked physically blocked in the front in our path by an enemy piece, I simply give a penalty. If we are defended and about to promote, okay, so this is, it looks a bit complicated, but it's not. So this is once again saying if we are on the 7th rank and we are not on TDP, then we only then do we check this. So this is actually like I totally forgot about this. Yeah, this is my own idea, and I really like this idea, and I'm glad that I made it work. So this is I'm checking the promotion rank for our side, and I'm checking if they have a rook on the promotion rank. And I'm really happy that this gets signal. The idea behind this is we have a pawn that's about to promote, and their rook is stuck on our promotion rank trying to defend it. Now you may say, well, they are defending it, so why is this a penalty or a bonus for the promoting side? The idea is that when their rook is stuck on the promotion rank, they are basically they are losing a piece, right? Their rook cannot do anything else, right? And so maybe I should also make an extra condition here for the amount of material on the board, because that plays into it, right? It plays into the idea that them being down a rook, right? Of course, this is not going to matter if we don't have a rook, or something else. But if it's rook versus rook, right, and they are stuck at defending that square, right, we're able to we can move our king up to move that pawn eventually. And so this does come through in tuning, and this is an actual thing, and so that I'm happy about that. And okay, so here I'm checking if our rook is in front of our pawn that's about to promote. Okay, so that is the idea, right? So that's our rook is on the passer file. If we are on the rook file, right, and we are not on the in front file mask. So if we're behind the pawn is when I give this bonus. However, if otherwise, right, if R pause and then I check if we are on F square, what this is checking is if we are stuck, if our pawn is about to promote and our rook is stuck right in front of the pawn. This is a very common pattern when it comes to things like very occasionally you will get in mid game, right, our rook ends up traveling to the 7th rank or something like this, right? And then we progress the game, and then this rook is still in enemy territory, right? And so we end up pushing this passer, right, up and up and up and up and up. And the enemy may be pushing their passer down towards us, right? But the difference is that now our rook that was supporting that passer is stuck behind it, right? And they may be attacking the pawn, and so this rook cannot get away from the pawn, if we don't have a piece that can defend the passer, right? Because as soon as the rook gets out of the pawn, then they will take the pawn, and then we're going to lose the game because they have a passer. This is a scenario that happens actually surprisingly a lot, right? In these sorts of endgame scenarios. And so I wanted to make some sort of estimation of this, and so that's what this is, right? And so I give a bonus if we have the extra passers on 7, which we were counting, and then I only give this penalty about this, rook stuck in front, only if the passers on 7 is less than or equal to 1. Okay, and we have that PR count, which is exactly this. Okay, so I defer this after just to make sure, because if we have 2 passers on 7, once again, it doesn't matter that that our rook can't deal with this because we have another passer about to promote, so it just becomes noise. And so that's all my passer evaluation. So I'm happy that I got this stuff to work because this is it's really like kind of my original ideas in terms of this. So okay, now what else? Okay, evaluate king threat. This is the end. We are finally at the end. So what's going on here? My king safety used to be very, very, very different in the a serious way. I kind of want to see. Do I have it here? This might be too early even for this. So this was like the first version of my king safety, actually. Yeah, so this was where I still had it within the per piece material eval. Was we had these, I was literally per piece pop counting, which is extremely inefficient. All of these different masks, like king attack, safe king attack, double king attack, and not enemy attack mask, and not king moves enemy king square, right? All of these various things, and I was giving these bonuses based on the counts. While this gives you a very accurate eval, right, this is extremely inefficient, right? When you get to a mature search, your searching an extra few plies is way more valuable than you trying to solve these horizon issues yourself by having an accurate eval. Okay, that's a hard lesson to learn here. So all of these, like, seriously a lot here. And this was me kind of, you see here the sort of the war zone that this code base is of how I was scaling these things. So if we look here at what it used to be, I used to square my king threat value. Okay, meaning that, if it's little, it stays little, and if it's big, it gets really big. And the idea is that, we want to minimize the noise in, if our king is like, just a little bit not safe, and if your king is really in danger, you want that value to be overwhelming. So that was my idea here. I haven't gotten it to work with the Texel 2 and stuff though, and it's something that I want to keep in mind for the future. However, having this exponential king threat value is it will really mess with your pruning, with all your margins, because really large values are of course going to cause a lot of cutoffs and things like this. And so I would recommend that it also not even cause a lot of cutoffs, but it may just simply like break pruning, because your bounds just might become huge just out of the nature of it. So all of these things, enemy king defended squares, I was scaling these things by these values that I had SPRT'd and stuff. So a lot of hours has gone into making this engine. many hours. And so, going through this and like saying, oh, I took this idea from here, I took this idea from there, I eventually reached a point where I was starting to understand why other engines do it a specific way. So just because I reached this point where my engine has become an amalgamation of my own ideas and other people's ideas does not mean that it didn't start from a point of me, implementing and figuring it out all myself, because that was kind of foundational to my understanding of why all of these other choices are important, right? And so it may seem, I'm realizing when I talk through all this that it may seem like, oh, I took the easy way out by, copying this or copying that. Definitely not, a lot, quite like, probably like 1,000 hours has gone into this, to making this engine, thousands of lines of code. I actually, I have my face cam here, but, the raw line count of all of these files, is large, Okay, so what are we doing here? Okay, so we are evaluating our king threat. Okay, so this is the new version. So what I do here is I compute the check masks for wherever the king is, because we are going to see if our pieces have moves that can check the king. Okay, I already pre-compute this when I make a move. So this is completely redundant, and I have a to-do here to move that over. With everything inside of a chess engine, though, this is something I want to make clear. I'm going through this and I'm saying that, oh, I may want to make this change, I may want to make this change. Well, why not clean this up and finish this before you make this video? You've got to kind of understand that everything in a chess engine has to be tested. Okay, there have been so many times where I've made a change that just seems, completely like this was a piece of code that was redundant, and it should have been redundant, but it breaks something somewhere, that was unintended. Okay, and you may not even notice these things because it's usually not a seg fault. It's usually not some obvious assertion fail, some memory corruption. No, your chess engine will just start playing very poorly. Okay, and so you're gonna mentally have to like backtrack and figure out what could I have changed that could cause this. Okay, so if you don't test every line of code that you change, it's very dangerous. It's very dangerous. And you may say, you made a game engine, like a very complicated thing, you definitely had bugs like that. I did, but usually the entire world would turn black. The screen would go black, okay, and I wouldn't be able to compile. In a chess engine, it's a different, you often get different types of bugs, okay? So moving on. Weak square. So weak square is, I define it as where we have attacks where they are not double attacking, and not attack mass for the not side, and or attack mass piece not side queen, or attack mass. Okay, so what's happening here is, this is kind of complicated. So what's happening here is we are removing the queen and the king attack masks. I'm just checking if this is correct. This should be correct. I've looked over this a billion times, but it looks very convoluted right now. Our attack mask and not the double attack mask for their side, and the not attack mask for not side, or yeah, I think that this logically works. It just looks very confusing. It just looks confusing, but it is sound what's happening here. It is confusing though. So it's not the attack mask for their side, or the attack mask for their queen, or their attack mask for their king. So I believe that this could be written a different way, where we could just like literally yeah, so this, no, it couldn't be written a different way. It just looks confusing. Okay, so we're saying we attack those squares, they don't double attack them, or they attack them, they don't attack them, or they attack them with a queen or a king only. Okay, so that's what we're saying here. It looks convoluted. It kind of is, right? So we're saying we attack that square, they don't attack it double, and they attack it only with a queen or a king, you know, or else it's not defended. So that's what that is, and the reason why this queen or a king thing is there is because that often will be, you know, dangerous for them to attack it with a queen or a king, especially when it's in relation to king safety, right? So that's why that's there. Okay, so I define safe as the TDP for their side. Okay, so mask that we have a threat, they have a threat deficit, right? So our safe attacks, I define it as weak squares in the enemy king zone. Now, what is enemy king zone? Okay, I could print this out. I could go to Bitboard Viewer. I think I will just do that. And this is all of the gradient descent stuff that I'm going to be, you know, walking through later. But yeah, so let's go to the Bitboard Viewer so that I can, okay, flashbang. Okay, so let's say we are white, and so we're going to be at this side of the board, okay? And let's say our king is on this square. I'm just going to put it there, okay? So the king zone in my engine is this. This is the king zone, okay? So it is just the 8 squares around it and 2 in the front. What it used to be was actually just a massive square right here, like this. This is what it used to be. However, I was reluctant for a long time to do this, okay? Even though I kind of knew in the back of my head that it probably made sense to do it that way. Just out of stubbornness, I had this like, oh, but what if the king gets attacked on the side, you know, on the flank? Mainly what king safety is for mid game. King safety in endgame, in endgame scenarios, you're going to notice your engine starts searching, you know, goes to depth 20, depth 30, right? Because there are less pieces on the board, there's less going on, okay? It can really see past the horizon, okay? During mid-game, there's a lot of complexity, there's a lot of stuff going on, and so that horizon matters more. And so when we do king safety, we're mainly looking at that mid-game, and so only these squares are really the extent that matters. Okay, you can think of a king, you know, is castled, right? A king is castled over here, you know, maybe it's here or here. You know, when it's white, it would be, you know, here, right? And so a king is castled here, and so this would be what our king safety is right now. This is just noise, right? This is just noise. Let's say they have an enemy knight here or something, right? This is not at all like a threat on the king, and so this is just noise. This is not noise though when, let's say, they have a bishop that comes over here and the queen is here, right? You know, so these squares start mattering a lot more. Okay, so the front two ranks of a king are, you know, very important for king safety, and that's why we have a king zone. Okay, so that's how I would explain it, and that what my engine used to do this. Okay, because, you know, like, what if a rook comes downtown, you know, or whatever, you know. However, you will usually see past that in Horizon, and it just introduces a lot of, as you can see, the amount of times I tried to tune that with, you know, enemy king defenders times 2.7 or whatever, you know. You it's really hard to tune with a king zone like that. Anyway, I hope that explains to you that's what my king zone looks like. So when I refer to king zone, that's what that is. So it's the weak squares. We attack. By the way, my king safety is king threat. So this is from the aggressor side. Okay, so the attacking side. So every time I do not side, I'm talking about the defending side. Okay, so right. So this is our safe attacks against the king zone, and so double safe is we have double attacks that are also safe, which I then subtract, right? And so the idea is that they are worth more. Okay, and so just like this, I bucket them like everything else. We're going to talk about the bucketing later when we get into extracting your features for Texel tuning, but this is how I do them, right? Just two separate scores here. So that's that. Those, once again, going back to my old implementation, right? These were historically, right, the things that I did per piece, right, were double king attacks, double safe king attacks, right? Now they are just simply, now they aren't actually the main part of king safety. They're really just there to represent the overall presence that we have in the king zone. Okay, so they're not the main thing. The main thing is actually safe and unsafe checks. It's pretty much the same for each piece, except for rooks and queens are different because we treat contact checks there. So basically we're just going through the attack masks and just checking against our piece mask for each piece that we computed earlier, if it's a safe check or an unsafe check. Okay, and then adding the scores. So that's all of this going down. And rooks and queens are different though. Okay, and I'm going to try to explain it because it's a bit complicated how I determine if a contact check exists, and possible room for improvement in my rook contact checks. Okay, so we are checking if, by definition, a contact check has to be obviously contacting the king within the king move. So that's just what this first part is. We are ending this with the not masks of the attack mask not king for the not side, and our attack mask for our side. Okay, so this is wrong, right? So this is why I have a to-do here for this very reason. This technically, in my logic, but I have to test it, should be double attack. The reason why is because we already attacked this square with the rook, right? So it isn't actually a safe square for us to go to. Okay, so the attack mask not king, right, is basically similar to the weak squares. Okay, it's similar to the weak squares, except a few things are different. It's just it isn't defended by something that isn't the king. However, if we want to do this, we probably should have it double attack, because then it might just say that we have a rook check that isn't actually defended. It's only defended by the rook itself. Okay, so that's possible. I have to work on that. So that's that contact check. The queen contact check uses that X-ray bitboard that I talked about earlier. Okay, so it is the queen check, right? And if it's a contact check, right? And once again, this, right? AM and K, and we defend it, or right, it is or it lies on the X-ray and Q side, and so yeah, so this QM, I was just making sure, is the Q check and the king move. So exactly where we are contact checking. So we are checking, hey, is this backed up with the X-ray, right? So yeah, I think possibly it should be something more like this. Okay. Possibly something more like that. I'm going to have to take a look at it later, because it is an interesting way of formulating it for sure. It kind of makes sense. But I think you may also want attack mass no king not side over here. So it's something I may have to go later and see. But yeah, a lot of this stuff I've iterated on just to the point where it comes through in Texel. So yeah, so I'm still working on that. But yeah, so that's the condition of the way it is now. But it used to be just like if R check and king moves in safe, right? But it was, saying that a queen contact check wasn't important. And if we go to it now, it well, this is very a rough thing. The queen contact check for endgame, I mean, hopefully it comes through. Yeah, so 52, which is pretty large, very, very large, right? So that's what that's about. Okay, so we have a correction for hanging pieces here. So this is my idea. Okay, basically I had this bonus for pieces that attack the king zone, right? This is what this AKZ is. KS AKZ, king safety, attackers to the king zone. So this is per piece, index per piece. Each piece has a different, threat value, right? So a queen would be very dangerous. But I only count it if the piece is not hanging. Okay, this is very important. In chess, in chess programming, you're going to get a lot of, noise, random positions that your queen is going to be hanging right in front of the king, and yeah, that's going to have such an insanely large threat value. It's going to make the score go into the bazillions, right? However, the queen is just hanging. The queen is just straight up hanging, and so that's what this is intending, right? Is if our piece is hanging, we're going to give a penalty, but also not count this contribution to attacking in the king zone. So that is what that is, and it comes through here. KS threat correction. You see that these are negative values. Now this is a positive value, but mainly it comes through, right? So mainly it comes through. So once again, you may have biases in your, we'll get into it later, but Okay, so that's what this is. Also, the main part of it isn't only the penalty, but also just avoiding giving the threat value. Okay. So once again, we iterate through the piece list and use those piece attacks again. It is possible, it's entirely possible that you could just move this into the per piece evaluation as well. But I prefer to keep everything in the same place. Okay. So this is kind of, we're going to go through it and figure out what's happening here. So this is, the bottom, and us also fighting back against the king threat. We're saying, hey, is the king just safe though? Like, do all of these, bonuses that we've applied, we're scaling them back based on how safe the king is. Okay. So the empty squares that a king can escape to, that's what this is measuring. We're measuring, can the king escape to any squares? And if so, we are, this is giving a negative value, right? Since it's the aggressor's side, based on how many of those exist, right? For the defended squares, we are simply saying, this is, I've iterated on this a bunch, but the attack mass without the king inside of the enemy king zone, right? We're defending it with other pieces, or within the king moves, and not attack mask for the side. Okay, so this is us saying the king can defend itself as long as it isn't attacked, right? The idea is a king can't actually capture a piece or enter into that square or defend that square or whatever if it's attacked by the enemy, right? So that's what this is, right? If it attacks the squares around itself, the king, then that's fine as long as it isn't attacked by a pawn. So that's attack mass no king, right? And then the rest is, attack mass no king. So that's good. Okay, so pawn shield is self-explanatory. I have masks, right? This is just going to be, I closed the bitboard viewer, but just the, the 3 pawns in front of a king. Okay, pretty self-explanatory. That, of course, is going to be a negative value if he has, more. You can see down here, the pawn shield, right? At just 1, it is a positive value for the aggressing side, and then a negative value since he's safe with 3 pawns. So that's why. Okay, so weak squares. Okay, so this is double attack squares next to the king. We're counting if there's more than 1. Okay, so if they have double attack squares, and it isn't defended by the not king, and it's within the 8 around the king, then this is dangerous. And as you can see here, this is, we get very good signal here. So this is 15 centipawns, right? That's a pretty big value, right? Okay, so the last thing is simply attackers in the king zone. Every non-pawn we have inside of the king zone, I just give a bonus for that. So this is all the bucketing that I have, right? So we just sum all of them up, and yeah, that's quite literally it. I return all of these scores. I add them up, add them all up, and then once again, since we have them in a 32-bit integer, both mid-game and end-game, what I do here is I have a macro that just shifts the bits over, and then and splits it up, and there we go. Then we just interpolate this. This is using the standard interpolation formula on the chess programming wiki that everybody uses to interpolate between mid-game and end-game phase. Okay, and there you go. That's it. And then we add it to our core hist and then return. Okay, so where's core hist? Well, core hist is very simple. Core hist is exactly what we were talking about earlier, where we were updating our core hist from our search. So all we're doing is retrieving it here, and we index into it the exact same way using our hash keys and using the core hist mask, which is once again hashing. The mask is going to be 1 minus the size of your table, and so that's exactly what's happening here. And yeah, that's pretty much it. So yeah, I mean, I think that that's all of eval. We've gone through all of it. We have, I hope that I've explained everything properly. I've explained everything good. Okay, so I'm back. This is going to be the hardest part of explaining all of this. And so I've taken some time to refresh my mind and try to make sure, even if I don't understand it fully, that I can give some sort of picture of what you're working towards if you choose to implement this stuff yourself. I'm going to be walking through my own Texel tuner using Atom and SGD, using momentum, decoupled weight decay, and warm restarts. What does all this mean? We'll get into this in a second. I'm also going to be walking you through my SPSA tuner, which plays games with my engine against itself and sets parameters up that change during the training run. So I'm going to be walking you through both of these things. However, during this last section of the marathon of all of this, I want to be absolutely clear that I'm no expert when it comes to all of this, and I may be doing this wrong, okay? But I urge anyone, especially at this point in the video, to correct me if I get any of this stuff wrong. I am coming at you being honest here with the fact that the documentation and the written evidence for all of this math is not only impenetrable and very difficult to understand, but also it relies on a chain of understanding of math, and also these arcs of papers that we're going to run into already assume that you understand the basics of gradient descent and regularization, and so often they will simply leave out important terms. And how do you even get to the point of calculating a gradient? How do you calculate the loss, right? These papers are completely going to skip over that because they assume that you know this. Not only are they assuming that you know this, but they are all the examples that you're going to look up. Can I get some example code? And it's just going to call a Python library. Okay, and so things like this are make the whole thing very difficult to understand, because you're going to be looking at example code and it's simply going to call PyTorch or whatever to calculate the loss, man. Just do it. Here's how you do it. Okay, first, before we get into what's happening here, we need to do two things. We need to parse and choose a data set, and then we need to create feature extractions for our entire evaluation. So let me give an introduction. So Texel tuning, okay, is how mainly we do our evaluation in chess programming and in tuning it. It is the easiest way with an extremely large feature set to do something like this, right? With SPSA, it is, incredibly would be incredibly taxing to play that many games, right? Though some big engines do choose to do SPSA, okay, but what I recommend, is to do Texel tuning and to create a Texel tuner. There are also, many of these external tools, external libraries that implement things that are similar to what I'm going to be talking about here. Like chess tuning tools, or I think I've seen a few of these things around that have, their own algorithms and optimizers. The good thing about implementing your own is that you have 100% control over what you're going to do, and if you choose to implement this or implement that, you can you have control over that yourself. So okay, and it's also very interesting to learn about all of this and figure it out. So without further ado, let us choose and parse our data set. So out of the ones that are available, if you don't want to, make your own data set, I suggest personally to choose a data set that is for computer chess, okay? I've seen recommended, the Lichess Big 3 data set, the Zurichess Quiet labeled positions. I'm going to recommend the Andrew Grant, I think his name is, the ethereal positions. I will perhaps put a link in the description to those. They are fantastic. I've gotten the best results out of them, actually, and yeah, they are large data sets of 10 million plus positions, and I believe that there's 4 of them. And so you can combine them. You can try 1 or 2 out. The problem with Texel tuning that you're going to find is that it's data set dependent. There are biases, even in the 10 million, 50 million positions. There are biases that come out, and unlike with SPSA, which is why I love SPSA, it is not data set dependent. It is this. We aren't just looking at the features themselves. We are manipulating things and actually playing the games out, and so. This is the difference. Texel tuning and gradient descent is about correlation, and SPSA is about causation. Okay, so to get into this, so all I do is I take in to my tuner the path to the data set that I am going to train with, and then I just go to parse. Okay, and I set up a data set which is literally just a struct with an array of entries inside of it. Okay, and the entries inside of it are literally they just have fens and results. Okay, so that's all an entry has, is a fen and a result. Okay, so all I'm doing here is I'm vectorizing, I malloc it, real quick and dirty, and then I realloc down here. This is just typical vector stuff, right? In C we don't do that, so we just realloc. Okay, so if the count plus 1 is greater than the capacity, then I just reallocate that based on the capacity plus 2 times 2. Is typically how I do it, and then I just realloc the entries pointer to the size of the entry times the capacity. This is the typical pattern, right? Okay, so I have 2 different parsing things here. Some data sets will have different notations. Okay, so the one that I will be talking about today, the ethereal data set, has these brackets. Okay, that are next to the result. Okay, so it's inside of these brackets, so that's why I tokenize based on that bracket, and then all I'm doing here is I am using stritod to get that result. Okay, and you may have your data set in a different a different format, maybe it's -1 win for black, etc. Typically, they are 0 as a win for black, 0.5 as a draw, and 1 is a win for white. And so the code, you're going to have to keep that in mind, that my code assumes that is what the result is that is stored inside of this result entry. So it's important that you just copy in the fen that you get and then use the result. So that is what is happening here. And so that's how we parse the data set on initialization. So how I do this is I simply call this function from within my engine, with a certain directory, a certain path, to an EPD or a .book with all the positions, and then read them in like so. Okay, and I do that before we start calling our tuner. Next thing I do is I initialize my param index. I talked about this before. The param index is how it's kind of like a guidebook into the feature array of what lives where. Okay, so this is what the param index looks like. Okay, everything in the param index is just a feature, right? So I go through all of the features that I'm going to be tuning, and I just increment k, and then at the end, that's the amount of my parameters. And while I am simply setting the param index for each one to k. Okay, so basically what's happening here is now the param index, isolated upon I, will point into the exact feature that inside of that massive array. Okay, this is a way so that we can use an array and not have to have a struct full of all this messiness, because we just want to iterate through the array regardless of what parameter it is, and do dot products and etc. that we're going to get into when we talk about the actual gradient descent. So that is necessary, right, for you to go through, do all of this with all of the features that you are going to tune. This is how I do it, how I've always done it. It is maybe painful to set up once, right? But after you set it up once, to add something isn't that painful. Okay, so there's that. So that you build that param index. Okay, now you want to allocate some buffers to the amount of your total parameters that we just went over. Okay, and what I'm going to go over now is the setup. What I would say the setup. So important here, okay, is some level of macro. Okay, I've really gotten over my fear of C macros thanks to this. Okay, it is very important that you have some way to see your weights, to get them printed out. Okay, and a perfect way to go about this, an elegant way, is a C macro. Okay, so the way my macro works, right, is I take in the weight array of all of the current weights, right? You're going to have one for mg and one for eg. Okay, so you're just going to take that into this function, and the param index is going to use whatever name you set here. Okay, and it is this name that you're taking into this function. So say it's the parameter of doubled pawn, right? The cool thing about a C macro is that you can just literally have the name here, and so that becomes your member of your struct that you're referring to, right? And you can also use the pound sign name to print it out as a string, right? And so when you call this with doubled pawn, it's going to say, your string of doubled pawn equals this, and then it will index into via the name. Similarly, with a loop, we can set up a very similar thing where we take in a name of some piece values, okay, and you set it up there, and you take in a count, and you're just looping through the count. But the same idea here, you can use that to take the member of the param index struct. This is just such a elegant way of going about this, and I was always so afraid of C macros and stuff, and this is just it's made me want to use them all the time. So many times inside of my code that I could have used a macro, but I didn't. And so this is this will show you, it will give you an error if you do something like this. So anyway, so I think that's super neat, and it'll print out like this. This is exactly I have multiple different functions, some that print out in integers, some that fprint to a file. I do checkpoints, so I print out to a file every like 10 epochs or whatever. And so it's very important that you have that, because you may want to stop early or something like this. So I highly recommend you set that up, if not beforehand, but just keep it in mind during. Okay, so we're getting into, I have two functions here. One called SGD, stochastic gradient descent, okay, and one named atom, which is something about moments, okay. So how do we prepare to do these things? Well, let's just go into here and see. So first of all, we need to figure out how we are going to loop through, okay? And so a big part of this is going to be extracting your features. Okay, so I'm going to go to extract features, okay? And this is just going to be an exact mirror of your evaluation, okay? Except we are not putting values into a vector as in scores. We are simply going to be using binary ones and zeros to represent the feature set. We are not going to be giving any values. We are going to let the optimizer itself figure out the weights, okay? So how do we do this? Well, what we're going to do is kind of like we are going to observe. We are going to take a position and we are going to observe the features on the board. We're going to say, this feature exists here, this feature exists here, okay? That's all we are doing. So we have an input vector called xi, and I have it as int 8t, okay? The reason why I have it int 8t is just to enforce the fact that this should never have any sort of precise value inside of it. It should always be an integer, okay? Now, maybe a caveat here is, at least this is what I have found success with, is just having it as an integer, as integers, okay? So just going through, I'm not going to go through exactly 100% of everything here, because it would be just regurgitating, okay? We're just going to take a look at what I mean when I'm talking about this. Okay, so for example, when we're extracting PSQT features, all I do is I look, okay, does this piece exist here? Then I put it at a 1. Here's also a thing you're going to notice, okay? We are putting -1 for black, +1 for white. This is important to have this symmetry, okay? Otherwise, obviously, it won't work, because what we've talked about earlier, this is the reason why we have results as, -1, or, 0 is black, 1 is white. We want to know which one has which feature, okay? Or else the sign is going to get switched. And I was pulling my hair out when it came to this earlier. So this is what I'm doing here, saying if our color is white, then we have 1. If it's -1, if it's black, then we have -1, okay? So for everything, I'm going and I'm using this pattern, okay? So some things I won't have as perfectly binary. For example, piece values. Piece values, due to the nature of us needing to incrementalize material, I have this simply as one thing where it's the piece values of one piece, I add 1, and that might be 2 sometimes. But for the most part, I try to bucket as much as possible. Now, what do I mean by bucketing? Okay, so let's go down and let's try and see if we can find a bucket. We can find a bucket. Okay, there's none here, none here, none here. Okay, a good example is this. So this is a bucket. Maybe it's not the craziest bucket of all time, but I'm bucketing by rank. Okay, so when you look at when I count my backward pawns, right? This sign, by the way, is simply -1 if the side is black, and then this is the same thing as me doing this, right? -1 is black, +1 is white. It's just we don't do it in line here. It's just don't do it. So what's happening here is I'm just simply indexing it by rank, right? And it's a different feature inside of the feature vector that isn't at all tied to the other ranks, okay? It's just a completely separate feature, okay? And it's the same thing here. I'm bucketing based on these edefs, okay? I am bucketing based on these save pawn push attacks, right? I am saying if it's this count, it lives here in the array. What this looks like, these are all buckets, okay? Mobility, bucketed, okay? So, excuse me, I have a bucket. These buckets are way larger than they need to be, but I have a bucket of 64, okay? And if a knight has just no mobility, it's here. And if a knight has like this many moves, and then it ends up here, okay? So we don't like add plus equals 6 to the feature vector. Now why? We want to keep our features as normalized as possible. I've gotten much better results when trying to keep features between 0 and 1 as much as possible. Okay, now sometimes we break that rule. But it's just what I've observed. Okay, and I've ran into some real problems with scaling when certain features are outside of that. So I hope that helps you out. So that's what we're doing. We are extracting our features. So before that, what we do is we just set our board to that fen inside of that data set, and then we just go through and we extract all of our features into a brand new xi. Okay, and that feature vector just has everything inside of it that I just went over, and we're gonna do this. Obviously this is exactly what we saw earlier in my evaluation. We are just mirroring exactly what we use in the evaluation in these functions to extract these features. And yes, it is an absolute pain in the ass. I'm not going to sugarcoat it. It really is. But once you set it up once, it becomes easier. But I had to set it up twice because my evaluation, I tried once and then failed with Texel tuning, and then later I returned to it with a completely different eval, and I had to start from scratch. So Yes, I sympathize with you. It's a pain in the fucking ass. It really is. Okay, I'm not going to sugarcoat it. Okay, so I want to talk about standard SGD first. Okay, standard SGD. Now, unfortunately, there is no real, ArcSiv paper for us to follow along with when it comes to just standard gradient descent. Okay, because this algorithm has been, around for such a long time. It's kind of, hard to find one. However, I'm going to be talking about my current implementation, okay, what I recommend, and we will be looking at the formula for momentum, okay? So let's talk about the parameters first, okay? So lambda is your weight, okay? So your weight typically is decaying, okay? What this is doing, it's what they call L2 regularization, okay? I'm not really sure why it's that fancy of a term, but what it does is it apparently regularizes your weights. I had to guess it's making smoother gradients, trying to combat noise and bias. A lot of what these machine learning things are doing is trying to combat dataset noise. Okay, now a big part of SGD inherently is combating noise, which is the whole point of these batches. Okay, SGD is all about batching. What is batching? Well, batching is taking a portion of the dataset and calculating the gradient over that, rather than just using the gradient at a batch size of 1, right? Which is non-stochastic gradient descent, as far as I understand it, right? Is that a batch size of 1 is like pure gradient descent, right? And you can see the immediate effects this will have on you if you try a batch size of 1, right? It makes your weights crazy, right? So the idea is that we are calculating the gradient over a greater portion of the data set to combat that noise. Okay, so that's what that batch size is. Okay, now what is LR? LR is learning rate. Okay, so learning rate is, from what I understand it is scaling our contribution from our current time step into the weights. Okay, so it is how we scale things when we are adding a new contribution. Okay, so a higher LR will learn faster, but it may may be really hard to converge because of how much you're changing per time step. Okay, so when you have a smaller LR, yes, it's going to take longer to maybe it won't take longer to converge, but the idea is that training might take longer, but you will reach convergence, right? I guess in a you're guaranteed, okay, to reach convergence with a low LR. Okay, so those are the concepts. Okay, once again, I'm no expert. Okay, I've just tried to understand. Okay, so we're gonna want some arrays. We want the gradients and we want the weights which we are passing in, right? It's doubles, and we want our feature set. Okay, now this M, what is this M here? What is this M? This M is momentum. Okay, so what this is actually SGD with momentum. Okay, so standard SGD will look different than what I'm about to show you, but the idea is the same, and the regularization is actually the same. I do not have decoupled weight in this implementation. So, okay. So what is this? So coming down here is my learning rate scheduler. Okay, there are many different schedulers for learning rate, and you can search them up yourself. Perhaps I shouldn't even get into this yet, but basically it helps convergence when the learning rate decays over time. The idea is that in the beginning you're trying to find the ballpark, right? And then once you've found the ballpark, you need to slow down so you can get those finer tunes to the point where you can converge. What is convergence? Convergence is the point where we stop losing. We stop, the loss stops. So what is this? Okay, so this is warm restarts. Okay, I implemented this because I really like the idea. Okay, I'm not sure what the performance is like. It's hard to really quantify if it's good or not, but I really like the idea. So, and I really want to implement something similar in SPSA. I had this idea, from working on my SPSA, I had this kind of idea of like, what if we did a zoom out, and in the same way, SPSA also has this sort of decaying learning rate. What if we took a zoom out as well? That's what warm restarts are. Okay, so we have found the ballpark, right, and we are settling down, right? And then what warm restarts do is that it jumps the learning rate back up. Okay, it jumps it back up. Now, why isn't this undoing our progress? It is possible that some of our weights have settled into suboptimal strata, and so what warm restarts is doing is it's jumping us back up momentarily, and it's saying, okay, let's see if we settle down into the same sort of position, so the idea is that we are jostling, introducing noise momentarily to maybe we find a new spot that previously we were blind to because we had already optimized into a certain area. I see the same problem really with SPSA, where at some point we settle down into maybe a suboptimal place, but then everything else starts to optimize around that suboptimal place, right? And so I have this idea that maybe it may be something similar that may have some merit. But anyway, that's what warm restarts are, okay? And so basically what's happening here is we have a t. Mine is initialized at 10, okay? And that is the amount of epochs that I like epochs. Is it epochs? I think it's epochs. Anyway, we have a t, which is going to be the amount of time till our next restart. Okay, and so we increase up until that t, and then we reset our count, and then double the t for next time. This is how they talk about it in their paper. And also they mention that it may be optimal to decrease the learning rate as well. So the idea is that you have this maximum and this minimum, that you are using this cosine to to smoothly sort of interpolate between them in this sort of pattern. And so the pattern kind of looks like, this sort of thing. So every time I do a restart, I decrease both of the learning rates. And the idea is that every time we zoom out, right, we're just going, we're getting closer and closer and closer and closer and closer to the bottom, right? So that's how you implement it. All you do is you increase this, this count every epoch you do, and then once you hit that variable, then you just multiply times 2, or you don't have to. But this is, I'm trying to find, which paper is this? Which paper is this? This one. So this is the exact formula here. Okay. This is the exact formula. This is, exactly what I use. And you can read it here. So based on their graphs, and what they found, I took, the t equals 10, t mult is 2, because it seemed to be the one that really performed the best, especially when I do my training. I do it probably to like 200 to 500 epochs. So having a T of 100 is already so large that you're only going to have one restart. And so since I like the idea, I like to have a lot of restarts. So that's what that's about. I hope that I'm explaining it right, though. I am kind of dumb, but yeah. Okay, so you want to shuffle your data set, okay? So to do so, I just literally just shuffle the pointers around. Okay, so you want to have some level of randomness. The reason why, apparently it's just how SGD works, where okay, so here's really why, is because of the way batches work, right? Is that we are calculating the gradient over some number of data samples, right? And so if we are, every iteration through the data set, if we are starting and ending at the exact same place, right, the gradients will always be the same. And so there's some level of bias there that we are trying to get rid of by shuffling the data set. At least this is, once again, as far as I know, is different. So we have, our weights that we are, working on. That's all of these weights, okay? So we have these weights and we are dotting them with the features, okay? So what is this? What is this? Okay, so let's explain what our goal is with gradient descent and all of these others. So with gradient descent, we are essentially trying to minimize loss, okay? We're trying to minimize loss. And so we are trying to estimate here our evaluation, okay? So that is why we are taking our current weights that we have been working on and we are multiplying them times the features, okay? This is why it is important for your Z to be normalized, that we were talking about earlier. Try and keep it to, very, very small values, right? That's the point, is that eventually we're going to dot it and try and figure out what our current evaluation would look like, okay, based on our current weights. That's why it's important for you to match your extraction exactly with your evaluation, okay? So given all of this, I'm sorry, I'm speaking low because my voice is going out. Okay, so now we get our eval. So how do we calculate this eval? Why are we interpolating by phase here? So we have our weights in two separate, we are processing them separately because, you have your mid-game weights and your end-game weights. It's important for us to have these for a tapered evaluation, okay? what is happening here is we need to, just like when we evaluate, right? Just like when we evaluate right here, right? When we evaluate, right, we have this score, right? And now we have to separate to interpolate, right? To come together and then, have a score to give out, to return, right? And so that's what's happening here, is we are coming together to one value, and that's why we are interpolating them separately, right? So this is the mid-game phase, and this is the end-game phase. Okay, so that is what's happening here. And now we take the logistic. This is the sigmoid function, okay? This is what it's used in terms of probabilistic loss. This is the more modern version. Other engines also use mean square error, which you can look at yourself. But this is the sigmoid function, okay? So we are taking the logistic and then we subtract our result. This gives us the loss. So the result, once again, is that value that we got from the data set that is going to be 0 to 1. 0 black loss, 0.5 is a draw, and then 1 is the white win. Okay, so that's that. Okay, so what are we doing here now? What are we doing here now? This is so confusing. Okay, so what's happening here is we are now diverging again. Okay, so we have now the loss for the entire, for this step. Okay, we have the loss, and now we are saying, okay, we want to now re-diverge, right? By saying, okay, so we are multiplying our phase times this feature set to get the MG versus get the EG again. It's doing the opposite of this, where we came together, our weights were separate and our dots were separate. We came together to get the eval. Now that we have that one value, we have to separate again to get to start accumulating two different gradients. Okay, very important. I got this wrong the first time I tried to do this. I didn't, separate. I was just finding the eval was just, the dots, and I didn't really get how to separate the mid-game and end-game things. So that's how that works. Okay, so how do we process a batch? Okay, so this is gradient descent. This is a batch. Okay, so when we reach our batch size, or when we reach the end of a data set, we want to process a batch. Okay, once again, we are processing a batch to eliminate noise, right? To accumulate the gradient over a portion of the data set. Okay, and that's exactly what's happening here. Okay, so why do we divide by the batch position? By the batch position. Okay, so we are dividing by the size of the batch. Okay, you can imagine this right now as batch size. Okay, the reason why we do batch position and not batch size is because we could be doing a small batch at the end of the data set if this condition is true. Okay, so that's why we use batch position. We are saying the gradient, and we are dividing it by how big the batch is that we are processing. So we do that, and then we are adding our L2 regularization for our current weights. Okay, so what is L2 regularization? Okay, so it is omitted here. This is the paper on SGD with momentum, okay, which is what I'm talking about right now. It is omitted here. It is common in SGD to apply L2 regularization, especially in terms of the chess programming discourse. Okay, so L2 regularization it's literally just this constant lambda that gets multiplied times our current weight, okay, which just weighs down the gradient a little bit. Okay. So what is this momentum that's happening here? Okay, so this mu is a 0.9 constant. It is pretty common to use 0.9 in most of the machine learning libraries. It is multiplied times the current momentum, and then you add the gradient, okay, and then you subtract this, subtract the weight minus the momentum times the learning rate. Okay, so what is this doing, mathematically, right? It's kind of confusing even to me. It's kind of like adding another dimension of growth onto it, right? So we are calculating the gradient over a certain portion of the data set and then processing that batch. Now we are storing into this other, variable that is growing what that gradient was, right? We are adding the gradient and then shrinking the current stored value of the momentum, and basically adding a new contribution, okay? And then we are subtracting it from the current weights. So this is complicated to explain, but basically we are growing a momentum. We are saying we are going in a certain direction over the batches themselves, okay? We are shrinking our current momentum and then adding the new direction of the current batch, and then it's a gradient over a gradient, I guess. At least that's how I understand it. You can read the paper for yourself. All of the arcs of papers that I'm going to be talking about, I'm going to leave in the description of the video. Okay, so this is the paper. Helps acceleration when the effective learning rates and the batch sizes are large. Okay, which I do kind of use large batch sizes when I do these tuning runs. Okay, so this is SGDM, and this is what I have here. So I hope that this is correct and this makes sense. After this, we clear out the gradient so that the next batch is clean. I also reset the momentum during warm restarts. I read this somewhere. I'm not sure if it's correct. I've tried it both ways. Haven't really noticed a difference, to be honest. So yeah, you want to reset your gradient, of course, every time you go into a new epoch, and of course reset your z. Okay, so we got through gradient descent, part 1. Now I'm going to talk about atom a little bit. Atom I'm more fuzzy on. I've quite literally just copied the formula, right? Atom is a faster optimizer for gradient descent. However, there are discourses surrounding if it generalizes worse than standard gradient descent, stochastic gradient descent, and so it's up to you if you want to use it or not. But I have used atom with decoupled weight decay, which is what I'm going to talk about next. So this was gradient descent, and now hi, it's editor Dust Mite here to admit that I did a really bad job on the section on atom, and listening back to it, I just realized, wow, I sound like I make no sense, okay? And so I've come back to it, adaptive moment estimation. I have an acute dislike for engineers and scientists, okay? They are the bourgeoisie in disguise, okay? We got moments that are actually means. We got moments that are actually variants, okay? Moments are very interesting ways of saying this. The wonderful songwriter Patty McAloon has a song about this very phenomenon called technique, okay? I implore you to to listen to the song, and maybe you'll understand what the lyrics are conveying in this context in terms of her husband works in Jodel Bank. He's home late in the morning. Okay. The video is 11 hours long. Okay. So I'm going to try to explain Atom to a better degree. What Atom is looking to solve in terms of just regular vanilla SGD, and why it is important and why it's so widely used, okay, as an optimizer. Atom is much like we talked about with SGD with momentum. We have these maybe it was silly in my idea of saying we are accumulating a gradient on top of a gradient. It's not really, okay, because a gradient implies, the very purpose of what we are going to use it for. Nonetheless, I was kind of correct in the idea of this momentum as we are adding contributions of each gradient into itself. The paper on the Atom optimizer talks about the two moments, okay, which are M and V, as similar to what I am describing. And we will look at the code here and talk about, what I think about it, and try to decode what it means in, human language. Okay, so in terms of the warm restarts, these are the settings. I've already discussed warm restarts. These are the settings that I have found to best be used, at least for my purposes. Okay, so a T of 20 and a bigger LR decay. Typically with Atom, you are going to have a smaller LR than with SGD. It just, the way it works out, you end up having higher values right out the gate, okay? And so 0.001 is a typical one, and mine has a min of 0.0001, okay? So those are the settings for my warm restarts, okay, and 0.8 is my decay. Okay, everything else in the middle here with us taking the logistic and accumulating into the gradient is absolutely all exactly the same. Okay, we are taking our weights, dotting it with the current features that we have discovered for this position. We are making a pseudo eval with that, and we are getting the loss, and then we diverge again by using the loss times the phase to diverge into MG and EG again. Okay, so that's what that is doing. We are getting the batch position again, and we are doing a batch, okay, by batch size or with to the end of the data set if we reach the end, okay? Now you may see here I have these commented out. This was me testing the alternative version of the few lines of the bottom of the algorithm that they should suggest could be replaced by this, okay? Theoretically, they should be equivalent. but just for, explaining this, I'm just going to go with the more explicit version. Okay, so we are basically doing it twice, one for MG and one for EG. So don't be confused with this. Just the top is this is all MG, and then this is all EG, right? Okay, so this inverse BS, okay, it's just how they write it for optimizing, right? Instead of dividing, it's faster to multiply times the reciprocal. So this is how they write it. Okay, so let's look at the algorithm itself. Okay, so this is matching exactly what we have. Okay, so this BT, okay, that's the correction beta, which is beta 1 and beta 2 to the power of t, which is t is the time step. Okay, it's just the amount of batches that we have processed. Okay, and that's what this is. This t is simply getting increased every time we process a batch and we make a new correction. Okay, so the idea is that as we continue going, these betas are going to get bigger and bigger. Okay, because it's going to the power of t. Okay, so we get the gradient in the exact same way. Now you may notice that our lambda times the weight is removed from here, and that's because we're doing what's called decoupled weight decay. I'm just going to explain everything else and then explain the decoupled weight decay. Okay, so very similarly to SGD with momentum, okay, we are adding the gradient into this this array. Okay, so this beta 1, okay, which is a constant of 0.9, does not change. Okay, times the current momentum. Okay, so what is this doing? This is doing exactly what we just saw in SGD with momentum, where we are scaling back our current contribution and then adding this new gradient. Okay, and this is being multiplied times the inverse of this beta 1. Okay, and so in this case, what that beta 1 is of course the inverse of this would be a 0.1. Okay, so what this is doing is it's scaling back our contribution, our new contribution, to equal into these two halves, right? So we have the 0.9 times our current value, and then we do the 0.1 times the gradient. Okay, and we add these two together. Okay, so if I had to give some inference into what this is doing, this is simply giving some sort of interior control over the amount we are changing per batch. Okay, so very similarly, the exact same thing is happening in the V, which I believe that this is what they refer to as the second moment, which is the variance. Okay, so that's why it's V. So M is actually mean in this case, and the V is, I believe they call it the uncentered variance, which is the gradient squared here. Beta 2 is 0.999, so really tight. And in my opinion, it makes sense since we are already squaring the gradient. Okay, and what squaring does, right, is that the smaller the values are, the smaller the squaring is going to change the value, the bigger it's going to amplify it. okay? And so the variance is, inherently trying to find the outliers, okay? So that's why the gradient times the gradient, right? The bigger values are going to have a much bigger contribution, okay? So that's my kind of inference into what is happening here and why it is valuable. Now, I also want to give the observation that I have found it better to never clear either of these arrays on a warm restart in Atom. Why this is, I'm not exactly sure, but it makes sense to me to not clear these in Atom because you are really losing progress. You are completely deleting your information and starting from scratch. So you don't want to do that. The idea of warm restarts kind of works really well with these moments already existing, okay? It's like when we zoom out and we introduce this little bit of noise and variance with the learn rate, we need some sort of anchor that gives us the direction to go in of our our already found kind of ballpark. And that's what this is giving us, right? It's pulling us in a certain direction. Okay, and that is why when we update our weights, we are using these values, the M and the V. Okay, so what is happening with the correction? Okay, so this is the part where I'm just going to talk straight from the paper because otherwise it isn't going to make sense. Okay, so the whole point of the bias correction, okay, according to them, is that there is initialization bias. That is all that it means. It means that our M and our V start at 0. Okay, now let's think about this because we have this calculation here, right, with the beta 1 times the current value, okay? Now suppose that current value is 0, okay? What they suppose is that these moments are, the mean and the variance are now weighed, biased towards 0, because they are initialized at 0. And so to combat this, they introduce this correction value, okay? And so that's exactly what the bias correction is talking about, okay? So this is, this is what they say here. These moving averages are initialized as vectors of zeros, leading to moment estimates that are biased towards 0, especially during initial time steps, and especially when the decays rates are small, which they are, right? Inherently with the 0.9, 0.999, very small. So this is why they introduced this bias correction, okay? Now, as far as bias correction, I'm not sure how it actually operates, okay? So it's what we saw earlier with this taking it to the power of t, okay? So I'm not really sure because the bigger this b correction goes, I'm not really sure. Well, actually, you know what? If it's beta 1 times the power of 2, that's 0.9 times 0.9. I could see actually this is getting smaller, so I was completely off here in my explanation. This is why this is why I believe, if I was to give a guess, it starts higher and then it decays, is because they need the bias correction more when we're starting out. Okay, so that's That's probably what's happening there. Okay. Now what's happening down here, okay, when we actually update the weights. Now if you recall from SGD, we're doing something very similar, except we're doing something special, which is we're taking the square root of the v, and what I believe this is doing is taking out how we squared the gradient earlier, and all of our contributions into v are that squared value, so it kind of makes sense to take the square root. Now why m over v? Not exactly sure. We may be able to deduce it if we look back here at I'm not going to be able to deduce it. To be completely honest, I'm not really sure what the end is really saying. Okay, so if we think about the mean divided by the variance, what I can guess this is doing is it is doing some interior, I'm trying not to say regularization, but if I can think of what the mean divided by the variance, it's saying, if it varies widely, to scale it back. That's what I can guess by this. Okay. Now, why do we add the lambda and the weight down here rather than into this gradient at the time? Okay, so this is what is called decoupled weight decay. Okay, I also want to clarify, listening back, I did make this misspeak where I was saying, oh, the weight of, is different of the regularization. When we say decoupled weight decay, we are talking about our weights are decaying. Okay, it is different from regularization, but it's doing something similar. Okay, here is the exact code that we are doing here. Okay, so instead of adding it to the gradient, okay, we are adding this down here, right? So this is exactly what's happening down here in the exact code. Is we are adding this exact term down here instead of up here. Okay. Their explanation is honestly pretty confusing. Okay, I'm going to just read straight from their paper. With L2 regularization, both types of gradients are normalized by their typical sum magnitudes, and therefore weights x with large typical gradient magnitude s are regularized by a smaller relative amount than other weights. In contrast, decoupled weight decay regularizes all weights with the same rate lambda, effectively regularizing weights x with large x s more than standard L2 regularization. My way of understanding it is that us postponing the regularization until after we add these contributions into the mean and the variance, we are able to more effectively control the large magnitude values rather than just the smaller magnitude values, which is me just giving that inference based on what they wrote. Okay, so this is was my attempt at explaining Atom, what it's trying to do, okay, and why it is so widely used, which is Atom W is so widely used. Okay, it may be that I am off with this, but if no one else is going to explain it, then I'm going to try. Okay, maybe that I'm off, but it's my kind of goal to at least understand what these are doing so that I can, I might find some use in the ideas later, which, I really want to possibly, take a look at SPSA and try and find some ways to introduce noise or some sort of ideas, not necessarily in terms of the atom optimizer, but as I said previously with warm restarts, I think it's an interesting idea. I hope that this was helpful. I was just listening back to it and realizing that I probably didn't explain it well enough. There are probably many things in the video that it is so incredibly long, right? There are probably things that I misunderstand, okay? But once again, my goal is to try at least, okay? So I just want to end this with a test run with Atom, just to show you what it's like. For this, I'm going to be using a batch size, as you can see here, of 6,432. I'm not really sure what the optimal batch size is. I've tried everything from really small batches of 32, 128, all the way to Andrew Grant's idealized 16,000, okay, that he talks about. I have found that, at least with Atom, I really like the results I've gotten with 6,000, but it may be that with different hyperparameters, other batch sizes might work better, okay? So once again, this is going to have a lambda of 1e minus 7, and that 0.004 is the lambda, and the epsilon is 1e minus 7. The lambda, that it is a peculiar lambda, but I did get that from a machine learning library. So I'm just going to give, just show off the test run and what the results look like, just so that you can have an idea, right? And so I'm just going to run that now. Yeah. I am going through and I'm editing the video. It was quite a shock to me, even knowing how long it is, to just drop it in and then see just how long it turned out to be. It's also pretty funny looking through the beginning, how full of life I am and how energetic and loud I am. To be honest, I really prefer the more quiet, but as I get more tired and more abstract and stuff, you can see me becoming more and more quiet, and my voice starts going out, and I start cracking up a bit at the ridiculousness of the length. Okay, so I'm not going to run it for too long because it's going to lag my bad computer and I'm going to start looking like a slideshow here. But I just wanted to show off what the weights look like just for the first few epochs. Okay, so as we can see, our night values start at mobility of 0, okay, and then we end up with a mobility of the exact opposite, right? And this is the sort of curve you're gonna end up with. Okay, so very similarly, the MG is very similar. Okay, However, this is the benefit of bucketing, okay, is that you get these sorts of curves that have more detail, rather than if you just had one parameter you were shoving the feature set into, okay? So when you have a more specific vector set, you're able to get better gradients. However, as I discussed earlier in the video, okay, once you have a more specific parameter set, you become more exposed to biases in your data set. Okay, what I mean by that is, I'm just going to stop it now. Okay, what I mean by that is that sometimes you will have these outliers that disrupt more smoother kind of gradients, right? For example, this bucket that I have for save pawn push attacks, look at this value, right? Okay, this value should never be negative 0.12, but it ends up that way because we have some term in the data set that has pushed it down with no other points in the data set that have that many save pawn push attacks, because it is a rare feature that you would have that many save pawn push attacks in one move. What this is measuring is how many save pawn push attacks, as in save pushes that attack an enemy minor or major piece. That's what that's measuring. And so having 5 or more of those is incredibly rare. And so within the data set, we end up with a position that turns this negative and nothing can counteract it. Okay, and this is kind of the downside of buckets, and something you should keep in mind when it comes to unbounding it to this extent. Okay, so that's what I just wanted to say, and yeah, you can cap these things at a reasonable value, like at 5, right? And that is a possible way to go about it. Another way to go about it would be simply to collect a much larger data set. Okay, with a data set of 50 plus million, you would be much less susceptible to such disruptions in your gradients. Okay, so I hope that I explained this properly. I know that it's speculative, but as I said, okay, I'm very stupid and slow to learn things, but it is nonetheless, it interests me, the whole machine learning thing. I think in a world full of artificial intelligence and stuff, and all this using external libraries for machine learning and training neural networks, it's all in Python abstracted away in somebody else's machine learning library. I think the joy is trying to understand these things yourself, implementing them yourself, and kind of taking a bit of a marvel at what is happening with the raw math. At the end of the day, that feels like that's what's always interests me, is the raw math. With my Linear implementation, it was creating life out of math. And this is the exact same way. We are creating this kind of self-sustaining learning organism outside of just math. And honestly, fairly simple math. There isn't some crazy math going on. It's very simple. It's just accumulations into vectors that are being used. So okay, well, I hope you enjoy the rest of the video. I'm going to talk about SPRT next, as very tired despite. Okay, thank you for watching. So let's go to SPSA. Okay, once again, all the code is going to be up on GitHub for you to see yourself. Okay, so what is SPSA? How does it differ from Texel tuning? What are possible things that you can do yourself? How stupid is dust mite in terms of okay, this is a quick and dirty implementation of SPSA. Okay, this does not have multi-threading. Okay, I'm too dumb to figure that out. My computer is way too bad to do that. You can barely run 2 instances single-threaded. Okay, listen. So what is SPSA? Well, there's a paper on it by Spall. Okay, and it's this formula. Okay, well, I wish we could there we go, get a nice front and center. Okay, so it's this formula. Okay, we have a step size of CK. Okay, and an A and an AK, not a 47, and an alpha and a gamma. Okay, do I really know what all these things are doing? Not really. All I know is that the CK is basically our step size, and the RK that we'll be using is the contribution of that step size. As far as I understand, you can read this. This is the Perl script that everybody uses to do it themselves, right? I just wrote it myself because I wanted to. I like to have my own tools. So he explains, or they explain what the RK is and why it's better for chess engine tuning than the typical AK. Okay, so they say here is that it's for the last iteration, right? The CK is, and the RK is for the last iteration. So from what I understand, we're deriving everything else from that, as in we're kind of we have the value for the end, and then we are calculating the value for the start and then decaying that over time. So that's kind of how I understand it, is that our variance is going to decrease as we reach the final iteration. Okay, that's the kind of the core of SPSA, is that you are optimizing, and then the oscillations are going to get smaller and smaller as you reach convergence. So what are the problems with SPSA? Well, the problems with SPSA are that it's extremely hyperparameter dependent. The parameters you choose for each of your parameters is going to very highly affect your results, and it's a problem I've had with that. I've had with it. It's a problem everybody's had with it. Okay, it's also there's a list of things and problems with SPSA. A big problem with it is that it is fucking long. It takes a fucking long time, man. I'm not joking. I can leave my my Texel tuner for a long time. Okay, 2 hours. Okay, and get some good results. With SPSA, no. Okay, this takes a long fucking time. Okay, to do 4,000 iterations for me single-threaded, this can take days straight. Like, I'm not talking about a few hours a day. So that's a big problem with it, and so you need to go into it with that expectation. It's not something I would recommend for someone who hasn't done a bunch of testing yourself with your parameters, you kind of want to get them into a good range, a reasonable range, before you go an SPSA. Because also, once you SPSA, all of your parameters are tied to one another. It makes it impossible to, take things out and move things around afterwards, because then you gotta wait a few days. So it's once you get into SPSA, there's no going back. So, however, it is amazing in terms of the things that SPSA finds and the values it will find, values you can never come up with. So it is very valuable. SPSA is used for search parameters. That's what I was showing earlier. It's used for my search parameters. All of these SPIID depth. This is within my SPSA values, which I initialize like this. I copy them straight in and like this. So these are, this was me sanity checking just a small batch that I've been working through. The good thing about SPSA is that it isn't reliant on momentum or anything. So you can pause it at any time as long as you keep the data of what iteration you were at. So that's a really good thing about SPSA. It's cool. At least you have that, the ability to pause it. So otherwise it would be completely fucking unbelievable. Okay, so how does the implementation look? Well, I, straight up copied the Perl script, like, pretty much just translated it into C. Okay, but how do I set it up? How do I set up the infrastructure? Okay, so I have different types here. I have types because when I send it into the engine, I want to cast things to int. Okay, not cast but round them. Okay, it's important to round to integers for things like depth. Okay, values that need to be an integer. Okay, because if you don't round them, then it's going to be biased to going upwards, right? Because if it goes down, then it might go down a lot, very suddenly. So you want to be rounding these things. Okay. Also, SPSA has a problem with magnitude, with things of different magnitudes. Okay. Okay, so you have a parameter. Okay, so this is the structure of my parameter. It has a name. It has a bunch of things here. Okay, which will get filled in later. It has E1 and E2, which is engine 1 and engine 2. This is me sending them out. Engine 1, engine 2 is the same thing as theta plus and theta minus, which I'll get into in a second. Okay, now it has this delta, which is a -1 or a +1. I'll get into that in a second. And it has this type, right, which is just this. Okay. Okay, so these constants for the alpha and the gamma, okay, these are what is in the SPAL paper. This is pretty much what everybody uses. These are just the best values according to SPAL. SPAL, I don't know how old this paper was, but pretty much everybody just goes based on what is in this paper. So that's the exact values that he talks about here. These values, this and there. Okay, so there's that. So now, how do I initialize my parameters? I do it all by hand, so there's no fancy CSV, anything like that. I just do it by hand. Okay, so I have a list of parameters here that I just initialize with a certain name. I have a min and a max. I have the starting value. The AK you leave at 0 always. The CK is the step size for the last iteration, and then this is, I believe, the portion of the step size for the last iteration. I don't know why these are two separate variables. It's complicated. Okay. All right. So I'm going to, this is more general because, to be honest, with the SPSA stuff, I understand it a lot less. There's also much less information about this in terms of, you know, learning yourself, at least that I've, you know, discovered. So when I was searching it up, it was pretty much just the Perl script to go off of. Okay. So we have all of this, all of the different ones. I have found an RK of 0.02 to work good for search parameters. In the Juna script, they say a RK of 0.002, but this is for search parameter or evaluation parameters. Okay. However, if a parameter is very insensitive ELO-wise, one needs to find a larger value for CK. Right? It's hard to find good values for RK and CK. Mine might be completely wrong. But it's important to have a reasonable RK for some of this stuff, especially things like depth, like the depth that something is done at, right? I want it to be able to explore a little bit and not settle, you know, and optimize everything around a bad value. I want it to explore and have that freedom. So that's just what I've found. It's possible that I do some more testing and completely change these and change my mind. And it's possible that you will, you know, watch this video and say, oh my god, Dustmite, those values are way too fucking high. But yeah, so that's just what I've observed. Also, this is like the newest stuff. The SPSA stuff is the newest stuff that I've been doing. So, okay, so I start my engine here. This, I had no clue how to do all this piping shit. It just works somehow. I don't really know how it works, this stuff. I put a comment here. I really no clue how piping works. So, not really sure if this is 100% safe, but I haven't run into any problems with long tuning runs for more than 40 hours on my very bad laptop. Okay? So that's self-explanatory. I have the name of the binary of my engine there, and that's that. Okay? I close the engine here. I use I kill with sigkill. I think that this works. I think. It hasn't failed me, so I think it works. You want to close out those pipes, okay? And you wanna give it the quit signal for the UCI mode, okay? So that's that. I init my fens. I have chess.epd. There's a repository with some EPDs from good, you know, equal starting positions for SPRT and testing, okay? And so that's, you know, this. So I init my fens and I simply just read them in to fens, okay? I have this, which initializes parameters from a file. I have checkpoints, you know, if I leave it running overnight, where it will just write out to a file, like Jan, you know, all of these, right? Where I have a file here where it prints out to a file, and you can restore from this. So that's what this is doing. Okay. Now we have the play game. Okay, let's talk about the loop first. Okay, so what's going on here? So we initialize our params. That's just the huge list you saw earlier. We initialized all of these arrays. Okay. And so we go through, and this is the formula for initializing these things. Okay. We set the value to the start to initialize that. And then the value is what gets mutated. Okay. So this is all the pre-loop stuff that's going on. Okay. This is exactly what is inside of the Perl script. Over here? No, over here. This is what's happening in the Perl script here. Okay. So the exact same thing is happening. I mapped it one-to-one with my code. Okay, the CK, which is the var C end, and times the iterations to the power of gamma. Okay, so all of this is exactly, should be exactly what they have. Okay, so the AK equals the RK times this to the power of 2, and then the A equals the AK times the power of A, which is the number of 1/10 of our iterations, plus K, which is the number of our total iterations, to the power of alpha. Okay, so these gamma and alpha are used for initialization. Okay, and then we enter into our iterations. It's important that you start at 1. Okay, don't ask me why, it's mathematical. Okay, and then we're going to K. It's fucked me up bad starting at 0 also. So it ruined everything for, okay, so probably because of this, or this 0 to the power, so this is how you do the updates every single iteration. You are going to do this for each one of your parameters, all of this. Okay, you want to be clamping between the min and the max. You want reasonable windows for all of these parameters. Very important. SPSA will optimize to fucked up values if you allow it. Okay, you have to kind of supervise it, right? You cannot just let it go all over the place, because it will go all over the place. It will put a thing to depth 0. It will. So keep that in mind. Okay, so what's happening here? Engine 1, E1, once again, this is theta plus theta, right? So for each parameter, we are getting this delta, okay? So this delta is either, it's random, right? -1 or +1 or +1, okay? And then we are multiplying that times the C, times the step. So we are stepping in either the negative direction or the positive direction. And then engine 1 will always get positive theta, which, once again, so it's kind of confusing, but this delta might be negative, right? Basically, it's just symmetrical, right? Engine 1 is getting one of them, engine 2 is getting the other set of parameters, okay? So every parameter is either -1 or +1 step size, okay? And then and then so they end up, we end up just giving one set to engine 1 and one set to engine 2. I'm trying to explain it, but I think it's like a 9-hour video, so yeah. But I hope that gives you, so the value plus that step size in that direction, right? And then the other engine gets the other direction. Okay, but theta plus isn't always positive, right? It's just one direction. Okay, so every new game I play, I start a new engine, okay, and then I close the engine at the end. And so this is this. So you play 2 games every time. You play 2 games, one with engine 1 is white, and then one is engine 1 is black. Okay, you just switch the side, and that's exactly what I'm doing here. And we get the result. It's going to be +1 for theta plus win. It's going to be -1 for theta minus win. Okay, so since it's 2 games that you're playing, right, you're going to end up with either -2, -1, 0, +1, or +2, right? If there's a draw, it's going to be 0, right? So you can end up with any one of those, values out, right? And so that's what this formula is going to assume, that you have it in that order, right? In the range of -2 to +2, where +2 would be theta plus 1, 2 games, -2 would be theta minus 1, 2 games, okay? Okay, so that's how we're going to use here. we are multiplying this r, which is the contribution once again of the step, which is c, times the result, okay, which was that 2, right? Not the 2, but that the result that we just accumulated from the game results, and then we're going to put it over the delta, okay? The delta is this division, by the way. This division does not matter, okay? The delta, once again, is just the sign. It's just the sign. So we are just switching the sign, okay? The delta is either 1 or -1. So that's all this is doing, okay? Once again, this is doing the contribution of the step size, which r is the contribution, the c is the step size, times the result, okay? So we're basically saying, how good were we, right? How good were we for this particular parameter? And then you want to clamp it again, okay? Very important, clamp it. Always clamp it. Always clamp it, okay? I just do this down here. I want to make sure that I'm never losing on time. My engines are never losing on time. Very important. You want to make sure there are no illegal positions. I'll show how I detect this in a second. My engines detect it themselves by giving, oh my god, error. That's that. So I keep track of those statistics, and then down here I write a checkpoint. By the way, I forgot to mention, with all the tuning, you want to have checkpoints, which is what I have down here. I write to binary every 10 epochs. So that's also very important, okay? Because you may have to stop tuning or for whatever purpose. Okay. Alright, so that's what this is doing. We are now going into how do we play the game? How do we play the game? Okay. This is going to be the most fun part, right, of doing all of this. The rest is just formula regurgitation. This is actually us. Now we have the UCI protocol, and we are basically facilitating these, these things that these chess UIs like cutechess and arena and all these do. Now we're doing it, which is it was really fun to implement. Okay, painful but fun, right? So we have 2 engines. We're gonna send UCI to both, right? We're gonna wait until we get UCI okay. I just fgets, okay. Strustra, just it makes sure that we don't have any like trilling spaces or new line characters that are going to get in the way of a string compare. Okay, I believe you want to be leaving a new line character at the end of all of these when you have printf into a pipe. Okay, that. Okay, so this is our UCI options. Okay, so this goes back to what I was saying. I would come back to earlier. I don't have the file open right now. Let's open it. Okay, so this is all of this. Okay, you want to write something similar. So this is once again a C macro. Very, very fun C macro to write. I was very annoyed on stream because I couldn't figure it out. But basically, it takes in this name, right, and then a string compares against it, and then we tokenize the string within the macro. The point here is that we are just that name. We don't have to write a giant if else with that name. We can instead just make it very simple here. All the way down. Just have a macro. This just makes the code a lot cleaner, and so we just have all of our parameters there. Okay, so that's what this does. It just tokenizes it, and then at the end here, what's important is you have this search parameter dot name equals that value that we got, right? So this is the syntax to write it. I didn't know because I'm stupid and I don't understand how to do C macros, but apparently this is the syntax. Okay, it isn't giving me errors now, but it was before. Maybe I had another error and I was just thinking it was, but this is also a way to do it. I think that's why, or something like that, where I think it was a pointer before. Anyway, that's that. that's how when I get a set option command, that's what I go into, right? I just I string compare for the name, right? Once again, the syntax is set option name and then a name and then value with the value, and I always send it as stritod, right? But I don't cast it within the engine. I round it on the SPSA side, which is what I'm doing here. The types have no other purpose other than rounding, right? So when I send it off to the engine, I round it. You want to round it when you send it off, not internally, okay? Because you want the values themselves to be oscillating, okay? Okay. All right. So this is just us processing the fence. This is kind of disgusting code, but I'm disgusting, you're disgusting, whatever. I'm putting a fucking null terminator there. I don't care. This is our time control. Don't do it fixed time per move. Don't be like me. Don't be a dumbass. Do 10 with an increment of 0.1 is good time control. Another one is 15. Okay, 15 is good. 20 is good. It just depends on how long you want to sit here. But with the higher depth stuff, you're, in all seriousness, having higher time does kind of matter when you're doing stuff like, singular extension depth. Okay. So we're getting the fen. We're fen copying. Okay. Get the fen, and we get down here. This is complicated. Is it complicated? I wrote a comment here explaining it, so I don't know, man. Okay, we are simply okay, the way I wrote this is kind of fucked up, okay? So we have a first engine and a second engine, right? And so we assign f white, this variable that says is f white, is as our first engine playing white. So my idea here was really it only matters who goes first, right? So if f white, I'll just make the first engine go first, right? Because the first engine is playing white, so it'll move first, right? And then if it isn't, then it'll go second, right? And then the second engine, S, will go first, right? And so that's how I thought. But then I introduced the fens, the starting position fens. And some of them have black to move. So that just threw a whole fucking wrench in my little cupcake, okay? So what I ended up coming up with, right, is that I have this side, okay, that is a token that we get from the fen string, which is what all of this is, okay? I'm getting the side, which is either a W or B, and then I'm switching it here. Okay. So if it is black to move, then I negate f white. Now, does this mean that the first engine is no longer white? No. The first engine is still white. It's just negating our logic of which one we put first. Okay, so f white has nothing to do with if f is actually white. It just is saying if f goes first or f goes second. Okay, so yeah, I know that's fucking complicated. I kind of wrote it like a jackass, but it works. So it works. And so if f is white, we do this up here because it still matters the time, right? If it's white time or black time, right? When we're sending these things via UCI, we're sending white time and black time. I have to check here if it's white, if F is white, then it goes to white time. Otherwise, it goes to B time. Okay, and we have to do that before we fuck up our semantics here. Okay. The rest of it is standard. So white time, B time, ink. You saw this earlier with when we were going over UCI. Okay, getting these go commands, right? And now we're, the GUI, talking to our engines, playing them back and forth, right? We're sending the position, we are sending the go command, we are getting our thing back. Okay, so if we get a best move, I break out. Otherwise, this is the no move found, is my engine saying, hey, we fucked up. So this is the illegal positions thing. And then we exit out. If it's a loss, we return a -1 if it's F. Remember, F always gets theta plus, right? So if F loses, that's a theta minus win. So that's a -1. It's returning a -1. And then if it's a draw, we return 0. Okay? And then down here. So this is us doing all of the time. We have the time now minus the before, which we calculate the before up here, right? And we just subtract the time, okay? And we increase the F time by the increment minus the time we lost, okay? And then if we lose on time somehow, if F time goes below 0, then we return this, okay? Which it should never happen, okay? That should never happen. Because we have an increment. And in computer chess, if you have an increment, you should always be able to play a move in 0.1 seconds, okay? So, and then with our move, we get our move, right? This is just if somehow there's some error, right? We're going to close the engine. We get the move. And then, we tokenize the move. We get the Sterling of the move. We get the end and then do the null terminator. What this is, it's actually just adding a space at the end of the move. It's super fucking janky, but it's cool. So it's adding a space at the end of the move and then adding a null terminator and then concatenating it onto our moves so that we are adding the played move every time. So that's pretty much the entire implementation here. Man, my voice is fucked. That's the entirety of the implementation here, and I am just going to compile it and show you what that looks like. So let's just get this ready. So what I have to do here is I want to compile the engine, a version of it without any of this stuff, because what I have is that it prints out the current board, okay, because I want to see what's going on, okay, but I don't want any of that other debug information. It's going to print out a lot, right? So what I do is I just come here and I want to compile this to 14, okay. And this is obviously not that, that's that, and I think that's it. I thought that I would never get done with this, now I've got to sit here and I've got to edit it. I doubt that anyone is ever going to sit through the whole thing. But nonetheless, I recorded it and I left it here as an artifact for anyone who has the same questions I had at some point. I'm sure that some of the information in this video is speculative and wrong, but then I urge you to correct me and enter into, a conversation, and, yeah, I mean, I really loved making my chess engine. When I was a child, there was this person in a position of power who laughed at my chess program. And it stopped me programming for years, And so my big fuck you is making a strong chess program to him. And that's what this is. And I think I'm satisfied in some mad scientist sort of sense with it. And that's this. And my engine is fighting itself, trying to improve. This Sisyphean task of getting better in life, what I refuse to do. Well, we have a Discord where mainly, they talk about graphics programming and stuff. Because I am notorious for graphics programming. Why has it stopped? Oh, my entire computer is lagging. Okay. Well, I was gonna do like this cool, talk while it's going, but unfortunately, my computer doesn't allow that. So, you can join the Discord and talk and send me a message if you have any questions. If you don't want to leave a comment, if I know a lot of people just want to talk one-on-one, and that's completely fine. I'm always open to that. I don't know what my plans are next, in general, beyond just the engine. I do want to make more content like this, of just sort of just, explaining what I know, but, it does take a lot fucking out of someone to get to this point, especially, with how hard it is to drill some of this into my fucking head, It's kind of hard to reach this point, it's sure this video is however many hours, probably 9 at least, right? But so it's kind of hard to get to this point because, yeah, sure, this was however many hours, but it's thousands, leading up to it, so I do want to go back and revisit the game engine for sure, but I'm a sort of a programming artist sort of guy, and it's not that I have given up on graphics programming or my game engine or anything like that, and it isn't like I've fallen out of love with it or that it's just the code base is too messy for me to deal with or anything like that. It's it feels like if I improve something more, it'll stop being mine, Goes back to this kind of this feeling of not necessarily wanting control, but realizing that improving something maybe isn't I don't know, would inherently change the quality of it, of what it means to me, and that's the point that I was getting to with it, where I was optimizing things, where I was getting ready to do all these changes and building this structure that would export to a format where you could open it up in Blender, and I just got to a point where I was it's no longer mine, I think I looked at all of these other things, these other shiny things, and then it no longer was, but I do want to come back to it and work on it again, but I don't know. I'm kind of somebody who just kind of like transiently, goes through life. I've never been someone who does, one thing. I think that that's probably tied to my bipolar crazy nature of like, that I just like, so I always end up, just packing my shit up and going, I think that kind of, same sort of, is this sort of, there is no reason for me. There never is a reason. It's more like there's just something else that I need to do, and for me, I don't know what that next thing is that I'm going to need to do. I think perhaps I may try and do these experiments with SPSA. I think my idea with this SPSA thing is maybe to apply the idea behind warm restarts to SPSA. I think it's a really cool idea, but I don't know how I would go about applying such a thing. But I do think it would help, because what I've been noticing with depth is once we get past a certain amount of iterations, we will sink into I don't know what the word for it, maybe it's that minima that everybody keeps talking about, but we find a way to sink into some strata where we're unable to change our course anymore, right? Where we reach a certain depth with some parameter and now it's suboptimal, right? But every other parameter now has is optimizing towards that suboptimal value, because it's such a binary thing, the depth, right? Where it really is only choosing the depth based on theta plus theta minus, like maybe 100 out of 10,000 iterations, because that's the only point where it reaches the exact line where it's straddling both. So yeah, it may be that like most other people just SPRT their depth and things like that. I didn't really talk about SPRT as well. There's a lot of good. You can go check out the I'm gonna leave a lot of links in the description. Check out the Rustic, chess engine, Rust book about the SPRT things and the rest of it. That's a big help at explaining some of this stuff. But yeah, I don't know. I hope that I've helped someone. I hope that I've helped someone. But yeah, I guess these are like my closing remarks on the entire video. Once again, the code, I'll try to get it cleaned up and get it uploaded. Yeah. Thanks. I mean, I just want to say thank you to, if anybody reaches this point, but, thank you to everyone who believes in me, the people who continue to talk in the Discord, and the people who, always have believed in me, from the beginning of me, making my coding projects public on this channel. I don't really have any other words, to describe, how much it means to me. That, I kind of have what so many people don't have, is that sort of, the people that believe in me. It's something that I didn't really have like most of my life, and so kind of is like this sort of push and pull with the not wanting to let people down, you know. There is that, you know, where I'm sad that, you know, you may not be as interested in chess programming or, you know, what have you, you know. And so there's that as well. But yeah, you know, that's all I really have to say, is that it, you know, so. And yeah, I mean, whenever I start my next project, I will go live more, because I haven't been, because testing this stuff is impossible to do with my computer live. As you may know, my computer is awful, and so going live is hard enough, you know, with the amount of shit that I have to do. It's hard enough to the point where, you know, launching instances of my engine is very, very hard for me to do live. But funnily enough, the last time I was live, I crashed my computer when I was writing this SPSA thing. It was so funny. Yeah. Yeah. Okay. Okay. I mean, rock on. Yeah, if you have any corrections, any questions, you know, I'm always here. Once again, all of the resources, all of the etc. You can join the Discord. Yeah. Man, coding is fucking cool, man. Coding is fucking cool. Okay. Yeah, it's gonna be a task to edit this, but hanging up my coat, man. I wonder how people are gonna react when I upload this fucking insanely long video. This is taking up like half of my hard drive. Okay, well, peace out. Peace out.